T, 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 T. Hello, hello.
Okay, good morning. Welcome to the last day of SPLASH'. We'll have some announcements, most influential paper, student research competition, artifacts, and a pitch on UPSLA 2024. So we'll start with John for the most influential paper.
Thanks, Vasco. All right, my name's Tony Hosking. I am here representing the SIGPLAN Executive Committee as one of two co-chairs for SIGPLAN Awards. The other co-chair is Ishil Dillig. She's unable to be here. She would normally present this award because she does chair the committee that selects the most influential papers for UPSLA. We're here to present the most influential paper of UPSLA 2013. This is presented annually to the authors of a paper presented at the UPSLA held 10 years prior to the award year. The award includes a prize of $1,000 to be split among the authors of the winning paper. These papers are judged by their influence over the past decade. And the committee is formed from the program chair and general chairs of the instance from which the paper was drawn, as well as the program chairs and general chair of the conference 1 year prior to this one, so last year's general chairs and program chairs. So that is the committee there that you can see on the screen, and I'm very pleased to announce that the winning paper is Empirical Analysis of Programming Language Adoption by Leo Meyerowitz and Ariel Rabkin. Neither of them is able to be here to accept the award in person, but of course we do always announce at UPSLA, that's the tradition, and so we're very pleased to recognise this paper as the winner of this year's award. There is a citation that goes with the paper, and this will appear on the SIGPLAN website. And here's the citation. Some programming languages become wildly popular while others fade away. This paper seeks to answer why by performing an empirical study spanning hundreds of thousands of open source software projects and interviews with thousands of programmers. The methodology used in the paper is thorough, and the paper provides insights of interest to the broader programming languages community. Overall, this paper is a role model for large-scale empirical studies of programming languages, making it worthy of the UPSLA 2013 Most Influential Paper Award. And in spite of the fact that the authors are not here to receive their award, I think we should at least give them some applause.
Okay, hello everyone. I'm Xu from the University of Toronto. I'm co-chairing with Justin from the Hong Kong University Science Technology on the SPLASH' 2023 student research competitions. With numerous effort from our judges, reviewers, as well as, of course, the student participations, I'm very glad to share the winners. For the undergrad category, we have the top 3 winners are Julia Freeman from Fraser Mason University, Holly Ye from McGill University, and Riven Raku from Barnard College. I'm not sure. I know some are remote, but if you are here, can you please come to the stage? I'll photograph the next. And given the competition was only finished last night, so we haven't got the certificates printed, but it'll be video soon. Yeah, congratulations. For the graduate category, the top 3 place winners are Jesse Halberg from KU Leuven, Marta Divina Mate from the University of Southern California, and Antonio Zigarilli from the MD Software Institute. Congratulations. And if you're here, please come to the stage. Yeah. Congratulations, guys. Yeah. Okay, sorry.
I did not realize we have a photographer. So we also have some awards to announce, so get ready. You might need to come up. Okay, OOPSLA this year had an artifact evaluation committee. Guillaume and I co-chaired, and let us tell you all about it. So we received 81 submissions. These were split between the 2 rounds that we had for OOPSLA, about 20 in the first round and 60 in the second round, and this is on par with last year. Almost all the artifacts were accepted in the sense that they were awarded a badge from the committee. So 44 artifacts had a clear case for being reusable for other researchers to build on, and 29 others were judged to be functional. And these acceptance rates and numbers are also on par with previous years. So some things that worked well. There was a 1-week kick the tires period after each round. During this period, comments were completely open between authors and reviewers. And this helped us work out through issues right away. And it also helped other reviewers. So if you were the second one to review the artifact, you could see the errors that the first reviewer had encountered. So this was good, and we should continue to do this, have open comments in future years. Another thing that worked well was reserving space on Cloud Lab. So Cloud Lab is free for any researcher to use. It took a little bit of prep work just to say register an account for the artifact committee, but then we had several machines that once in a while they helped us get a machine that was just big enough to run the artifact. So Cloud Lab is good. What happened for the artifacts that did not receive a badge? Well, the 2 common problems were lack of small examples. How do I get this running when I don't have the resources for the full multi-day experiment? And issue 2 was it's unclear what's the scope of the artifact or how do I proceed with a step-by-step evaluation. Now, if I was up here 3 years ago, the issues would have been we couldn't get it running at all because the authors didn't provide a VM. That's no longer an issue. We were able to get most artifacts up and running, so that's a great step forward. Okay, statistics out of the way. Now we get to the exciting part. The past 2 years for AEC have been very different because the AEC was combined with the External Review Committee. Everyone who reviewed artifacts also reviewed papers as part of the OOPSLA PC. Why did we do this? To solve 3 problems. First, recruiting. So normally an AEC is made up of junior PhD students, and there are only so many of them in the world, and there are 4 conferences now competing for them. So we want to make a better offer to get people to join the committee. Second is to hopefully help with the review workload. In order to review an artifact, you need to understand what are the claims in the paper that the artifact should support. And this basically requires you to review the paper. So why not review the paper beforehand, and then you're in good shape to review the artifact right afterward. And then third, we have a hope of at some point opening up more of a dialogue between the PC and the AEC. We made basically 0 progress on this third point, but it's something to keep in mind. Point 1, recruiting, things worked very smoothly. So we sent out 100 invitations, we had 60 accepts, I think a very high rate, and 58 people were able to 58 of those accepts were able to participate in the end. And we had a very distinguished AEC, very qualified, made up mostly of postdocs, some assistant professors, and senior PhD students who were close to graduating. Yep, that's all to say about that. Okay, point 2. I think that the workload and the combined AEC, ERC was a good decision, but better yet, let me tell you what people who participated thought. So we sent out a survey right after the AEC was finished. We received 28 responses, so keep in mind that this is a small fraction of the whole PC. And let's go quickly through these graphs. So first, did the ERC offer affect your decision to join? Yes, that was a good incentive. Did ERC work help with AEC work? Sometimes. 50% say yes. So what was often the problem was you review a paper for OOPSLA, there's a low chance that it gets accepted and a slightly lower chance that it goes on to submit an artifact. So in the cases where we did have overlap, the work typically helped, but that wasn't always the case. So one idea One idea for future years is to ask PC members to submit requirements for what should an artifact support. I'm not sure who is going to do that work or when it's going to happen, but it would satisfy the same goal that we had with ERC AEC. How was the review load? That was okay. We did ask quite a lot for AEC members because you're reviewing papers on artifacts across 2 rounds. But this middle of the road, this is fine. Were the guidelines for the functional badge clear enough? Mostly yes, but we have some no's. So how do we fix this? The main point of friction is this question about whether the functional badge means that we have fully reproduced all the results in the paper. So my take is that the functional badge should have a slightly lower requirement. There should be running code that's relevant to all the parts of the paper, and this is in line with what the ACM functional badge is. It's not in line with the old SIGPLAN badge. So what's going on here? 2 years ago, we switched from SIGPLAN style artifact badges to ACM style badges. So now there are 3 possible badges that the ACM will offer. One is the available badge, which does not go through the artifact committee. The second is the functional reusable badge, which currently goes through artifact evaluation. And ACM has a 3rd badge that OOPSLA does not currently support. That's reusable and reproduced. That's reproducible and replicated. We cannot do replicated, but we could do reproduced. And if we offered reproduced and functional as 2 parallel tracks, that would solve the friction that we saw this year. I want to bring up one comment that came up in the survey. So here's AEC member says, I would say the bar for getting the badges should be a bit higher. Some artifacts barely ran and needed so much time for reviewers, but they still got functional. For what it's worth, I disagree with this comment. I think if an artifact comes in and it doesn't run, and through feedback with the AEC we get it into a runnable state, then the AEC has made a huge contribution for future users of that artifact, and I'm sure the authors are grateful too. This is a valuable piece of service. Were the guidelines for reusable clear enough? No. So what's going on? There's many different ways that an artifact could be reusable, and it depends on what the artifact is trying to accomplish. Reusability for a binary is different from reusability for a library. So what we propose for future years is to have authors of the artifact submit a guideline for in what ways do you think that the artifact is reproducible. It's the same idea that we currently have for functional, asking for step-by-step instructions. So step-by-step instructions for reusable is something that we should have next year. Okay, now for the awards. We want to recognize 2 distinguished reviewers who not only wrote excellent reviews, but also went through some painful times. Rob Sasson and Shiwei Wang. If you're here, please come forward. So Rob took the lead on the discussion for several artifacts where, first, the artifact was not in his area of expertise, and second, the artifact was borderline. So Rob's extensive reviews and comments helped us reach decisions. And Shiwei helped us find a critical piece of hardware to evaluate one artifact. And this was not so simple as digging up a computer that was in the corner of his lab. He went through several rounds of trial and error before he finally found something that let us judge the functionality of the submission. Second, we have distinguished artifacts. So if you're here in the audience, please come up for a picture. We have 4 artifacts here that were of exceptionally high quality. So first, they were nominated by AEC members, and then Guillaume and I reviewed them and confirmed that these are top quality artifacts. So if you're a student in the audience and you would also like to write an award-winning artifact, make sure to look these up. Anyone here? Let's thank them again. OOPSLA next year will also have an artifact committee, and I'll turn the mic over to Guillaume to say a bit about it.
Hi, so I'll be super brief. So the evaluation next year will be similar to the previous years, so with a kick of the tire period of 1 week and a full review of 1 month. The main message here is that we are always looking for motivating people. So if you are interested in participating in the Artifact Evaluation Committee, please contact us for next year or the years after that. Next year, the external review committee, or the review committee and the artifact review committee will be separated. So anyone can apply, like PhD students, postdoc, faculties, please reach out. And for the authors, there are 2 new requirements in the description of the artifacts for next year. One is that we ask that you have an explicit hardware requirement section at the beginning, so we can quickly filter through artifacts that reviewers cannot review. And the other one is, as Ben said, a reusability guide to help reviewers for that. Thank you.
Okay, hi everyone. I'll be quick. We're still in the middle of this amazing SPLASH 2023. I've been having a fantastic time, but I wanted to whet your appetites for SPLASH 2024, which will be next year in Pasadena, California. You can see the dates up there, very similar to this year. So I'm Manu Sridharan, I'll be the general chair, and Evan Chang and Alex Potanin are the review committee chairs, so we wanted to all show our faces in case you had any questions. So yeah, maybe some of you know about Pasadena it's very close to Los Angeles, but based on Alex's suggestion, I contacted the Tourism Bureau, who put together this short sneak peek video. Let's hope that this works. Okay. Whoops. One time is enough. So Pasadena is about 11 miles from downtown Los Angeles. It's well served by air. For those of you coming internationally, probably LAX is your best option. For those of you in the United States, there are some other options. Burbank, Ontario airports are all pretty reasonably close by too. We have nice weather. The average high temperature in October is around 83 Fahrenheit, 28 Celsius. It's very pleasant, not too hot. It's really nice. So right nearby in Pasadena itself, we have great restaurants, coffee shops, shopping, and also some sites to see. We're very close to Caltech University. It's a beautiful campus to just wander around. There's the Huntington Gardens. There's Norton Simon Museum, which is really nice. And then, of course, there's the broader Los Angeles area, which is more famous, and there's plenty of things to do. We can get down to Disneyland if you'd like. There's lots of art museums. There's the beaches if you want to go a little further afield. It's a really great location. Our venue is the Hilton Pasadena, and I wanted to note that we have a very high walk score. So this is right near Old Town Pasadena, the downtown area. There's plenty of places you can just walk to. So I know LA, it's like, oh, I have to drive everywhere. This is one of the places that's an exception to that. You'll come and you'll be able to walk to lots of different things right near the hotel that are very interesting. And then I wanted to share who's on the organizing committee thus far. We'll be, adding more people to the organizing committee soon as we do more planning. Alex and Evan are here, the review committee chairs. Guillaume is here, the artifact evaluation co-chair. So come talk to any of us if you have any questions, and we hope to see you there. Thank you.
So we have 7 minutes until until the invited talk. So I'm not quite sure what to do here. Shall I sing a, shall I sing a song or? But I suspect you shouldn't start ahead of time, right? Because we'll be broadcasting and everything. So yeah, so we'll wait 7 minutes. What do you say, Mira? What's it? Yeah. Pardon me?
ring the bell. We need to ring the bell. Well, people are here, but I have to go outside.
Sure.
Okay, let's start. Good morning. Here I am back on stage to introduce our wonderful keynote speaker of today, Amal Ahmed. She did her bachelor degree at Brown, went for her master's at Stanford, went back to the East Coast for her PhD at Princeton, and after several postdoc positions at Cornell, Harvard, what else? Assistant professorships at University of Indiana, and even a position at INRIA in France. So she has been quite around. Now she is professor of computer science, of course, at the University Northeastern University in Boston. And her research focuses on using programming language semantics and type systems to reason about imperative programs, to reason about properties like security, concurrency, behavior, and so on. And more recently, she has been working on verified compilers, and especially on verified compilers that or linking in the compiler that kind of link to code in other languages. And that's, I guess, the topic of today's keynote, bringing all languages together. And I don't know about you, but I'm very excited to hear what Amal has to say, because these kind of languages are the only relevant languages today. And we need to address this interplay between different languages. So with that, and without further ado, I'll leave the stage for you, Amal, and very happy to hear what you have to say.
Thank you so much, Mira, for the wonderful introduction. Yes, as you heard, I've hopped around an awful lot. It's interesting to sort of see it come, read out. Okay, so my group for the last decade or so, we've been working on a lot of things that, in the early days were about, how do we do compiler correctness in the presence of linking? Like, how do we even state compiler correctness when you need to link code that comes out of your compiler with code from a completely different language? But more recently, we've been thinking sort of more in terms of the formalisms and frameworks that you might need in order to verify, FFI implementations and so on. Often this takes a very formal theoretical bent, but with an eye to how do we even develop the techniques that could be applied to a practical setting. So that's what I'm going to talk about today. So let me just dive in. Well, I thought I'd start with a slide of a lot of languages. There really are a lot of languages out there. Ultimately, what we'd like is the more type-safe languages on this slide, like let's say OCaml, Java, Haskell, etc., and Rust, to interoperate safely with the much less richly typed or unsafe languages on this slide. That's sort of like the overarching goal here of a lot of the things that I think about. Okay, so let's start by talking about, right, so it always becomes about protecting the type-safe languages from the unsafe languages. So let's start by talking about type soundness, right? So for many of the practical languages that you saw on the last slide, we have people in the PL research community who at least, will take a core of the language, be it ML or Haskell or Java, and they will verify type soundness, typically using progress and preservation, but at least a core of the language has been proved type sound, right? But then, this is the theory, what happens to type soundness in practice? That's really the question. Right, when you go off and you implement ML in OCaml or Haskell or Java, you ultimately have to support a foreign function interface that allows you to interoperate with code in other languages, right? So this might be C types for OCaml or inline C for Haskell or the JNI for Java, right? But you have to implement these. But when you implement these, they're essentially escape hatches to type soundness, right? They're letting a lot of unsound behavior in. in. Essentially, you're linking with C code or native code. And you don't really go ahead and again prove type soundness in the presence of these FFIs. We do a lot of stuff to, implementers, designers of FFIs do a lot of stuff to kind of produce guidelines, give advice, to design these things in a way so that we are doing a best effort. But it is a best effort and it's not verification. So I'd say that, not the meta-theoreticians, but maybe the working meta-theoreticians need some sort of a technique for proving type soundness of languages as they're implemented, or perhaps for proving soundness of the language plus the interop, or soundness of the FFI. So that's what I'm going to talk about in sort of like the first part of this talk. So all of these languages, interoperability, all languages support interoperability. I've already talked about some of these examples. At the bottom of the slide, I have two categories which, you might not, like a bunch of languages that compile to the JVM support interop at that target level. Languages that support that are, in the .NET family that target the CIL will support interop at that target level, right? So all languages support interop. How do we do type safety? Now, I want to go back to a seminal paper, a paper that I consider pretty seminal. And this was Jacob Matthews and Robbie Findler, Popple 07. They were sort of the first to say, there's a lot of language interop out there, right? But ultimately, all the work that was happening in that space, at least in 2007, was about how do we implement these things? People work on SWIG and so on, right? Various tooling for interop, but how do we understand the semantics of interop? And they gave this very nice framework. Where basically they said, suppose you have a language A and a language B, a red language and a blue language. If you want to, let's start to put them together and actually define how we want them to interoperate, or how we expect that they interoperate. Now, this is at the level of two source languages, right? But the basic idea was that you want to introduce two boundaries. You want to put the two languages together and add two boundary forms to your language, which lets you embed code AB, lets you take the blue code from B and embed it into an A language context, so it's surrounded by A language code, and vice versa. BA boundary lets you put this red term from the A language in a B language context. So, so you're literally plopping code from one language in the middle of another. But there are sort of types on the two sides to say, oh, the term with this red type, is embedded in a blue context, which expects it to convert to this particular blue type. Like that's the idea. And then they gave typing rules for the boundary terms, which capture the idea that I just said, right? The types on the two, like if the term on the inside has this red type tau, then the term on the outside has a particular shape of blue type tau. And then the interesting part was they gave a sort of very standard methodology for type-directed, for this operational semantics for boundary terms. So how do you run a boundary term? Basically, you just run the term blue E according to the blue language semantics all the way until you get this blue value V. And then comes the interesting part. How do I convert from blue language to red language? That's the part that you have to do. As the multi-language designer, you have to say what, so let's say you have, let's say the number 5 is blue and you're converting it to binary or something, it's 101, right? But you can do this for functions, closures, higher order stuff as well. Okay, so that was this paper, and it's been pretty influential. Oh, and then you can just, now you have one language, you can just use standard techniques, progress and preservation, to prove type soundness of the multi-language. That was also a very, very nice part. Right now, you can use standard techniques. So this was very influential. It's led to a whole lot of people building on it and designing various multi-languages. I think the most effective part of this thing was that it gave you a recipe, a framework, and then people could go off and apply it to more and more interesting language pairs where it wasn't really clear how to do the conversions across the boundaries. And so, but it gave people a way of focusing on the interesting part of the problem. Anyway, but let's fast forward. The point I want to make is that this is excellent work, and multi-language semantics helped us understand or formalize source-to-source interop really well, but that's now not how FFIs are implemented. Okay? So I want to talk about how interoperability is typically implemented in practice. So let's say we have a blue language and an orange language. We have source code in each one. Essentially, what the FFI implementer is doing, you're compiling the code from each one of those languages, and you are, implementing an FFI means producing the glue code that is going to do the conversions from the blue language to the orange language, and vice versa. Right? That's what ultimately needs to happen. So there's glue code there. How do we know it's doing the right thing? So that's what I want to talk about. We need basically some sort of a framework that helps us design FFIs, at the source level and implement them using glue code at the target level. And we need a way of verifying sound language interoperability that is actually connected to this, form of implementation, this kind of implementation. Okay, so let me talk about a framework or a recipe for doing that. So this was work that appeared at PLDI 22 last year. Here's how we advocate doing that. So suppose you're an FFI designer. How do you even start? Let's say both languages are typed. What do you do to start off with in order to define interop between these? I'm going to phrase it as I'm going to add some sort of a boundary form. I'll stick to this generic form of boundary, which essentially lets me put orange code inside blue context and vice versa, just like I was talking about. I'm just using slightly different notation. And then the main thing that you have to do, the decision that you, the FFI designer, has to make is which types in the orange language should be convertible to which types in the orange language. Okay? I'm going to capture that with this abstract convertibility relation. You might decide ints are convertible to ints, strings of this particular format are convertible to strings of that particular format. You would never say that a function should be convertible to a pair, right? So basically, you give a set of convertibility rules of which types in language A make sense to convert to which types in language B. And again, I'm talking at the level of a framework, so I'm abstracting over details and trying to capture the essence. Okay, so the idea is then that if you have an orange term of tau B, and tau B is a type that's convertible to tau A, then I can put it inside the boundary. The person writing the code can put it inside that boundary and use it in a context that expects a tau A, and vice versa. Okay, so decision one, specify convertibility rules. Which types are convertible to which other types in the other language? This, then second step is you have to implement the target level conversions for each pair of convertible types. So for every convertibility rule that you gave, you have to specify, what's the glue code that's actually going to take the compiled thing that used to have type tau A and convert it to something that has the right shape as a tau B, but at the target level. Right? So these are target level conversions. I'm going to write them as these functions C that are, you should think of as the glue code that converts from a blue type to an orange type and orange to blue. I'll get more specific in terms of those types later. Okay. Now, I want to prove soundness of this entire FFI design and implementation. And this is sort of the novel idea. To do that, we want to define something that I'm going to call a semantic intermediate language, or semantic intermediate representation. How do we define this semantic IR? We're going to use, sort of insights from semantic models of type systems that, we've been working on for the last couple of decades, really. But here's the basic idea, even if you don't know what a semantic model of types, et cetera, looks like. Basically, I want to say, given a blue type, what are the shapes of all of the target terms or target code that behaves like that type, right? So if the blue type is an integer, then the terms that inhabit it, or at least the values that inhabit it, will be some representation of numbers. If it's string, it'll be some representation of strings. If it's a function, it'll be some representation of a closure in the target language. Okay? And then there will be further constraints on how they behave when they run. But essentially, this is a logical relation. For those of you who know about logical relations, it's just a semantic model of source types, as you want to think of them as the sets of target terms that behave according to the rules of those types. Okay? But these are target terms, and we're saying when they inhabit the source types. That's the key novelty. Okay. I want to visualize this just a little bit. I want this picture to sort of sit in your heads. So for all these types in my orange language, for every type tau, I'm basically defining a set at the target level. What I'm doing is, the entire IR at the target level, or I can say IR or I can say target, is a big language, but essentially a semantic model. The semantic IR is cutting it down to a sensible space. That dotted orange circle at the bottom essentially includes all of the behaviors that actually exist in this, that correspond to something you can do in that source. Okay? So we're cutting out the junk. Okay. So now, once you have specified this sort of semantic IR, this semantic model, you can prove conversion soundness, okay? So for every convertibility rule that you had in your language, you said a blue type is convertible to an orange type or vice versa, and you wrote the glue code for it, here's the theorem you have to prove in order to prove soundness of your glue code. So if blue tau is convertible to orange tau, then given any target code that inhabits the set of the blue tau, right, that behaves like the blue tau, if I wrap that code with the appropriate conversion wrapper from the blue type tau to the orange type tau, then that code behaves like an orange type, belongs to the set that is the orange type, and vice versa. Right? So give me something that behaves like a blue thing at the target level, and after I put my wrapper, my glue code around it, it will behave like the orange thing. That is the sort of, given your model, that is the ultimate definition of, yes, I have taken behaviors from this type and turned them into appropriate behaviors in this other type that this other language understands. Okay? All right, so that's the key thing. And once you have that, you essentially, you keep turning the crank for the way you do these logical relations, and you prove soundness of the entire system. Okay. So yeah, this was in this paper, if you're interested in details. What I'd like to do next is, I'm just quickly going to say what we did in this paper. This paper was about a framework. So we did 3 separate case studies in the paper. The first one was, we looked at shared memory interop and kind of data representation. So basically, when is it safe to share mutable references or mutable data structures across 2 languages without copying or wrapping? Once you start building these semantic models, you as an FFI designer can actually make much better decisions about what you want to allow to be converted from one language to another. Some things might be way too expensive to convert. So you can choose not to include the convertibility rules for those things if it's really, really expensive to do that, or if it's expensive to do that safely, let's say. So we discussed some of that in the paper. We took a look at a language which essentially looks like ML, and another language which has, which we called AFI, which makes sure that you cannot use a resource, affine resources or affine types, in which you cannot use any affine resource more than once. Though you can use it not at all. And that basically is, safe mixing. We use runtime checks to ensure that any affine resource is not used twice. Actually, I'll go into this in more detail because it's sort of the simple case study that I can walk you through. And then finally, this was the most interesting one, and the thing that we are really sort of proud of, which is we looked at 2 languages which have very different memory management strategies. One is a garbage collected language, basically like ML. And the other is L3, this language which essentially you can think of as a core of Rust that only supports Rust's sort of ownership discipline, doesn't support borrowing, etc. But it has a type safe, the type system essentially guarantees that you can safely free memory, you can safely change the types of data stored in a memory location, and so on. So yeah, safe interop between a GC'd and a manually managed language was this final case study. Okay. So I'm going to go into, I want to walk you through the recipe with an actual concrete example. Doing the GC'd and manually managed language is a little bit too much for, for a 1-hour talk, and so I've picked the middle case study. Okay, so this is just, you don't have to read this. It's just, I'm trying to say give you a flavor of my 2 languages. One has the first one, MiniML, has polymorphism and references and pairs and all those things. AFI is basically a standard affine or substructural language. It has, these lolly types, tau 1, lolly tau 2, and so on. Okay. The key thing here in the syntax, again, the rest is completely standard, is just that we're adding these boundary forms so that we can embed code from one language into the other. Okay, I'm going to compile to a rather high-level target, okay, because, again, showing you low-level code is going to be too difficult. So I'm compiling to essentially a lambda calculus. You can think of it as scheme if you like. It has references and memory allocation because our source languages well, one source language has references. And we give ourselves a way of raising errors. So there's fail, and you can fail with a type error, which would be like a scheme-like error, a runtime type error. And this conversion error, which is something that only the compiler will use in its glue code. Okay? And so the moral here is going to be that when we interop, conversion errors need to be caught, and they are okay. Type errors should never arise because you have two type-safe languages interoperating. Okay? All right, so this is just for those of you who haven't seen affine languages or typing rules, this is just to say that the context omega keeps track of all of your affine variables. Those are the ones that you cannot use more than once. So you have to appropriately split the context so you make sure that that resource is never used more than once when you're type checking the application term, two subterms. You can't reuse the same affine variable. Okay, so, and again, I'm trying to present this in a very recipe kind of way. What are the steps that we need to do, right? So those were the languages. Now let's take a look at the compilers. So again, the compiler for MiniML is going to be very standard. We're just compiling MiniML to essentially the lambda calculus, right? So mostly what we're going to do is we're going to erase types. I mean, you can see some of this right here where you have the two terms that involve polymorphism. We're just leaving that as a suspended computation and forgetting about the types. The interesting bit is really just the very, very last line. When we encounter one of these boundaries, we say, oh, go ahead and compile. I'm writing plus for the result of compiling. So go ahead and compile the orange term, and then wrap it with the glue code wrapper so that you can convert it to the appropriate blue term. That's exactly what we expect, right, for the boundary terms. They need to be implemented at the target level using the conversion functions that you have. Okay. So I wanted to show you how we're compiling the affine language. It's a little bit more interesting. Basically, any affine resource, you want to make sure that it does not get used more than once. Now you're in a target language where you cannot, you don't have any type mechanisms to ensure that something is not used more than once. So you have to use some sort of dynamic mechanism to ensure that. And what we do is we have this thunking kind of operation. For every affine resource, we're going to wrap it in this thunk. Basically, we allocate a new flag reference cell, if you will. At the beginning, the reference cell says, oh, this affine resource, the one that I'm protecting, it's unused. Then when you call it, if you call it and it has already been used, then you you fail with a conversion error. If it hasn't been used yet, then you set it to used and return the thing that you were protecting, the underlying term. So you're just making sure that that flag makes, reports a failure if the affine resource is used for a second time or a third time, etc. Okay. And then the compiler basically uses this in all the appropriate places. Here, because this argument E2 is being passed to a function that expects an affine resource, we wrap it or thunk it before we pass it, and so on for the other things. Okay, now let's talk about what types from one language should be convertible to what types in the other language, right? So start really simple, and you don't have to read like all the C stuff. It's just boilerplate. Basically, what I'm saying is, the FFI designer will decide that unit in one language can be converted to unit in the other language, right? In the second case, it's pairs, and I will have to go implement the C functions or the glue code functions to do that. So I'm just saying that they will be done. Just look at the pink highlighted part. I guess the interesting part here is that when we implement the conversion from unit to unit, it's just the identity. You don't have to change anything, because unit is represented the same in both languages. And for pairs, we just sort of recur, right? So we say, you have a pair, E. OK, let's extract the first thing from the pair and convert it using the tau1 to tau1 conversion function. And let's take the second component and convert it using the tau2 to tau2 conversion function. So it's all very standard, is what I'm trying to convey. OK. Now I want to get to this interesting part. What do you do for functions? Okay. Now you'll notice here that I'm basically making the decision that tau1 lolly tau2 from my affine language, which promises to use the tau1 at most once, right? That's what the type means. When you convert it to ML, you can't give it some blue tau1 to tau2 type. You have to give it the type that's, I expect a suspended computation, or a thunk, right? So essentially, I'm expecting my argument tau1 to be wrapped in those thunks that I showed you. Okay? So it will be convertible to something that takes a unit arrow tau1, one of those thunks that are protecting the tau1 essentially, that's sitting inside, and then gives you a tau2, right? And this is assuming the tau1s are convertible to tau1s and tau2s are convertible to tau2s. Right? So that's really sort of the interesting bit that you have to sit down and think about. Otherwise, soundness of the FFI will not be a theorem you'll be able to prove unless you make these decisions correctly. I'm not really going to go into how we implement these. I have it on the slide, but you can take a look at the paper. It's just a lot of thunking in one direction and applying unit and so on. We implement it somehow. But the basic idea is which types are convertible to which ones. OK, now, I just want to give a little flavor of the model that we set up, just to give you a sense of what this ends up looking like, at least for a very simple case study. So this is, for those of you who haven't seen, sort of step index logical relations. There's been a lot of work, again, in the last couple of decades on this kind of stuff, so some of you might be familiar. For those of you who aren't, I promise I can sort of give you the essence of this, even based on this one slide. Essentially, what we do to construct the model of the blue types and the orange types is we first say, let's figure out what are all the value forms in the target that inhabit the blue types and the orange types. And then as a step 2, we will figure out what are all the non-value terms in the target language that inhabits the blue types and the orange types. Okay? That's the basic structure. So let's talk about values. Basically, the shape of this is going to look like, for every blue type, I'm going to say, when is a value v? Notice that the value v over here is black, so it's target code. So I'm going to have some sort of a world which describes the shape of the heap. And given that shape of the heap at that point in time, what I want to know is, does the black value v, the target value v, behave like the blue type tau? Okay? And similarly on the other side. That's the essence of what we're trying to capture. Then you might say, what exactly is this world? The world, well, it has a step index in it. That's what the K is, for those of you who have seen step index logical relations. But other than that, that's kind of the boring part, and we don't have to get into it. But the interesting part is that the world is describing what are all of the references. So the heap typing, psi, is describing what are all of the references that came from ML, right? Because only ML can allocate proper references. What are all the references that are currently in the heap, and what are their types? And this A thing is also describing ref cells, but it is describing only the ones that we're using as flags. You know those flag ref cells that are protecting the affine resources? They're all in that set A. Okay? And the interesting part here is that then in the model we have to say, all we keep track of is, oh, there's a flag ref cell. Does it contain used or does it contain unused? So the state of the world, the current state of the world, has to tell me that. In these logical relations, we always then also say, if I'm currently in this world, what are all the future worlds that I can move to? And for this model, the one thing that you want to capture, well, you want to capture that if you have a reference cell in psi and it has type tau, then it will always in the future have type tau, because that's how ML references work. You cannot change the type of value stored inside them. So that's one condition. But the other condition that you want, which is interesting for the flag ref cells, is that once you have stored used in a flag ref cell, you cannot change it to unused, right? Because then everything would go wrong. So once it's been used, it will stay used forever. Okay? The math for it looks like this, but that basically says everything that I just said. If you have a flag reference L that's true, it's used, then it will be used in the future. So you can go from a current world to a future world under a set of constraints. But it basically is what I just said in words. Okay. So you can set up this model of types. For integers, they're inhabited by numbers. Integers in both languages are basically, the target level terms will be numbers. And I'm just going to sort of very quickly skip through some of this in the interest of time. I want to give you a little bit of a... Actually, how many people would like to see a little bit of the logical relation? Sophia's hand has gone up. All right, then I will keep going. I wasn't sure. OK, the goal here was, the reason I have this slide is I thought, I want to give a little micro tutorial if necessary, just to show people how this works. OK, so if I have a pair, then in that set, I have to say, what is the canonical shape of the target values that inhabit that blue pair type, tau1 across tau2? And basically what I say is, in the current world W, v1, v2 is a pair that is a legitimate tau1 arrow cross tau2, tau1 cross tau2, if v1 is it belongs to tau1 and v2 belongs to tau2, right? So it's exactly what you would expect. If the components are values of the types tau1 and tau2, then the pair is a value of the pair. Functions are more interesting, and this is, I'm just covering basics, but tau1 arrow tau2, the blue type, is inhabited by these untyped lambdas in our target. And the way that we always define this is very standard, but I just want to read through it, is we say that in the current world W, this lambda behaves like this type. If in some future world you give me an argument of the type tau1, then in that future world, once I substitute the argument into the body of the function, it will behave like a tau2. And the E just means here, now this is a running term, it's not a value form, I can run it. And it will still give me an answer of type tau2. Okay? Now, that was the standard slide. But we need to do something a little bit more interesting when it comes to these lolly types. Okay? So when does one of these lambdas behave like tau1 lolly tau2? Well, it behaves like that in the current world if in the future world you give me an argument of the right type tau1. And then what I have to do is I have to allocate a new flag ref cell. That's going to be this fresh location L. I have to put false. I should have said used. Sorry, unused. False is unused. I have to put unused in it. And then I have to go and substitute V wrapped with that. So I'm going to use thunk VL to essentially wrap my argument with this in a thunk where we have a ref cell guarding it. And we substitute not just the V, but the thunked V into the body of the code. And when we run, we have to get a tau2. So we have to do a little bit of extra, right? We can't just substitute the argument. Our compiler isn't doing that. So our model isn't doing that. Okay? All right. And then just to sort of read this in the interest of completeness, we say that target terms, these are non-value forms, runnable terms, behave like either a blue or an orange type tau in the world W. If you give me a heap that satisfies the shape that W needs, right? Because W is saying how many heap cells do I have and what flag references do I have. So give me a heap that has all of those things that the world needs. If I go run my program, then either I will fail with a conversion error. Note, I will never fail with a type error. Okay, the model does not allow it. Or I will reach some future world in which this heap, satisfies the future world, and the final term that I got by running this satisfies is a value of the right type. Sorry, there's a lot of math. If you've seen it before, you're probably like, yeah, this is standard. And if you haven't, you're probably squinting a little. So happy to chat about it afterwards. But just wanted to give you a flavor and highlight the fact that the model does not allow failure with type errors, right? Because that would be a failure of type safety. OK, then you sort of pull the standard trick, and logical relations have something called a fundamental lemma that you prove, and that essentially amounts to proving type soundness of the whole system. Oh, yes. And when we substitute for affine variables, we have to do the definitions in a way so that we substitute thunked, affine values wrapped in a thunk with a fresh flag, just like we've been doing all along. OK, so with all of that in place, we've essentially gone through all of the steps of the recipe that I showed you before, right? We defined convertibility, we implemented the conversions, we defined the semantic model with the semantic IR, and then we can use that to prove all of the conversion lemmas. All of the glue code that we defined, we can prove that that is sound, that is soundly converting from an appropriate blue type to orange type, or vice versa. OK, so now I claim that using this sort of recipe, you can prove the soundness of FFI implementations. At least the basic structure exists. So, I wanted to say this thing. I don't know if some of you may have noticed that basically in the very simple model that I just showed, the sound interrupt that I'm doing has a serious runtime cost. Every single affine binding is wrapped in a thunk. So even if an affine value never flows off into the ML language, right? I'm still dynamically checking it, which is really unnecessary. Those are totally redundant checks. For any affine value that never flows over into the unrestricted language, right? You statically know that it's never going to be used more than once. But what the naive compiler that I showed you isn't doing that. But that's we show how to do that in the paper, and if you're interested, you can take a look. The basic idea is you need an analysis to figure out which are the affine values that flow into ML and which are the ones that don't. For the ones that don't, you statically know that they're fine. You don't have to thunk them or wrap them with these reference flags. Okay? I'll skip over that. That's all that was saying. Okay. So for the remainder of my time, I'd like to talk about future work, right? Where are we going with this? So this was a recipe for FFIs. And I've told you a little bit about what the paper that we had on this, the 3 case studies that is doing. Really, I think that the most interesting work is ahead of us. So right now, there are 2 things that my students are working on. We're interested in figuring out interoperability using this framework. We'd like to apply it to realistic languages. My student Andrew Wagner is working on a model from of Rust types inhabited by WebAssembly terms that we'd like to then use to study what sort of safe interop can we design between ML or CAML and Rust. My student Nate Yazani is working on interop between a Haskell-like language. Essentially, it's like the core of Haskell, and C++, compiled down to LLVM. And we're basically trying to study this interop using the framework that I've just described. Of course, these are very substantial languages and efforts, so this is going to be some time. I want to talk about other future things and things that we need to think about now that we have this framework, because even if you have the framework, the work of FFI design is certainly not done, and there are a lot of decisions that we need to make when we implement FFIs between 2 languages. So I'd like to sort of walk you through some of these issues. The first I've sort of called, we need to be thoughtful about the meaning of types. So the next few slides will walk you through what I mean by that. I thought I'd do this with 2 languages, just to sort of show what I mean. Imagine that we have a pure language. It's not pure in the sense of terminating. It has recursive functions, but it does not have state. You cannot allocate memory, okay, or have read-write effects. And then there's a stateful language with ML-style references, etc. Okay, so I want pure and stateful to interact. And let's think about what what the types should be. Oh, first let's think about what target we're going to compile it to. So I'm going to make up a contrived target just to make my point. Okay, the contrived target here is basically an untyped lambda calculus. It has fix, so we can do recursion. But I've basically this language has a dynamic region-based kind of memory and a memtrap instruction. The memtrap instruction, so region-based memory, basically what we want to do is all locations will be allocated in some region. There will be some most recent region. And basically what memtrap does is it reports an error if the program accesses locations that are not in the most recent region. Okay? I'm making up a contrived target, but I have a point I'd like to make in a minute. All right, but just imagine this model of you're allocating things. Perhaps at some point we will figure out how you decide, oh, I need to move to a new region and allocate stuff in it. Now, if while you're in that region, you can only access locations in that region, you cannot access locations in an earlier region. Okay, and I'm going to use this in a particular way soon. All right. Now I want to go back to these kind of models and say, what did we actually do when we wrote them down? Okay? So here is a model of P plus S, pure plus stateful languages. All right? And I want you to focus on this part. What is it saying if I define it this way? It says, oh, if you run the program E behaves like a blue type tau. Remember, blue types are pure. They're from the pure language. They're not supposed to have stateful effects. But this says that if you run E behaves like this pure type tau. In the world W, if you run in a state or a heap that satisfies the current world, and then you get to some future state or heap that satisfies, blah, blah, blah. But notice that this W prime can now have more locations. So while I ran this supposedly, this term that's supposedly supposed to inhabit a pure type, this is saying, oh, it's perfectly okay to have stateful effects. Right? It's saying, oh, yeah, you can allocate, you can do whatever. Is that what we want? blue is a pure type, right? Or a type of the pure language. And this is really a decision you need to make. Like, when you do interop, are you allowing the stateful language to kind of just bring stateful effects willy-nilly into your pure language? Do you want that? Do you want to define the model this way? Or do you want to do something different? Here's a different way of specifying that. This says that I'm going to run, because at the target level we do have references. So I'm going to run my term, and I maybe end up with the store S prime or state S prime. But ultimately, the value that I got needs to behave like tau in essentially the original world. I am not allowing W to change to some future W prime. I'm not allowing it to have more references. I'm saying state needs to be the same. Okay? So here, pure types are not stateful. And then, let me show you a third model. This is the sort of completely naive, utterly obvious model of a pure stateful language. This one has no world. It's, I'm a pure language. Why do I need a world? Why do I need references, right? I just don't need them. So this is a model of the pure lambda calculus, essentially, or simply type lambda calculus. So I'm saying that a lambda behaves like this. If you give me an argument, I stick it in, and I can run it. And here we're saying, yeah, OK, the target might have some state and heap, and maybe something happens, but ultimately, we are still in the pure model, right? We will get a value that belongs to the pure type. So this is really a pure model, right? So you, as a language designer, need to figure out, if you're setting up these models, which one of these are you trying to enable via interop? Do you want really loose interop in the first category, or do you want really tight interop that essentially corresponds to the second and third category? Now, why did I show you? OK, yeah. So here, pure and stateful, right? So what do we want? I just basically said that. So if we really do want stateful code to not affect pure code, then you need some way for this boundary, right, that's sitting between the orange and the blue code. You need some way to actually enforce, your compiler needs to enforce, safe encapsulation of foreign behavior. So your compiler needs to insert something to enforce safe encapsulation, right, if you want stateful code to not affect pure code. The reason I showed you this region-based language with the mem traps is we can do that by writing, in a very simple way. Basically, I'm saying, oh, the second I have to insert the glue code for these boundaries, what I'm going to do is I'm going to allocate a new region, and then I'm going to run the term E only in that new region. So that means that whatever stateful effects it has in only the very last region. It cannot touch prior ones. And the second I'm done, I'm past the boundary, I cannot, access code in a region that's gone, essentially. That's not the most recent. So I will memtrap. So essentially, a dynamic way of capturing errors anytime encapsulation is violated. Of course, this is a contrived example of how you would implement this in the target, but it's just to give you an example of the kinds of decisions you have to make if you really want, safe encapsulation of behavior. Yeah, so once you have this, if you implement your glue code for that boundary using this idea, then you can prove that, any term in the P plus S model, right? So you can prove convergence happens, but you can also prove that if you have something, wait, what was I trying to say here? Yes, so this is the middle model that I showed you, right? So if E belongs to the pure plus stateful model in world W, then I can just throw away that world and it still belongs to the pure model. So that we actually do have captured the obvious notion of purity. Okay, let's talk about another thing. Suppose that I have code in the pure language, and inside it, I want to use some library code. Maybe what the library code is doing, so there's bits of this orange stuff in there, which is library code. And they're imported functions, let's say, like alloc, read, and write. Okay? Now, I've purposefully put some uses of orange in there, and then there's some blue surrounding them, and then the boundaries on the outside, right? The problem is that if I'm using alloc, read, and write in here, then in these blue parts over here, I need some way of talking about references, right? But that's sort of unfortunate, because then that means that I can't just use alloc, read, and write. All of the code over here, anything that takes the result of an alloc and does something with it, all of the code in here needs to be written in the orange language, but I don't want to go write code in the Orange language. I just want to use some library functions from the Orange language. So what do you need to do in order to enable, use of libraries in this kind of fashion without resorting to, switching to the library language in order to write the code in that boundary? Yeah, we shouldn't have to write the surrounding code in the stateful Orange language. So here, we've been proposing an idea called linking types, that essentially you need to augment the types of pure so that you can allow a programmer the flexibility to essentially work in a slightly richer type system for part of the language, but you still want to take advantage of encapsulation at the boundaries. So you want to allow the programmer to choose where to place those encapsulation boundaries that I have in that picture. And then in the middle, they can sort of work with richer types than the blue language has within this region, but once they go outside the boundary, they have to switch purely back to blue types again. So what does that mean? Augment your types with these pink linking types, which actually do have references in them, so that I can take the result of my alloc, let's say, and maybe do a read or write on it later, right? But it's all within this region where I'm working in the blue language, but with richer objects, richer types. But once I get to the programmer inserted boundary over here, I have to switch entirely to blue. Okay? I mean, I'm very abstractly describing things that do very much arise when are things you would have to think about when programmers are writing code. How do we make this easier for them, and how do we still make it make sense? Okay, and if you want to read about this stuff, we had a paper at Tidy this year just describing this idea of semantic encapsulation using linking types. Okay, so just a couple of finishing thoughts. Now that we have these semantic IRs, what are other things we could do with them? And I've done a lot of work on so-called secure compilation that I want to talk about briefly. So let's stare at this picture. Basically, what's happening here? This semantic IR is cutting down the space of the target, right? It's saying, oh, you only need to think about the things that are in this orange circle. But basically, what we're doing by constructing this model is we're saying, we assume we will only link with things inside the dotted orange circle. We will never link with things that are outside the dotted orange circle, right? What if you want to link with things that are outside the dotted orange circle? What do you need to do? Can you use this model in some way to think about that issue? What about linking with things that are not in that, or context or target code that's not in that circle? And this is where secure compilation kind of comes into the picture. Secure compilation is always about, oh, I need to be able to somehow link with arbitrary target contexts. How am I going to protect myself from them? So in this case, the issue is you need to protect yourself when linking with a context that's outside the dotted orange circle, but still within your target, let's say somewhere over here. Your compiler might need to do something to protect the stuff in the dotted orange circle from the stuff outside, so to speak. Right? You might need to insert wrappers or checks statically or dynamically. Basically here the idea is that you want to show that you want to switch to models which actually talk about equivalence. So secure compilation would say that if you have two compiled programs that are equivalent in the orange circle, then the protection wrappers that your compiler inserts to protect code in here from code out here, you would need to show that once you've inserted those protection wrappers, the equivalence is still preserved. For those of you who worked on secure compilation as an equivalence preserving problem, that should ring a bell. Okay, so that's the connection to secure compilation. Let me switch gears to end. I've been talking a lot about building these semantic IRs. Right? But building semantic IRs is hard. And you might have been sitting there feeling rather skeptical, like the people who go and implement FFIs, maybe they're not the type of people who actually want to dive into a whole cock verification project or something and go and actually verify their FFI. Maybe they're just trying to do sort of best effort and get safe interop, which they're doing right now, but right now I would claim that they have very few ways of thinking about it. So is there some middle ground that we could use? And plus, FFI implementers might not be sort of so well versed in these semantic models and logical relations and so on. So here's another idea that my group has been advocating a lot. We we can support safe interop, or we can give FFI designers a better substrate to compile to so that they can more easily think about safe interop or more easily catch unsafe interoperability. So the basic idea is design much more richly typed IRs or target languages. Okay? The kind that have the ability to reason about, mixing of code from a GC language, a code from Rust with ownership and borrowing, and code from ML without any ownership and borrowing, right? So you want a target language that or IR that has the ability to think about these concepts and keep them separate and enforce the rules. And then a compiler writer can take advantage of that by writing a type-preserving compiler from their language into your richly typed IR. And they don't have to think too much about, they just have to think about what types am I compiling to in the target. And then you can do type checking at the target level to catch any problems with interop. Okay, so let me step ahead to a picture. So we've actually had a project underway for quite some time. It's called Rich WASM, Rich WebAssembly, where we're designing a very richly typed WebAssembly that sits on top of regular WebAssembly. And essentially, well, let me first say what Rich WASM has. Rich WASM has capability types. It has unique capability types. For those of you who know L3, they're very much in the style of L3 unique ownership capability types. But it also has shared capability types. Essentially, those are the ones that we would use to represent references compiled from ML, the GC'd references. Okay? But what this does is it gives you fine-grained, it allows modules, one that might be compiled from ML and one that might be compiled from Rust, to share memory with each other in a very fine-grained way. I have to give you a capability for this little tiny chunk of my memory, and you cannot read, you can't just do pointer arithmetic and read past that. The type system enforces that. So we can do safe sharing, fine-grained sharing of manually managed and garbage collected memory using the Rich WASM type system. We can reason about that. And then the idea is that if compiler writers who are compiling typed languages could write type-preserving compilers to Rich WASM, then maybe they don't have to think so hard about their interoperator errors at the source level, because after they compile, they're compiling to a typed language, and if there's a mismatch, if ML is trying to stash, some data structure from Rust that should be owned, if it's just trying to stash it somewhere and reuse it later, the Rich WASM type system will report that as a type error. So your type checking for unsafe interop moves to the target level rather than trying to do verification of an entire FFI. So I think of this as a lighter weight solution to giving people a way of implementing safe interop between languages. Okay, so that's that. And now some of you may be thinking, okay, she talks a lot about typed languages interoperating, but what happens, so this Rich WASM substrate is great if I want to study ML and Rust interoperability. Actually, we can't do full Rust yet. we can't do immutable borrows from Rust yet. My student, Sarah Marshall, is working on that. But we hope to be able to do Rust. We can do a subset of that. But yes, so Rich WASM can catch all sorts of interop errors between these type-safe languages if you do the work and set things up right and have type-preserving compilers. But ultimately, C has does not have enough type information. There's no way we can compile that to Rich WASM, which needs too much rich type information. So we're going to compile C to WebAssembly. So then how do we ultimately handle the interop between the typed languages on this side of the picture and the unsafe or untyped languages on that side of the picture? You still have a problem. We still have a problem that we've sort of punted on. And here, there are a couple of things that I'd like to propose that we're looking at, or hoping to look at. So ultimately, this becomes, C compiles to WASM, the ML and Rust are compiling to Rich WASM, so you need to study the problem of safe interop between Rich WASM and WASM. This sounds very much like a gradual typing problem, right? Which can be very expensive if done with dynamic checks and so on. But I would say that there's another decision you need to make about what kind of interop you want between C and the typed languages. Basically, if you decide that you don't, you're not going to, if you want to do shared memory interop between C and let's say, one of the typed languages, then you have no choice. This is a gradual typing problem. You will have to insert protection at the boundaries. It will be expensive. Maybe you can use some ideas from static contract verification in order to eliminate those checks in order to get better performance, the standard tricks that the gradual typing community sort of understands. But you could do something else. You could do shared nothing interop. Now, there's already underway the WebAssembly component model that actually my student Lucy is working on with Luke Wagner and Andreas Strasberg. Well, she's working on the spec for that. Primarily, Luke's been working on implementation stuff. The component model is a way of doing, essentially it has these interface types that allow you to do shared nothing interoperability between WebAssembly modules that often might have come from different languages. So you could use the component model's interface types to sit at the boundary between the code that comes from C and the code that comes from the typed languages into rich WASM. So that's another idea. That way you don't have to worry about performance problems. Because you're not sharing, you don't have to protect. OK, and that's about it. I want to leave you with these two pictures as the takeaways. Right? These are the two main ideas I've tried to kind of go through. And again, these are frameworks, right, for how to think about interop in the wild. There is tons and tons and tons of work to be done to take these framework or methodology kinds of ideas and actually apply them to realistic languages. And some of this we're a little bit further along than for other things, but I think that there's a lot of exciting work to be done. So, questions. Thank you.
Okay, I don't need to ask for questions. Go ahead, but yeah, you have no mic. Here it is.
Thanks. Yeah, great talk. I have one thing where I seem to be missing something. So in your example where you compile down to the stateful language is encapsulated and you have this memory region way of protecting things. So how would this work if in the case where actually the stateful stuff like the FFI wants to return something, it has to allocate in memory to the pure thing, to the pure side, right?
See, that's the thing. That's what I was trying to get at with that picture where I was saying let's use. This is exactly the picture I think that you sort of are talking about. So the stateful language, the orange code, right, wants to, let's say the first orange bubble over there is a call to alloc. And it tries to return a reference, right? Now, if I was just returning a reference from the orange language to the blue language doesn't have any references. Is that basically what you were asking about?
Well, the blue language might be implemented with reference underneath, right? So the FFI might have to allocate something for the blue language so that it has to outlive this boundary.
Yes. But see, in my first picture over here, I had this assumption that whenever I have this blue boundary, that it's just automatically there anytime I transition from orange code to blue code. It's just automatically there always. And the point that I was trying to make with this picture is I don't want that boundary to be automatically placed because I want to use the references that are coming from these calls to the orange libraries. I want to use them for a little while, right? So I want to take a pointer from the first bubble and pass it to the second bubble, but how do I get it through the blue thing that's sitting in the middle? Because that doesn't have references, right? How do you implement that? Am I sort of answering your question?
Yeah, I'm still a bit confused because you implement the blue language with references underneath as well,
yes.
right?
And in this,
say there's a string type, you allocate that on the heap with the reference. You never mutate it, but maybe the FFI wants to allocate a string, initialize it, and then pass that string to the blue side, and it's going to live there forever, right? It's not bounded in any way.
I guess what I'm saying is you don't want to take a reference and pass it to the blue language and have it live forever, right? If you want to maintain blue language's purity, you don't want to do that. But with this picture, I do want to do that within the pink boundary. So if programmers get to place the pink boundary, now you can actually do exactly what you're saying. You can take advantage of the fact that at the target level, you have references, and in this pink region, I have those references.
That's what I get, but what would I do then instead of passing it? What would I do for my string example? Would you have to copy it at the boundary?
You would have to copy.
Okay.
Exactly. Otherwise, you don't get purity.
Okay.
Yeah.
Thanks.
And again, this is a contrived example of pure and stateful, right? Which is sort of the ultimate one we go to when we want to show something really draconian. But I think situations like that arise.
Is there any way of like loosening that you would not have to do this copy at the boundary? Or is that not something you have looked into?
It's not something. There may be clever ways of doing it, but I don't know off the top of my head.
Fair.
From the point of view of language design of the target language, in your experience, can you elaborate on what are the features that a good target language should have to facilitate, or in some sense to be ideal, to allow composition of language without losing their properties? So, in my opinion, it would have to be a typed target language, right? Ultimately, so compiler has many IRs in it, right? And I often like to put it this way, that it would be nice if your IRs could all be typed until the point in the compiler where the last of the linking happens. Because types are only essential to make sense of whether linking is safe or unsafe. After you have a whole program, you can erase the types. Now, you said, what are the properties of the target, right? So, I assume you're not asking about untyped targets, right? I'm leaving it to your interpretation.
If you want to compile to untyped targets and reason about safety, then you should be using, I think, the way you need to think about that is using the first picture here, right? The thing on the left. Because that framework completely handles untyped target languages. But the way you handle it is by building a semantic model of source types in terms of untyped target terms. You can do assembly then. You can do x86. It'll be a bit hairy to build that model, but people have done it, right? Like for idealized things. But the advantage of the right-hand side is more, I think, in line with what you're asking, right? What are the features of a good IR or of a good target? And here I would say that rich WASM is something where we've tried to do that. It should be something that has a type system where the types that you have can be used as building blocks to encode a lot of different kinds of features that come from source languages. These days, one of the biggest things that we all struggle with is, the ownership and borrowing discipline of Rust. How do you encode that at the target level? Rich WASM does not have ownership and borrowing. It has capability types, but it has unique capability types and shared capability types. And we might need another form of shared but fractional capability types in order to handle immutable borrows. But these are the kinds of building blocks, they're capability types, not like Rust-like thing, that you can use to encode different disciplines from the source languages. That's the intuition.
Hi,
yes.
Thanks for the talk. That was very interesting. I was wondering, so you mentioned that in sort of rich WASM and richly typed IRs, you can sort of catch interop errors by type checking.
Yes.
So is there, I had a question of whether the processes of backporting errors in rich WASM to sort of the source language is easy, or are there challenges in there? And what's the process? Thanks.
Yeah. So most of the work on rich WASM has focused on, we have this massive cock-proof proving. Type soundness is a very fancy type system. So we built 2 prototype compilers, one from like a mini ML and one from L3, which is like a core of Rust. And the rest, I think, is future work. Backporting errors, figuring out how to report them. My student Daniel Patterson and I had a paper a few years ago at Snapple, I think it was Snapple 2017, on linking types. And we talked a little bit about cross-language type errors and how we think they ought to be reported back, but that's not something we've actively worked on. But I have some vague ideas if you want to chat later.
I see. Thanks.
Yeah. Or read that paper.
Thanks for the talk. So when dealing with FFI code, I find callbacks to be some of the most annoying things to get right. Do you have case studies with callbacks?
Not case study as such, right? My group has focused very, very much on like frameworks for how do you actually verify this stuff. But right now, at least at the level of what we're doing between ML and L3 at the rich WASM level, that is not a problem because the type system at the target level is rich enough that it works out. Sorry, not a very detailed answer, but yeah.
Thanks for your very inspiring talk. So could we reuse your approach to build an interrupt between the coq proof assistant, for example, and imperative ML through coq extraction?
Ooh, through coq extraction. What's the target? Imperative ML?
Sorry?
The source, one source is coq. The other one is imperative ML, right? And the target is also imperative ML.
Yes, exactly. And you want to extract, so you want to program in coq with...
The extraction is the compiler.
Sorry?
The extraction in that case is the compiler, right? So yes, I'm going to just sort of say that at least after thinking about it for 1 minute, yes, the framework should be applicable, but it will be very hard.
Okay, thanks.
Sure. Thank you. Thank you, everyone. Oh, thanks.
So welcome to the session on verification. My name is Gautam Kaki, I'm session chair. The first talk is from Chenglin Wang on solving conditional linear recurrences for program verification, the periodic case. Chang.
Morning, everyone. It's my great honor to be here to introduce our work on recurrence solving and its applications on program verification. I'm Chen Ling, a PhD student from HKUST, supervised by Professor Fangzhen Lin, who is also the second author of this work. So before diving into the technical details, I would like to introduce some motivations for the recurrence analysis. So most of us are familiar with Area VM, so, which is a really powerful and popular compiler framework. So I tried to ask ChatGPT which components in it make use of recurrence analysis. And here is the answers. So you can see passes like loop virtualization make use of recurrence analysis. So actually, if we compile our work using any Area VM-based compiler, we are very likely to be benefit from it. And also note that all the listed passes focus on code efficiency, but in our work, we focus on its applications on program verification. So for verification, Professor Lim proposed a method for translating any C-like program into a set of first-order language, which can be fed into SMT solvers directly. This is the example, and the key point of the translation is that a loop is translated into a set of recurrences, but current SMT solvers doesn't dealing well with such a recursive definition. So what we need to do is to remove them by computing closed-form solutions for them. But current recurrence solvers are still limited in dealing with the conditional recurrences, like the one in the running example. So for example, Mathematica is one of the most powerful algebra systems in the world. It provides a function called rsolve, which is really powerful when the recurrence is non-conditional. But if they encounter the conditional ones, they will just give up. I tried to give it the recurrence in the running example, which is conditional. Then it just give up and return what I type in. But a closed-form solution does exist for this conditional recurrence. And here is the result produced by our tool. And then together with other actions in the previous slide, the SMT solvers can prove the correctness of that assertion. So here is a short summary for our contribution. So first, we propose a method for solving what we call periodic linear recurrence. And then we extend this result into two much more complex settings. And finally, we also implement prototype tools and apply it in some verification tasks. And the result shows that with this more capable recurrence solver, more programs can be verified. So here comes the definitions of conditional linear recurrences, so for which we want to compute a closed-form solution. So each conditional linear recurrence, it consists of some branches, and each branch are guarded by some condition. And if this condition is satisfied, there is a corresponding linear transition. So that's why we call such a recurrence conditional and linear. So for the running example, we will also represent it in this matrix form. But before we try to solve the most general conditional linear recurrence, let's first see how to solve a much simpler version and try to gain some insights from this process. So periodic recurrence, we just replace the conditional part with these modular operations. And this is then a concrete example. So for solving this example, let's first run it for several iterations. So the first table of this row, the first row of this table, it denotes the iterations of the loop of the recurrence. And the second row, it denotes in the corresponding iteration which condition is satisfied. And the last row, it just records the index of the second row. So from the table, we can see the index sequence in the last row is actually periodic because it contains 0, 1, 0, 1, 0, 1. So the effect of this recurrence can be summarized in every 2 iterations. So that is, if k is an even number, then the sk should be equal to this term. Otherwise, it should be equal to this last term. So what we need to do next is to compute this matrix power symbolically. So for that purpose, we resort to the Jordan normal form, which is actually an extension for matrix diagonalization. Many algebraic systems like SymPy, Mathematica, they all provide these functions. So for the running example, we need to solve this matrix power symbolically, and this is the result produced by Mathematica. And finally, we just need to replace this matrix power into the formula we derived in the previous slide. And then finally, we will achieve the closed form solution. And here is the formal result for computing closed form solutions to periodic recurrences. So the reason why a periodic recurrence is solvable is that the order of each satisfied condition is periodic. So the final transition, the effect of all the transition can be summarized by just multiplying those matrices in different branches in order. And then the closed form solutions can be obtained by computing matrix power symbolically. So this suggests that for any general conditional linear recurrence, if the corresponding order is periodic, then we can solve a closed form solution in a similar way. So here comes the most important concept in our paper. That is what we call index sequence. So intuitively, the index sequence is just record the order of the fire conditions when this recurrence is used to generate the whole sequence. So for the running example, the index sequence is actually this last row of this table. That is the whole index sequence. They are 1, 1, 1, 1, followed by infinite number of zeros. So recall that if the index sequence is periodic, then we can compute the closed form solution as what we did for the periodic recurrence. But unlike the periodic recurrence, whose index sequence is known. So we don't know what the index sequence of a general conditional linear recurrence looks like. So we decide to adopt a generate and test method. That is, we first try to run the loop or the recurrence for the first several iterations, and then recall the order of the fire conditions, which is actually some prefix of the whole index sequence. So, and then we guess the periodic segment from it. So for the running example, we will start from x0 and try to run it for the first 2 iterations. And because the index sequence is 1 and 1, so we just guess the periodic segment is 1. That is, we will assume the whole index sequence is 1, 1, 1, 1, 1, which means the second condition is satisfied. So the second matrix is always applied. So for the current iteration, we will compute the closed form solution to sk to be equal to k. But for now, this closed form solution is just a hypothesis because we have some assumption on the index sequence. And the assumption is that the index sequence is 1, 1, 1, 1, 1, so which means the second condition is satisfied. So the validation condition is set up by replacing the sk in the second condition with this hypothesis closed form, and then establish this validation condition, which is obviously it doesn't hold. And the smallest k that violates this validation condition is 50. So in the next iteration, we will restart this process from x50. But for now, we can still conclude that for all k less than 50, the closed form solution is k. And then for the next iteration, we still run it starting from x50 and see that the index sequence is 0, 0, 0. So for now, we assume the periodic segment is 0. That is, the whole index sequence are 0, 0, 0. So which means the first matrix should be applied forever. So we can now get another closed form solution. And again, we need to verify this result. So because the assumption is that the whole index sequence is 0, 0, 0, so the first condition should always satisfy. So we set up this validation condition, which obviously it does hold. So we can conclude that the whole closed form solution is something like this one. Previously, we just considered the case where the initial values are known so that we can generate some prefix for the index sequence. But if the initial values are all unknown, then we cannot even get such a prefix. So to handle that case, we also propose a method, but due to the time limit, we can only show some examples to show the capability of our tool. So for this part, for more technical details, you may refer to the original paper. Our experiment has two parts. The first part where all the benchmark program has known initial values, and the second part, all the initial values are unknown. To compare, we compare with 3 other tools. The first two, ICRA and VIAP, they also perform recurrence analysis, but with some different approaches. In the last row, the very apps, it ranks first in the rich safety check in SVCon. And in this table, in each cell, the number on the left, it denotes the number of safe program. And the number on the right, it denotes the number of unsafe ones. And the program on the right is some example in this benchmark. So this table concludes the results where all the benchmark program contains unknown initial values. And the notation is similar to the previous table. And the program on the right is an example in the benchmark. So that's all for my talk. Thank you.
Anyone? Okay, I'll start. So it does seem like there is a close connection between closed form computation and inductive invariant inference. Is there one? So is there any connection with the closed form inference and inductive invariant inference?
What difference?
Inductive invariant inference.
Inductive.
So you're computing the closed form solution for loops, right?
Yes.
So how does that relate to the inductive invariance for the same loop?
Sorry, I don't quite understand the last sentence.
Okay. Maybe we'll move on to something else. Any other questions? Did you try integrating this solution into the Mathematica? Because that's how you started your talk, right?
So for you mean I need compare with the Mathematica, right?
The Mathematica. So your initial, you tried the same solutions in Mathematica, and you wasn't able to work. So were you able to integrate your solution into?
Yeah. For example, for this non-conditional one, my tool can return the same result as the Mathematica. But if the condition, if the recurrence is conditional, then the Mathematica just give up.
Okay. Any more questions? All right, let's thank the speaker again. Okay, our next speaker is Armel. He's going to talk about Melocoton, program logic for verified interoperability between OCaml and C. That.
Yes, can you hear me? I guess you can. Right. Hello, everyone. I'm Johannes. I'm actually not Armael. Armael is in the audience, however. And I'm presenting Melocoton today, which is a joint work with all of these awesome people. Right, and it's our approach for multi-language program verification. And we care about multi-language program verification because multi-language programs are everywhere. Here are just some examples. For example, you have NumPy, which is a library for fast number crunching in Python, and it's also written in Python, C, and in Fortran. Or as another example, Firefox is written in C++, Rust, and JavaScript at the same time. Or alternatively, OpenSSL is a cryptography library. It's just written in C, but it often gets embedded into many projects that are all written in different languages. Right. And our goal today is to verify the functional correctness of such multi-language programs. And in order to verify functional correctness, when you look at the literature on single-language functional correctness, you find that there is lots of work that does functional correctness verification. Here are just some of the papers that were published at the top conferences in our field in the last few years. And when you read them all, you basically get the idea that there is some kind of recipe that you can follow for single-language functional correctness reasoning, which is that you try to use for logic when you have a simple imperative language, but when you need some more advanced features, like you want to be more modular or you have to handle aliasing, you might use separation logic instead. So that's the picture for single-language correctness reasoning. But for multi-language reasoning, the picture is a bit more sparse. There is not that much background literature. There is, of course, the work by Amal. She gave the keynote this morning. You might have seen it, on semantics and on logical relations. And there's also some work in the ComSet context. But today, we want to reason about proving the functional correctness of individual programs, where in these individual programs, you might combine languages that are not actually typed, that might have unsafe features that you cannot account for with a type system. So you need to do individual reasoning to prove that such programs are correct on their own. Right, the literature is a bit more sparse. The question is more open. How do we actually go about reasoning about these programs? And to start, we should first look at an actual multi-language program in the real world to look at what it looks like so that we can figure out how to reason about it. Right, and we're going to combine OCaml and C today. These are the two languages we focus on in this talk. And your example multi-language program in OCaml and C might look like this, that you have some C function. Let's say it's hash pointer. The idea is that you pass it an integer and then you hash it. And let's say that this is implemented in OpenSSL and it's a very long and complicated method. And we really don't want to port this to OCaml. We would much rather just use the existing C function in our OCaml program. Right. Here's our OCaml program. It's just called hashref. And the idea is that hashref is supposed to now do the same thing that the C function does, but of course with an OCaml reference instead of a C pointer. And in order to make this all work, we need to write glue code. The glue code has to link up these two functions. Right, so we need to write some glue code in C, and the C glue code looks like this. It's called the function camel hashref that takes OCaml values, and it does a bunch of stuff, and then in the end it has converted your OCaml values into C values and can pass this to the hash pointer function. And similarly, in OCaml, we also need a bit of glue code, but it's less glue code. Our glue code in C has the job of telling the compiler which C function to actually call when we call this hashref function in OCaml, and it also gives us the type, but it doesn't really matter. So this is our example multi-language program. But it turns out that when you, the key idea here is that you have your business logic and that you have your glue code, right? Every multi-language program has business logic and it has glue code. But oftentimes, when you look at more advanced multi-language programs, you find that there's quite a lot of business logic, but actually very little glue code. And the idea is that when you write your business logic, for example, you write your OpenSSL C library, you really don't want to care about all the other languages that might get linked with the C library. And all you want to focus on when you're writing OpenSSL is just writing a correct C library. And similarly, when you're writing your OCaml program, you really don't want to care about the fact that OpenSSL is actually written in C. You just want to care about the fact that it encrypts stuff. And it's the job of the glue code to make sure that this reasoning actually works, right? The glue code has to make sure that we can link those languages together in a way that we can then later forget about the fact that we're actually mixing two different languages, and we can mostly reason as if we were in a single language. This principle of mostly reasoning as if we were in a single language, we call this language locality, and we think it's quite important that our framework supports this language local reasoning. Okay, so getting to our framework, to actually build now our tool for reasoning about everything here, or our logic, we follow the very common approach that you first build an operational semantics that tells you how your language should compute, and then you build a program logic on top of this, in our case specifically a separation logic. And of course, we're mixing two different languages. We need to account for all of the stuff that goes on in our glue code. But we also want this language local reasoning. The way we get language local reasoning specifically here is that we assume that there are already existing semantics for OCaml and C, or in our case for idealized versions of OCaml and C. And we just take these existing semantics and the existing program logics and we embed them into our combined semantics and program logic. So that if at any point in our program we're in a part of the program that is just written in a single language, we can just drop down to this level of the single language program logic and then reason the way you would normally verify a program, ignoring all of the multi-language part. Right. That's the idea, that we can combine language locality and language interaction in this way. But there is actually quite a bit of tension between language locality and language interaction, right? This is just a high-level overview. There's a lot of details you have to resolve. We're going to now focus on one of those details. Specifically, we're going to focus on what happens when OCaml data is accessed from C, or more broadly, the question of how we can actually transfer data between our individual C part and our individual OCaml part using the glue code. How does the data transfer from one part to the other? And to answer this question, how OCaml data is accessed from C glue code, what do these weird methods like field and so on actually do? It's that when you're accessing your OCaml data from C glue code, you're accessing it at a lower representation. So you have your high-level OCaml values, your pairs and stuff, and when you're accessing them from C, you're only seeing a representation that's based around blocks somewhere in the heap that stop pointers to other blocks or store integers. So it's a lower-level representation. Since this is a PL talk, we have to invent some fancy notation for this. We have this tilde ML, which we use to relate the high-level and the low-level values. And as I said, if you have simple OCaml values like integers or booleans, you just encode them as integers in your blocks. So for example, true gets encoded as 1. And for more complicated values, like pointers to an array, you encode them as pointers to now blocks, and then your block will store the contents of your array. Or similarly, every OCaml value that you have has one corresponding block level representation. Right. And now we need to deal with this block level representation in our semantics and in our program logic. So first we start with the semantics. In our semantics, you might remember we earlier said we embed the existing OCaml semantics. And this means that we have a heap that stores OCaml values the same way you would do if you just model OCaml. But in our glue code, it is much more convenient to instead phrase the operational semantics as if we operated on a block level heap that stores these block level representations. Right, so we have these two heaps, but they actually store the same data, so we somehow need to keep them in sync. And the basic idea, what you can do here is that whenever you cross the language barrier from OCaml into C, you also take your OCaml state and turn it into C state, or the other way around. The key idea is that when you're in OCaml, all you have is the OCaml state, and this block level heap does not exist. Then when you switch the language barrier, you are now in C, you have your block level heap, and your OCaml heap has now gone away. And then whenever you switch back, you convert the heap from one to the other, but you only have one of those heaps being the active heap, and the other just is not there. Okay, and in the semantics, this works, right? You can build a semantics that work like this, but in the program logic, it is a lot more difficult to figure out something that is nice to use. And to see why, we're first going to try a naive approach of building a program logic and then see why this fails. So specifically, our program logic is based on separation logic. And in separation logic, you have your points tools, right? For those of you who know separation logic, you know them. And the idea, for those who don't know, is that you want to reason about your memory locally, about just each individual location at once, instead of considering all the locations at the same time. So instead of having one heap, you have a lot of these points tools, each one for each location, which describe the content of the memory cells and also carry ownership. Right, so in your proof, when you design the program logic, you actually have to keep track of like all the points tools, but in your proof, you're only ever using some of them. So you now have the points tools here, and these points tools describe the contents of the heap in our operational semantics. But I just told you earlier that we actually don't have both of those heaps. We only have one of them, and we switch back and forth between which heap actually exists. Sorry, what happened there? . no longer connected. I have plugged it in. So how is everyone enjoying the conference? In order to prove that your call into C is correct from OCaml, you get to convert all of the points tooth into block level points tooth. In the end, you get to convert them all back. For those who know separation logic, you might see that this is a very bad approach because it's very non-local, it's not small footprint. For those who don't know separation logic, the idea in separation logic is that we reason about our program in a local way. So when we prove that our program is correctly operating on some sort of heap, the idea is that everything else that the program does not use is not affected. And this is formalized by this frame rule, which just tells you that this part R of the heap that is not affected stays the same. And at the end of the program, it's just still R, and it hasn't changed. Which switching doesn't allow it because it forces you to convert all of your points tooth. But you actually don't care about all the points tooth. Most of them you will just not use. And this is what makes this rule bad in separation logic, and we want to have a better approach, right? It breaks when you switch the language. And the better approach is that we somehow try to make our OCaml points tooth remain valid, even if like the OCaml heap has gone away. So the idea is that you're in C, but you still have all this cloud of OCaml points tooth flying around. And now in your glue code, let's say you really only care about this one location, L1 here. So you want to have a rule that allows you to convert this one location into its glue code form so that you can reason about what's going on in glue code when it accesses this one location. or if you have 2 locations, you just convert 2 locations, right? You can convert each individually. And then in the end, you convert it all back, and then you're now back at a description of an OCaml heap using OCaml resources, and this means that you have proven a specification for your C program that just uses OCaml, so it basically behaves like an OCaml program. And to formalize this intuition of switching back and forth individually, we have some update rules for those who can parse separation logic. These rules here basically mean that you can take an OCaml point to, you can convert it to a block level point to, and the values have to match up, and then you can convert back. But these just formalize this intuition of being able to switch each point to one at a time individually. Okay, so how do we make these rules work? I try to speed it up a bit. We make these rules work. The problem is that our OCaml heap goes away, but our points to should remain there. So the idea is that you introduce a ghost heap, which just lives in your program logic, and it doesn't actually exist, but you just keep track of it in the logic to make sure that these OCaml points to still mean something. But this OCaml ghost heap cannot be any ghost heap. It specifically has to be like the high-level encoding of what is currently going on in your glue code, so that you're able to reason about the low-level effects that your glue code has at a higher level. Then to implement these rules, this connection here between the heaps is actually very complicated because it also allows you to do like points to trading and transfer ownership between those 2 block levels and implement these rules and so on. Right. So this is like one of the problems that we had to square in Melocoton, which is how we can connect language locality and language interaction in just this particular instance when you have to transfer the data. There are some other problems that show up like reasoning locally about external calls. And also we consider much more features of the OCaml FFI than I've just shown you. There's also garbage collection going on. We glossed over this totally. We handle like callbacks, which is when you pass higher order functions around. And then we have some case studies for all those features. And a very nice thing that we think we have is that we think is nice, is that we have a logical relation for your OCaml types that does prove that your OCaml language is type safe, but it also tells you what your C functions need to fulfill for properties if you want to claim that your C function is safe at an OCaml type. Right. Everything we've done is mechanized in Coq on top of Iris. For technical reasons, we use transfinite Iris. And that's basically it. We have Melocoton, where we try to combine language locality and language interaction. For more information, you can follow this link. Thank you.
Yeah, we have time for a couple of questions.
Thanks for a great talk. How close would you say does this get us to taking some C verifier, let's say from a C, and combining that with like an existing OCaml verifier? Are those kind of tools out there today like compatible enough with sort of the way that the logic is set up?
I don't know what these tools do. I guess I have to leave. I don't know what these tools do, unfortunately, but like, the whole idea behind our work is that you verify that these switching rules are correct, and then you can hopefully implement them in your like automatic verifier without having to think about them too deeply. But it would depend on the verifier. I'm not too familiar with automation. But we can talk about it later if you are more interested.
Hi. 2 questions. Oh, the mic's up there. Okay. First of all, how low level is the C language you're working with? Like you do pointer arithmetic and things like that? That's all included?
Yeah, it has like, the idea is that in C you have pointer and manual memory management, and in OCaml you have garbage collection and null freeing.
Okay.
But, yeah.
And then the second one was, what do you use the transfinite iris for?
Yeah, great question. You actually need at places angelic non-determinism. And when you have angelic non-determinism and the angelicism is too large, you want to have transfinite iris to get a proper adequacy theorem. But we can talk, like it's a bit more intricate for just like 20 seconds. So.
Okay, let's thank the speaker again. Our next talk is on outcome logic, a unifying foundation.
Thank you. Yes, I'm Noam Zilberstein from Cornell, and I'm very presenting this work with my collaborators. So I want to start with a. Oh, sorry. More technical difficulty. But it's better. And I end up in a state satisfying the post condition. And given that we just have this one assertion, the best thing we can do is to kind of use a disjunction to say, well, either this program will terminate in a state, or it will terminate successfully in a state with x pointing to 1, or it will crash because X is null. And the question is, well, does this actually characterize the bug? And the answer is no, because this disjunction isn't really expressive enough to tell us that the error can actually happen, right? It's possible that all of the program traces are going to fall into the first disjunct, and the error is not actually realized by a real execution. So to see this kind of more pictorially, let's look at the semantics of a non-deterministic program, right? You start in some state, here we call it sigma, and then you may end in one of many states, which here we call tau. And what Hoare logic allows you to do is kind of draw circles around the valid start states and the end states, and you use those pre and post conditions to describe the behavior of the program. So more specifically, any start state in this blue circle will end up inside of the green circle when the program executes. So given that this is what we call correctness, you could ask, well, what is incorrectness? Incorrectness should be the logical negation of this, which means there is some valid start state that's going to end up outside of the post condition. And if the program is completely deterministic, then we can kind of just shrink the precondition until we're just characterizing this bad start state and prove that that ends up inside of some umbrella of bad end states. And then you've kind of proved that the program has a bug. The problem is that a lot of programs have effects, like non-determinism, such as the malloc program that we saw at the beginning. And when the program is non-deterministic, you may have some states ending up in some end states ending up, in good outcomes and some ending up in bad ones. And we need some way to isolate the bad outcome, which Hoare logic doesn't really give us a way of doing. So let's go back to the picture of what does a Hoare triple kind of look like pictorially. You can see this program has this branching behavior, right? So we start in one state, but we end up in one of many states. And what we do in outcome logic is we kind of say, well, why should you just get this one assertion to describe all of the end states? Why not give you an assertion to describe each of the outcomes? So that's kind of the idea behind outcome logic intuitively. But let's look at how we actually formalize this. So the semantics of outcome logic triples are kind of similar to Hoare logic. You have these triples with preconditions and postconditions, and at a high level, the precondition describes valid start configurations, and the postcondition describes what's going to happen when you run the program. But now, the pre and postconditions are satisfied by sets of states rather than individual states. And that's going to allow us to talk more about the branching behavior that the program exhibits. So in order to just talk about the branching, we need some sort of language, to talk about that. So we have these outcome assertions. And the outcome assertions have a lot of standard things like true, false, conjunctions, and disjunctions, but there are also a few new constructs as well. The first new construct is what we call the outcome conjunction, this O+ thing. And what this tells us is if we have some set of states satisfying phi and some set of states satisfying psi, then their union satisfies the outcome conjunction of those two assertions. So you can kind of split the set of outcomes into two parts and describe them individually. And then P, we use the Latin letters as kind of atomic assertions or primitive assertions to talk about individual outcomes, where every state in the set of outcomes must satisfy P, but we also require that the set of outcomes is non-empty. So this outcome is non-vacuously reached. And using all of these constructs, we can now describe the bug that we were originally looking at. So essentially what we've done here is we took the Hoare logic specification we were looking at the beginning, but we've replaced the disjunction, which wasn't expressive enough to describe the bug, with this outcome conjunction, and we now see that both of these outcomes are non-vacuously reached by actual program executions. So in particular, what this means is, well, the error is definitely reachable. So that tells us we're describing the bug. But the problem is, well, maybe it's not so much of a semantic problem, but we are still carrying around information about this OK execution, which isn't really relevant from a bug finding point of view, but even worse, you could imagine that maybe this program isn't just 2 lines, it's like these 2 lines followed by a million more lines. And once we get to the point where the program has crashed, we know that nothing else is going to happen to that trace, but we shouldn't really have to analyze the next 1 million lines in order to see where the OK outcome is going to end up. So what can we do there? I mean, this is the under approximation that I was alluding to at the beginning. What can we do here? Well, we can kind of just rearrange this post condition. We can drop the OK outcome and replace it with true. True is an assertion that describes any set of states. And now what we're saying is, well, this error is still reachable, but maybe something else happens too. Maybe there are other outcomes. And that true is vacuously satisfied by any outcome, so we don't really have to keep examining the rest of the program. Going back to the pictorial world, what this kind of looks like is in the post condition, we draw this circle around the bug. We call that Q. And then we draw another circle around everything else that could happen. And we just say, well, all of this is vacuously satisfied by true. OK, so we've now seen kind of anecdotally that outcome logic can describe bugs. But we actually have a more formal result as well, which essentially says that any specification that's false can be disproven in outcome logic. So you can kind of read this theorem in two directions. If you look at the top, you see this triple. What you think about this is kind of what you want the program to do. But if it's not semantically valid, then going down, we can see, well, there must be some other outcome logic triple that is valid. And then going up, we say, if you prove this other triple, then you've disproven the original specification. So one question, you may have heard of incorrectness logic, and one question you may ask is, how does this compare to incorrectness logic? So you can use both of these logics to describe bugs, particularly the type of bugs we were looking at where we're trying to find programs that crash due to memory errors. But the semantic description of the bugs you get is quite different. So in outcome logic, what we say is, if you run the program in any state, seg faulting is one of the possible outcomes. In incorrectness logic, you say any crash state where x is null is reachable via some execution from some start state. And then you may ask, well, which of these semantics is kind of more preferable? And the answer, or one answer, comes from a paper from Uppsala last year, which talks about manifest errors. The idea of manifest errors is that it's really useful to be able to know what initial conditions you have to satisfy in order to force one of these bugs to occur. And you can see in outcome logic, we immediately know in this example that this bug can occur starting in any start state. Whereas in incorrectness logic, we just know that it will occur in some start state. So the semantics of outcome logic makes it a lot easier to identify these manifest errors. OK, another thing is that you may ask is, well, OK, we've showed this theorem of that you can disprove any specification, but what do these disproofs kind of look like? More specifically, I showed this picture before that this is kind of what a valid outcome logic triple looks like, but how can this specification be false? Well, there's kind of two ways that this can be false. The first one is that something bad sometimes occurs. And these are the type of bugs that incorrectness logic also deals with. But there's actually another way that this can be false, which is that one of these good outcomes never occurs. And this is also something you can prove with outcome logic, but it's not possible to prove this with incorrectness logic. So I started by asking, can a single program logic handle correctness and incorrectness? Let's kind of up the stakes a little bit and say, well, can we handle correctness and incorrectness with effects? And so in the paper, the actual formalism we use isn't really based on sets, but is rather based on, it's parametric on some monad. So you can instantiate this logic with a variety of different types of effects and prove correctness and incorrectness in those different scenarios. And one such effect is for probabilistic programs. So you can imagine that maybe you don't just want to know if some bug is reachable, but you want to quantify how likely the bug is to occur. And one example where that may come up is if you're dealing with some sort of distributed program that's communicating over a network, but the network is unreliable and may drop messages, and then you want to bound how likely is an error to occur. And so in this case, we say, well, this program will succeed with probability 99%. Okay, so I started with this quote, program correctness and incorrectness are two sides of the same coin. I hope I've now convinced you that correctness and incorrectness are actually just two usages of one program logic. And with that, I'm happy to take questions.
We have time for 3 or 4 questions.
Thank you for the great talk. So at the beginning, when you were giving the semantics to this outcome conjunction, you used union. And my question is that, like, if we change that to disjoint union, do you, like, what would be the effect?
Yeah, so I think at first glance it may seem like disjoint union is actually what you want, but it doesn't actually work so well in terms of program semantics, because you can imagine that you branch into 2 non-deterministic paths. It's possible that both of those non-deterministic paths kind of end up in the same end state. And if you use disjoint union, then you can't encode the semantics of that program.
Thank you.
So it's a very interesting idea. So I have a rather naive question regarding, like you mentioned, in the post condition you can write OK and error, which I'm wondering if they are just tags, or you even have some way to express, because even for non-deterministic programs, maybe we also want to know that, for example, under which cases we can trigger this bug, because that's how you exactly find the bug to confirm that the developers confirm according to this kind of condition.
Yeah, so they are kind of tags, but they also, exceptions are another effect. So I kind of glazed over this, but you also need to have some sort of a monadic execution model to encode.
So meaning there are ways to encode, like what are the more like underlying semantics or model for these tags?
Sure, yeah, you could, yeah.
Thanks.
Hey, thanks for a nice talk. I had a question about this dropping or not inspecting this other code once you found a bug. So do I interpret correctly that if you find error x is null O plus top, as there is also some execution which doesn't error, since the non-empty condition?
So the non-empty condition is only on the primitive assertions. So top is also satisfied by empty set.
Okay.
And you can imagine, maybe there is a non-deterministic choice, so you kind of say, well, we can witness that there's another thing, but it's possible that execution diverges.
Yeah, exactly. That was my question.
So, but it's still valid in that case.
Thanks.
Thanks for the super interesting talk. So I guess with all these things in terms of over and under approximation, the challenge is really figuring out what do you do? Do you have partial correctness? Do you have total correctness? Can you distinguish that in the outcomes, or is that somehow built in already?
Yes. So outcome logic in this formalization is sort of between partial and total correctness. It's not really total correctness because it's based on a finite trace semantics. So you can prove, for example, that the program always diverges. You can prove that it sometimes terminates, but you can't prove that it always terminates or that it sometimes diverges, which is something that we're working on extending. But yeah, you can encode partial correctness by basically, because these primitive assertions guarantee some sort of reachability. So you just take a disjunction of that with like something that says that the set of outcomes is empty, and then that's partial correctness. Okay.
Let's thank the speaker again.
Thank you.
Thank you.
Our next talk is from Anshuman Mohan on distinguished paper, the title Formal Abstractions for Package Scheduling. So over to Anshuman.
Thank you. You may have heard of this hip new thing called software-defined networking, which made networks programmable. So an early goal was routing, and that was all nice, but now you want a little bit more. You want control over packet scheduling. So here we are in Qashqai, and packets are coming to us from either Hibamar or from Barheo. And I want to know in what order these packets will be released from me, because I'm just a waypoint. They're going on from me. Okay, basic tools will sort of work fine. So imagine in my Qashqai-based packet scheduler, in my switch, I have a FIFO, just first come, first served. I can do basic buffering, life is good. I can do a little bit more. I have a PIFO. PIFO is just networking speak for a priority queue. I can do a little bit more programming, nice. But actually, modern scheduling requires quite a bit more, often in terms of hierarchical scheduling algorithms. So say every packet that came from Hibamar is either headed to Porto or to Torres Vedras, and I've been asked to interleave red and blue packets, and among red packets also interleave purple and tangerine packets. I'm in a bit of a fix, actually. My PIFO is not going to be able to handle this. But thankfully, from SIGCOM Valhalla, I've received a PIFO tree. This is a mythical beast. It doesn't actually exist in reality, but it's been given to me gratis for the purpose of this talk. And it totally solves the problem, right? This is a tree-shaped challenge, and I have a tree-shaped solution. Great, life is groovy. In fact, the PIFO tree can even do more than I've asked. It can do arbitrary sort of sharing, not just equality. It has state. Very, very nice. The day is saved. Sadly, the user says, look, everything worked fine. You did what I asked, but I was still seeing congestion because large packets were sort of clogging up the works. I want to split up my flow in a different way. Please interleave small, medium, and large packets, and then do some more stuff among the small packets. That is my new request. Look, my PIFO tree is totally going to keel over and die. It just can't conceive of splitting the flow 3 ways. It's intimately tied to the notion of splitting 2 ways, and then 2 ways again on the left side. You don't know what a PIFO tree is. I appreciate that. I'll solve that shortly. But already you can appreciate, what you can appreciate is how unsatisfying this problem is, right? This is a nice gadget. It can do a bunch of stuff, but it fails in an unsatisfying way. And I've not just sort of made this up. And users are going to want to program the trees in all kinds of ways. And the hardware, which does not turn on a dime, is going to want to build one thing and deploy that. And I'm going to have to make a connection between those 2 things. And that's what this work will do. I'll show you what to put on all your hardware and how to get there. All right, time to talk about PIFO trees. This is I'm still trying to solve the red, blue, purple, tangerine challenge from earlier. I have a tree-shaped gadget, and all my nodes are PIFOs, priority queues for our purposes. In my leaves, I'm carrying packets. These are the colored things. In my indices, in my other nodes, I only have the 1 right now. I'm carrying indices. In particular, I must carry 2 instances of the number 1 because there are 2 things in my first child, and I carry 3 instances of the number 2 because there are 3 things in my second child. Of course, the order of those is up to me. That's just a PIFO doing its thing. If I honor this stuff, then my PIFO tree is well-formed, and a well-formed PIFO tree is a real cool thing because it behaves like a queue. It can be pushed into and popped from. Let's do both of those things. How do we pop it? You pop the root. Out comes the most favorably ranked item, which in this case is rendered on the far right. So the 1 comes out, and this triggers the popping of my first child, and what comes out? P1. This is the result of popping this tree 1 time. Let's do it again. Pop. 2 comes out. Pop. B1 comes out. If you do it all the way, that's what you get out. And I'm going to put the tree back for you, but this is the logical state of the tree. This is what the tree is sort of trying to say. I'm going to put these bars over the purple packets just to show you that those are actually also red packets. This will become germane shortly. Let's push into this tree. So our tangerine packet, the first tangerine packet is arriving, and where does it go? Well, it's going to go into this suggestively red-colored left leaf, okay? And because I have a chance to sort of get some justice, I have 2 purple packets in a row, and I have a chance to put a tangerine packet in there. I'm trying to get parity, so it sort of suits me to put that tangerine packet between them there. This tree is no longer well-formed, and I owe the indices, I owe the root a 1 to make it well-formed. And again, it suits me fine to put that 1 between those 2 2s, and therefore achieve parity. Okay? So this tree is well-formed. It has fully accepted my tangerine packet, and just to show you the state of this tree, it looks like so. And I put those bars back on there for you to show you what a blue packet is and a red packet, and then further to red packets, we have tangerine and purples. And I've successfully accepted this tree indeed because, look, I have red and blue interleaved, and further purple and tangerine interleaved. Something quite subtle had to happen along the way, though. B2 and P2 have swapped places, and I didn't do that in front of you. It sort of happened as if by magic. It happened because of this, because I, T1, was popped not by the 1 that I inserted, but by some other 1. And the 1 that I put into that queue with my own hands in front of you has triggered the popping not of me, but of somebody else. Like that. This on-the-fly switching of targets is what gives PIFO trees their power and expressivity, and can do stuff that a PIFO can't just do. It also makes them a pain to study. If I lost you there because it was all sitcom stuff, please come back. We're going to get into PL land now. The key insight here is that a PIFO tree, by its very shape, manifests a programming language. And a program written using that programming language is precisely a scheduling algorithm. In particular, when a blue packet's coming in, what's actually happening, my program is looking at the packet, looking at its state, etc., and then figuring out a path with which to insert this blue packet. I'm going to have to put a 2 in there with some rank, R1. R1 is the rank with which I'll insert the number 2 into my root. And R2 is some rank with which I'll insert the packet B1 into my right child. I'm obfuscating what R1 and R2 are. For our purposes, they are just the ranks I needed to put the thing where I wanted it to go. Right? So 2 went somewhere, B1 went somewhere in that queue. Great. And you're sort of seeing a connection between the shape of a tree and the expressivity of the language that the tree manifests. And now we're really cooking with PL gas, okay? Because can we compare the expressivity of languages? Well, can I affect the same permutations on the incoming flow that you can? Can I compare expressivity of trees? And sort of the pièce de résistance, can I compile a program written against one tree so it instead runs against a different tree of a different shape? I'm not just doing this for my health. This is going to solve our problem, right? We had no way to deploy our gadget. I'm going to tell you what tree, some sufficiently expressive tree, to put into all your switches and how to get there via compilation, right? So crisply, the contributions of the paper are the first formal model of the PIFO trees, general theorems of expressiveness with regards to tree shape, the compiler I just mentioned, and a simulator to aid experimentation. The talk is not the paper. I will lead with the compiler and give you the rest as I need to. Okay. Expressivity of trees basically follows your intuition. If you fix a particular height, trees with more leaves are more expressive. If you fix a particular arity, then taller trees are more expressive. This quickly gets out of hand, actually, when you have bigger and bigger trees. But thankfully, it's all captured nicely by our new notion of homomorphic embedding, which is to say, try to find, so here's my source tree and my target tree, try to find a map from nodes to nodes, trying to get the root to map to the root, leaves to leaves, and as you do so, respect ancestry. So here's a successful case of homomorphic embedding. Here's a hairier case. But let's look at the simpler case, because I'm going to show you a little thing about it. So the point here is that the target tree, if you believe me, can accept the source tree. It can say what the source tree is saying. It can affect the same permutations. But by failing spectacularly in the next slide, I'm going to show you why it's a little trickier than you think. So let's try sort of a simple case. The tree on the left is just trying to do parity among its 3 children, red, blue, and green, with those equal signs. And I've told you to please try and get the same behavior on the binary tree on the right. All right? The first approximation, you might say, OK, just do it 1/3 and 2/3, and among the right node, do 50-50. Right? This seems to work at first. You know, if everybody is chatting, this actually will work. But consider what happens in case of silence. In case the blue flow fell silent in my source tree, my oracle tree, then the red and green would correctly share what remains, 50-50. This is what I want. However, on the right, if blue fell silent, green would totally take over the entire right half of the tree and dominate red 2/3 to 1/3. The point is, there's a little more to it than you think. All right? Basically, I had a root, and I copied over the root sort of faithfully, but I've had to insert this transient node just to make the shape work. And my point is that trying to give the transient node any standalone policy, like we just tried, is always going to fail. It's going to be subverted by some sort of unfriendly flow of packets, usually full of silences, that will sort of hurt me. Right? The observation is that the root on that receiving tree really still has 3 children, red, blue, and green. And we're all still on talking terms, no problem. It's just that my children, blue and green, have left home and gone to college. They live out of state now. Okay? And earlier, I used to be able to reach blue by just saying 2, and now I reach blue by saying 2 and then 1. Right? Keep that intuition in mind as I crisp this up in the next slide. So I've given us some numbers in the root node now. I'm trying to achieve parity as before. And the way to actually copy this over, actually make the compilation work, is it proceeds in 2 steps. I'll do it node by node. So for the root, I copy over the queue, sort of ranks and all. Ranks I'm not showing because they're sort of baked into the way I've drawn it. That queue has been copied over, but I'm in the wrong addressing regime. We already know every time I say 3 or 2, I really mean 2 and then something. So I renumber to change all the 3s and 2s into 2s, like so. And for the transient node, I'm going to copy again, but I have no heirs of being able to reach red anymore. I have no 1th child as before, so I copy it over, dropping all 1s, like so, and then renumber for the new addressing regime, like so. So this different style of copying is resistant to silences and sort of adversarial packet flows. It's really illustrative to look at a push going through, so let's look at that. If a blue packet were coming in the oracle tree, I would have assigned some path to it, starting with 2 and some rank R1, and then something else, okay? What do I do in the receiving tree? So the 2 went in, and I achieved parity. You can see 3, 2, 1, 3, 2, 1, 3, 2, 1. Very nice. And in the receiving tree, that same B is going in, right? And you'll already know that we're going to have to put a slightly longer path in there, starting with a 2 and then some 1. The question is, with what ranks? And here's the great news. The answer is actually real clean and simple. Use the same rank, R1, as the original tree would have. And as if by magic, my 2 will slip into the right place, my 1 will slip into the right place. Why has this happened? Because I copied my queues over faithfully, just changing numbers cosmetically, keeping the ranks around. So we were given an embedding from a tree shape to a tree shape. We were able to lift it to now operate on a brain, compiling to a brain, automatically generated. But why should we be given an embedding? Let's just make our own, right? So remember, this is what we're aiming for, trying to get these dashed lines, trying to get these homomorphic embeddings automatically. I have 2 algorithms for you, and they both start with heterogeneous source trees, by which I mean I don't actually make any assumptions on the arity or regularity of my source tree. If you tell me that your target tree is a regular D-array tree with some arity D, I have an efficient algorithm which will actually construct for you the minimum height D-array tree that can accept your source tree. If you bring your own tree, it's a heterogeneous tree, it's a wild tree, I have another algorithm less efficient which can tell you if a mapping is possible, and it gives you the mapping if so. So what's the workflow of somebody trying to actually use all this stuff? Say they had this dream. It's a 3-tier hierarchical thing with 7 different floors being managed. WFQ and RR are different scheduling regimes. We won't get into it. This is their dream, right? But they are told that the hardware only supports a regular branching binary tree. No problem. We know how to instantiate it now. We'll use the first algorithm I mentioned to create the minimum height binary tree that will accommodate my tree, and then I'll instantiate it, as my compiler suggests, like sort of so. This is automatically generated with an automatic brain, which I didn't have to write by myself. Okay? And now we can sort of look at all this stuff go through a simulator, which is also a contribution of our work. So the point of the simulator is that it can take a pcap of packets and run it through a PIFO tree and show you what would happen if the PIFO tree were to schedule those packets, including like overtakes and delays and so on. So simulating the first tree, the logical desire shows us sort of this. This is a hip new way I'm trying to visualize schedulers. I hope the community catches on. But basically, shorter bars mean better performance. You were held up by the scheduler for a shorter time. Longer bars mean worse performance. The scheduler held you up for a longer time. A bar sort of starts when the packet enters the scheduler, and it ends when the packet is released, right? So that's the result of simulating the first one. And this, the second one, they are the same picture. Great. Why should you believe any of this? Well, we have an underlying formalism. Here I'm just showing you what it takes to sort of chase a push up the entire formalism. It really is better appreciated in the paper, so I'll send you there. I will say there's no point in the paper where I have a horrible picture like this. The paper does quite a nice job gently introducing you to all this stuff, so I do recommend it. But the point is that we've solved our problem. We have a general way to deploy PIFO trees. Let the hardware support some tree, and let the user program against some tree. Today they want that. Can I compile it? Well, yes, I can, into that fragment of my target tree. So please light up that much, and I'll do my business on that. They wake up the next day, they want something else. I compile again and see, is it going to fit? Yes, it is, into that fragment. And so again, life is good. I can go on. But the next day they want that, and I check if it's compilable. Oh, no, it's not. But now I can go to my user and give them a little bit more information. I can say, oh, look, you had too many leaves, or your height was too much, or whatever, and they can sort of adjust. And if it turns out that like millions of users all need something that the hardware cannot provide, we can ask the hardware providers for some change in a sort of an informed way. We're not just not just being flip and asking them to make new things for us every single day, right? This has been formal abstraction packet scheduling. I've been Anshuman Mohan. I'm happy to take any of your questions.
You have time for a couple of questions.
Okay, at the end, those checks and X's went by a little bit quickly for me. So what are the formal properties that the system satisfies? Is it sound and complete?
So for the first algorithm, where I was telling you about a tree being constructed for you, basically it's always going to work. I'm always going to be able to construct a tree of your desired arity. It just may be awfully tall. It may be taller than your hardware sort of supports. And so I might say, look, it's not going to fit into what's actually provided. Yeah.
Okay, and then when you say it doesn't fit, there is no fit. If your tool says that there is no fit, I can't compile it down to this hardware. That's
accurate. Yeah.
That's accurate
Yeah,
too.
yeah.
Okay, great.
Yeah.
Any more questions? Well, I have a quick question. Okay, let's thank the speaker again. Our next talk is by Jens on P4R type, a verified API for P4 control plane programs.
Yes, well, okay. I'm Jens. And if you're not already tired of the software-defined network talks, don't worry, here's some more. So, yes, I'm going to talk about this API that we've been developing. But first, I'll have to give an introduction to these software-defined networks. So, software-defined networks is a new type of network architecture that's emerged within the last decade or so. And essentially what they are is that they provide the user with more options for programming network devices. So network devices as in routers and switches. And this P4 language here is the one of the most popular ones for programming these network devices, these software-defined network devices. However, with increased configurability comes also an increased risk of errors. And particularly what we look at here is that actually about 4 out of 10 of the bugs in software-defined networks occur when trying to process system configurations. And this essentially means they occur when trying to update these software-defined network devices. So our problem statement is relatively straightforward. Can we verify that these configuration updates actually can we verify the correctness of these configuration updates statically? And well, to answer that problem, we have to look first into a little bit of how P4 works. So the P4 language is a domain-specific language for implementing router behavior. What this means is that in P4 you implement the way that how the routers pass and depass packets, which forwarding tables they contain, which actions they contain, and how these actions work, so how a packet is forwarded, how a packet is dropped, and so on. And then you compile this program, and then you send it to your device of your choice, basically your router of your choice. But when you compile this program, you also get a metadata file that's called a P4 info file. And this P4 info file contains basically a description of the configuration of the data plane, the program that you've just sent. And it contains sort of the list of tables and the actions that are hooked up to specific tables and the parameters that those actions take and so on. And then, sort of as part of this P4 language, as a separate part, there's also this P4 runtime API, which is language agnostic. And that is provided for doing these dynamic control plane updates. Now, what are control plane updates? Well, they are essentially updates that relate to the networking logic of the router. So this more or less just amounts to sending, reading, and deleting forwarding table entries. So that's what the P4 runtime API does. And the intention here is that the problem here, I guess I should say, is that this API is weakly typed. The intention is that you look at the P4 info metadata and you adjust, you format your forwarding table entries accordingly, but actually there's nothing that forces you to use this P4 info file. To give an example of a problem, consider this snippet on the left of a P4 info file. It has a list an IPv4 table that matches on the IPv4 destination field of a packet, and then it can run the IPv4 forward action. And on the right-hand side, we have a Python script that uses this P4 runtime API, and it's pretty simple. It builds one of these forwarding table entries for the IPv4 table. It says, okay, match on this particular IP address, and if it matches, then run the IPv4 forward action with this MAC address destination and send it out of that port. And that's all well and good, but you can see, since it's in Python, you could make some errors here. So, for example, you might make a typo you might use a table name that doesn't exist. You could try to match on a field that doesn't exist, or more subtly, you could use an action that might exist somewhere else in the P4 info file, but it's not hooked up to this specific table. And now you might say, oh, but well, this is in Python. Why don't we just, since the API is language agnostic, why don't we just use a type language then, like Haskell? Well, Haskell won't save you this time, because while the API for a strongly typed or a typed language will specify the format of the packet, so it will have a table name match field and so on, the actual data will still be strings. So we need to do something a little more sophisticated. And the whole point here is that really we want to force the users of the API to conform to this P4 info file. So our idea is to capture this P4 info file information at the type level. And that is actually exactly what our Scala library P4rtype does. So it provides two things. First of all, it provides a type generator for encoding this P4 info file as Scala types, and it provides a strongly typed type parametric API that overlays the weakly typed P4 runtime API. And so the idea is then that if you use this strongly typed API together with the types that you've generated for a specific P4 info file, if you try to update a router that uses the configuration from which that P4 info is derived, you can basically prevent any operation that contains non-conforming table entries. And as the underlying theory for this, we also develop a formal language, FP4R, which I'll get into in just a second. But let me just show you a quick demo of how this API looks in practice. So here is a Scala 3 program that uses our API. We connect to a switch, and then we insert a table entry. You should notice here initially that this looks very similar to the Python program. This is essentially, it does the same thing as the Python program does. But there's no sort of, there's basically nothing in this program that's not already in the Python program. We don't need to do any sort of type annotations or anything else, it just works. But if I try to do one of the errors from before, so for example, if I write IPv6 forward here, then, yes, an error will occur. And it will say, actually, you've given me this IPv6 forward action, but I was expecting a table action for the IPv4 table. Good, it works. OK, then let's move on to the formal foundation. So we developed this FP4R formal language. It's based on FSUB, as well as the theory of match types. But we have some significant additions to this. So first we add concurrency and communication primitives in the style of process calculi. Instead of the nominal subtyping from the match types paper, we add structural subtyping, and that's because we need to be able to reason about the data, specifically the forwarding table entries. So we need records instead of classes. And we add these singleton types, and we also add, we adapt from the match types paper, we adapt these match types, but we omit the option of having default cases in the match types. So just to show a quick snippet of the term syntax. There's nothing here that's super weird. We have values, variables, records, match terms, match expressions, function applications, and then we have this up here, which is the communication primitives. So this up is just basically what overlays the weakly typed API. And you can connect to a server, and then you can read, insert, modify, or delete table entries as you wish. As for the type syntax, again, most of this is something that you've seen before, but there are some changes. We have typed server addresses and typed channels for communication. We have these match types, but without the default case, and we have these singleton types. So here's an example of a match type, or I guess it's a type abstraction that contains a match type. But this is actually how, the P4 info file, this is how the constraint provided by the P4 info file is expressed as a type. And the way this works in practice is that so this is a type abstraction, we apply it to this singleton type IPv4 table, the singleton string IPv4 table. Now the type doesn't reduce, but it is subtyping equivalent to, so first of all, beta reduction by just replacing this type variable table with the singleton type IPv4 table, but then that is also subtyping equivalent to the continuation type of the specific case that the IPv4 table singleton type matches on. So in this case, it's the union type. It's the union of the two singleton types, IPv4 forward and drop. Good. Now that's the syntax. As for the semantics, so we provide both a server semantics and a client semantics. The server semantics have this predicate in them that says that if we try to insert a forwarding table entry V, then it must conform to the server configuration C. And so obviously you can see here that if the table entry that we're trying to insert doesn't conform, well, then the server semantics get stuck. But actually there's, on the client side of the semantics, there's nothing in the client semantics that prevents it from trying to send an ill-formed, essentially, forwarding table entry. But this is where our typing discipline comes in. So our typing rule says that if we're trying to insert this forwarding table entry, well, that actually has to type using the same types that are used in the communication channel. And together with this, we also have this conformance property, which says that a table entry conforms to the server configuration C if and only if that table entry can also be typed using the encoded the match type constraints that are encoded from the server configuration. So basically the typing rules and this conformance property allows us to get, well, type soundness. So these are the theorems and the lemmas that we show. There's nothing super strange here. You've seen progress and preservation many times, I imagine. The main thing, I guess, here that's strange is that, or different, is that we show type soundness not just for a single client, but actually for all clients in what we call well-typed networks. So if a network is well-typed, then all clients in it will fully reduce into values. Can be fully reduced into values. Right. So actually that was pretty much our contribution so far. In terms of related work, there is no previous work that addresses verification of the P4 control plane. There is a lot of work, however, done on the P4 data plane verification. And there is a lot of previous work as well done on control plane verification in general, but it's not P4 specific, and actually it's either it's actually too, it differs pretty significantly from what we've done. Either it's too specific, it focuses on specific protocols where P4 is protocol agnostic, or it's too general, or it's on a different level of abstraction entirely. Yeah, so in conclusion, we contribute a formal model of P4 runtime networks that compose P4 servers and P4 runtime clients that are written in this, where the P4 runtime clients are written in this formal language, FP4R. We provide a typing discipline as well for this formal language, which essentially only allows conforming P4 runtime updates to type. And using this theory, we developed the P4R type API for Scala, which is a strongly typed API for invoking this P4 runtime API. In the future, we'd like to ideally have a fully verified P4 programming pipeline for both the control plane and the data plane. And we're actually looking into extending currently FP4R with behavioral types, which would then allow us to show not only these, how to say, basic properties of conforming to the P4 info file, but actually show that that FP4R programs have some or preserve some property in the network. Thank you very much.
Okay, questions?
Thanks for the talk. This is cool stuff.
Thanks.
I'm not sure, you probably know this history, but others don't. So the first P4 API, control plane API, was actually typed. And P4 runtime was introduced by Google and some other companies because the typed API was sort of too coupled to the rest of the control plane stack. So concretely, they'd have to sort of recompile, many, many lines of code every time something in the P4 model changed. And so they moved to this untyped API so that they could sort of keep the same protocol speakers on either end and then, change things higher up the stack. So I'm curious if you have thought about situations where there might be, transitions between control plane apps or control planes, and where there might be a period where you can't sort of turn off the whole network and upgrade everything. So you've got some data planes running this P4 program, some other data planes maybe running a different one, some control plane apps running one application and some the other. And so you have this mixture, and you still want to know somehow that all the API interactions are well typed and maybe also some behavioral properties.
Yes. I mean, yeah, the thing is, so I guess, does this relate to, I mean, so obviously you can, if you change the configuration of a P4 enabled device on the fly, the types would also change. Is that what you're?
Yeah. So I think in practice, one needs to handle situations where there's multiple versions, right? And most protocol APIs support versioning or other ways of dealing with this, but.
Yeah. So that's sort of like currently it's a limitation, right? So you'll notice that there's no primitive or operation that changes that allows for changing a configuration, right? And it's something that we will have to eventually handle. Yeah.
It'd be really cool to extend the typed approach to do that.
Thanks.
Well, to answer the previous question, that sounds like a gradual typing problem. I'm curious about behavioral types. Can you say what's next?
You mean like specifically regarding behavioral types?
Specifically regarding behavioral types.
Oh, well, so we're just looking into it basically. And the things, so we are using a version of behavioral types that was published a few years ago, related to this FPI library, and well, I mean, we are kind of we're looking into it, I guess, is the state of it. So I mean, in terms of properties that we can prove, maybe, I guess you're just, I mean, yeah.
Also, it reminds me a bit of Amazon's work on blocking public access and configuration files. So they have a solver, Zelkova, which will see if my collection of rules allows public access to this data. And that's certainly something that I don't want to happen since I went to the work of writing all the rules.
Right, yeah. Yeah,
Okay,
I'm not
so it's
sure
in
I'm too
progress.
familiar, but maybe we can talk afterwards. So, yeah, thanks.
I have a question. So these types are parsed from a configuration file, if I understand it.
These types of what, sorry?
Parsed from a configuration file.
Mm-hmm.
So there's this concept of type providers, which is their part of, I think, Idris language, which try to do it for database schemas, right? So you parse this type of the data from the database schemas, and that becomes, the type checking is based on the types that are actually parsed from sort of configuration files. So do you see any relation between type providers as been implemented independently typed language to whatever you've done?
In relation between type
providers?
Type providers. I'm not familiar with that theory, so I can't say, unfortunately.
Okay.
Yeah. but I'd be interested to talk afterwards.
Okay. Okay, thank you. Thanks, speaker.
2 session of UPSLA papers. I'm delighted to introduce the first paper, Stuttering for Free, by Minky Cho, Youngju Song, Dongjae Lee, Leonard Gaher, and Derek Dreyer. And Youngju Song will be giving the talk.
Can you hear me?
Yes.
Oh, great. Thank you. I'm Youngju Song, and today I'm going to talk about freely stuttering simulation, which we believe is an ultimate form of stuttering simulation. This is a joint work with Minky Cho, Dongjae Lee, Leonard Gaher, and Derek Dreyer. Behavioral refinement, shortly refinement, is a widely used notion in formal verification for relating two transition systems. The target system behaviorally refines the source system if the set of behaviors of the target is a subset of the set of behaviors of the source. In other words, refinement ensures that the target behaves as specified by the source. For example, the correctness of a compiler is usually stated as a refinement between the source program and the compiled target program. One of the most common tools for proving refinements is the method of simulations, especially those more advanced versions of simulations called stuttering simulations. In this work, we propose a new stuttering simulation called freely stuttering simulation, or FreeSim for short, that provides strictly better usability than all existing stuttering simulations. To see what FreeSim is, let us go step by step. I'll first explain refinement, stuttering simulation, and then explain FreeSim. Consider proving the refinement between the following two systems. In this talk, the state A is always the initial state. On the left is a target system where it either steps to the state B while emitting an event 0 and then comes back to the state A, or it emits an event 1 and directly returns to A. On the right is a source system similar to the target. It either steps to the state B while emitting 0 or steps to C while emitting 1. On both cases, it can return to A, and in case of C, it can step to B while emitting 42. Of course, one could establish the refinement by directly computing the set of all possible behaviors in both systems, and then by giving a mapping from the target set into the source set, and thereby showing the set inclusion. But such a reasoning is temporally global in the sense that we should match a whole trace in the target with a whole trace in the source. With simulation technique, we can prove this in a more temporally local fashion, that we match a step in the target with a step in the source. Now let us see how stuttering simulation can help us proving this refinement. Let us first consider only the subsystem of the previous example. The simulation technique first requires us to specify a relation R, often called a simulation relation. Such a relation should relate the entry point of the target system and the source system. Then one should prove that for any pair of state t, s in R, if target takes a step to t prime, emitting an event E, the source should simulate this behavior by stepping to s prime, emitting the same event. The resulting state t prime, s prime should again be in the relation R. Now, back to the example, we first set up the following simulation relation, which simply relates the corresponding states. Then the proof proceeds as follows. It begins execution on A on both sides, and for whatever execution target takes, the source should follow it, and result in R again. Then for whatever next step the target takes, the source should again follow it, and result in R again. That's all. What we have shown is sufficient to imply refinement because any whole trace in the target can find its matching whole trace in the source by repeating this stepwise translation. Now let us consider the full example. Proving this branch is similar to proving the other branch before, but there is one critical difference. On the target, it takes a single step to get back to A, and on the source, it takes 2 steps to get back to A. Thus, both rule alone is not enough to relate these executions because we can only match the same number of steps. So let us enlarge the simulation with 2 more rules that allows us to execute the source only or the target only. In these 2 rules, only one side is taking a step, which is often called a stuttering step. And this is the reason why such a simulation is called a stuttering simulation. Now let us see how this works with the example before. If target executes the lower branch, we use both rule and pick the upper branch in the source. Now we are left with proving that the target execution can come back to the state A alone. We proceed with source-only rule, in other words, execute a stuttering step in the source, then the proof is done. As you can see, stuttering simulation provides powerful mechanisms to establish refinement in a local fashion. However, there is one minor caveat. The caveat is that the simulation that I just showed you is actually unsound. In other words, it does not imply refinement. The reason is as follows. Those two edit stuttering rules are overly powerful that it trivially relates diverging system with any other system. For instance, suppose we have a diverging system on the target. We can prove simulation against any system on the source by picking the simulation relation containing just AT and AS, and then, given any t, s in R, we can trivially finish the whole proof by just executing target only. The lesson here is that infinite stuttering is bad. Thus, to prevent infinite stuttering from happening, all the stuttering simulations enforce one more condition to the user. The exact style on how such an enforcement is made differs by simulation, but on the bottom line, they all require the stuttering steps to appear only finitely many times before executing both. With this fixed simulation, it is easy to see that the previous wrong proof is properly ruled out. The wrong proof applies target-only rule infinitely many times without applying both at all. However, while this condition ensures soundness, it is often burdensome to the user and rejects some perfectly valid proof strategy. To see this, consider the following motivating example. Transition systems are now equipped with variables p and q, and assigning a value to a variable is considered a silent event. The system on the left first picks the value of the variable p, either 1 or 0, and then picks the value of the variable q in the same way. After assigning these variables, the system either repeats this process or prints the current value of p and q and terminates in c. So the whole behavior of this system comprises divergence and printing a pair of integers. Now consider the system on the source. It is basically the same as the target, except that it picks the variables in a different order. That is, it picks q first and then p. Now, when proving a simulation between these two systems, existing simulations unnecessarily restrict the proof strategy. Intuitively, the proof should be rather straightforward. Whatever pair of values target chooses, source should be able to simulate it just easily. Specifically, starting from the simulation relation that relates A on both sides, you would like to execute the target twice and execute the source twice, picking the same branches as the target. However, this proof does not work. In the case of a divergent execution, concatenating this proof segment infinitely many times would result in a proof with infinite stuttering steps without executing the both rule. This is somewhat unfair because this is actually a sound proof strategy, unlike the unsound proof earlier. What actually matters for soundness is ensuring that both sides are taking a step, and in this proof, we actually do. Because this intuitive proof fails, all the existing simulations enforces us to find the right place to execute both rules in the for side. And this is often burdensome. Suppose we just apply both rules in the beginning. However, we do not yet know what is the right branch to execute in the source, and let us just assign 0 to q. But if later the target execution chooses a different path, that it assigns 1 to q, it could end up printing a different value on the source and the target, thus failing the proof. Indeed, the only way to conclude this proof is to execute target only, both, and source only in this exact order. To summarize, in existing simulations, the user needs to understand the system in detail before starting the verification in order to execute the both rule at the just right point. This enforcement complicates the proof, and here comes our question. Can we verify this example asynchronously as in our first attempt? The answer is yes. And the key idea of FreeSim could be pictorially described as follows. To begin with, progress is what ensures the soundness of a simulation technique, where progress means that every proof segment, a proof starting from R until it comes back to R, contains at least a step on both sides. What existing simulations enforce is what we call a synchronous progress, meaning that it should execute the both rule. However, the synchronous progress is just one way to ensure progress. In FreeSim, we relax such a condition and allow what we call the asynchronous progress. In FreeSim, executing any stuttering step now contributes a partial progress on each side. Source only contributes the source partial progress, and target only the target partial progress. These partial progresses can be made asynchronously, of course, and later be combined into a full progress. And the asynchronous progress interface gives us strictly better usability than the synchronous progress. This is because every proof involving the synchronous progress can be translated into a proof with just asynchronous progress. This is the summary of our contributions. We developed FreeSim that allows asynchronous progress for the first time. FreeSim is propositionally equivalent to existing simulations, but it offers a strictly better usability than all existing stuttering simulations that we know of. To objectively compare the usability of these different techniques, we have devised an interesting notion called replayability. Our theory is fully formalized in Coq, and we evaluate FreeSim through various challenging case studies, including extending I-tree's library with dual nine-terminism. FreeSim is ready to use and is available in OPAM. In the rest of the talk, I will explain the upper 2 points further. The definition of the FreeSim is as follows. For any pair of state in R, one should proceed the proof with K, which is inductively defined with 4 cases. The relation K carries 2 Boolean flags, BT and BS, each denoting whether partial progress has been made on the side. Executing both rules turns on both flags, and executing the stuttering steps turns on only the corresponding flag. When concluding the proof with the base rule, it checks whether the full progress has been made. Now let us consider the motivating example before. It begins the proof with the both flags as bottom, turn the target flag on when executing the target, turn the source flag on when executing the source. And we can now conclude the proof since both flags are on. So we have seen what FreeSim is, and there is one last thing I would like to talk about today. At the beginning of the talk, I bragged about FreeSim being an ultimate stuttering simulation, like the only stuttering simulation. And I'll explain why I think so. FreeSim and existing stuttering simulations, notably explicit stuttering simulation and implicit stuttering simulation, are propositionally equivalent. It means that if one simulation can relate 2 systems, the others also can somehow relate those systems. However, as we have seen before, FreeSim offers more proof strategies and giving a better usability. Such a difference is captured with the notion that we adopt replayability. FreeSim can replay the other 2 techniques, but not vice versa. OK, so what is the replayability, and why should we care about that? Replayability is defined as follows. If a host technique can replay the guest technique, it means that the host can do everything guest can do. In other words, the host technique can emulate the behavior of the guest technique. Formally, replayability means that for whatever rule the guest applies, the host can simulate it with its own rules. What is even more interesting with replayability is that it gives free techniques. If a host technique can replay 2 different guest techniques, 1 and 2, it can mix these 2 guest techniques in a single proof. For specifics of proof, it may use the technique 1, and for the rest, it may use the technique 2. This gives rise to a free technique, 1 plus 2, that allows interleaving between these 2 techniques. So in this slide, I have put all the stuttering simulations that we know of, a zoo of stuttering simulations. As mentioned, FreeSim can replay eSim and iSim. And on the top, there are 3 additional variants of stuttering simulations called MSim, FSim, and EFSim, used in the context of ComCert. We have proven that FreeSim can replay FSim, and then FreeSim replaces the remaining 2 for free. This is because MSim is a mixture of eSim and FSim, and EFSim is a mixture of FSim and iSim. Note that these techniques were proven manually before. All in all, FreeSim can replay all the stuttering simulations that we know of. In the paper, there are other interesting points that I wasn't able to cover today. While I have sanitized all the serious advanced mathematics in the presentation, this work actually required a good amount of them. And we generalized FreeSim further that Boolean flags are extended to ordinal numbers. We show that FreeSim scales better when adding new primitives like angelic nine-terminism, and also provide a compositional rule stronger than before. I'm on the job market this year, and Dongjae Lee is applying for PhD. Thanks for listening, and I'm happy to answer any question.
All right, we have time for a couple of questions. Let me start things off. First of all, really enjoyed the talk. It's nice to see this very general technique. I wonder if any of your case studies illustrate what you talked about in terms of replaying other proof techniques or maybe mixing different proof techniques.
Yes, like the one major case study in the paper is about replaying the proof techniques in COMSERT. COMSERT comprises multiple different simulation techniques, like each opted in for like the specific purposes. And what we realized is that the FreeSim can be like a unifying foundation for all these different stuttering simulations. We can replay like all the stuttering simulations in COMSERT, basically.
Excellent.
Yeah.
So another question I had about your technique is you mentioned that you can use ordinals as flags in addition to booleans to see to track the correspondence between making sure both sides take steps. What benefit do ordinals give you for the theorem prover versus booleans?
That's actually a very good question. So when replaying the explicit stuttering simulation techniques, by which I mean the stuttering simulation techniques already equipped with ordinal numbers, like we need to extend the Boolean into the ordinal numbers, and having such a fine-grained flex is useful when you are proving optimizations in compiler, because it gives you more dimension on specifying your simulation relations. So, for instance, the simulation relation the COMSERT uses already uses this index varying from the natural numbers or pair of natural numbers, or they don't use ordinal, but they already use such a power. Yeah.
Excellent. And one last question. So you mentioned usability, and I can sort of intuitively see the benefits for usability in the flexibility of the proofs. But I wonder, might it be possible to take this and do a user study to show that people can prove more easily using your technique?
That will be a very interesting the future work. It isn't included in this paper, but that will be definitely very interesting. Yeah.
All right. Any other questions? Well, let's go ahead and thank our speaker. Thank you so much. If the third speaker can come and get mic'd up, that would be great. So the next talk is on generating proof certificates for a language-agnostic deductive program verifier. Yes, it's by Xiaohong Chen, who will be giving the talk.
Thank you.
Mintai Trin, John Wang, and Grigory Rosu.
Yes, thank you.
So, looks like we're all set up.
Good. All right. Hello, everyone. Thank you for the introduction. So, and thank you for coming in on the last day of UPSLA, in the afternoon. I'm Xiaohong from Runtime Verification. And the work I'm presenting today was actually finished when I was a PhD student at UIUC with my UFI colleagues, Zhen Yao, Mintai, John, and Grigory. And since then, Zhen Yao, me, and John have all graduated. So this is why we have some sort of diversity there in the affiliation. All right. So our research work is about making formal verification results more trustworthy for all programming languages using proof certificates. And this research is important because we have issues of having large trust base in formal verifiers. And this is because program verifiers are very complex programs themselves, so it is very difficult to prove them correct. And usually they are not based on a form of semantics. So even if we want to prove them correct, we don't know what correctness means here. They are correct with respect to what? Now, what we know is that sound and complete formal verification for all programming languages is possible. And it has been implemented in the K framework, which I'll talk about later. And we also know that K has a very small logical foundation called matching logic. However, actual reduction from K's formal verification algorithm to matching logic proofs has not been studied. And this is what our work is about, right? So we formalize formal verification results using matching logic formulas. So they are the claims we want to prove. And we translate executions of the formal verification algorithm into matching logic proof certificates. And these certificates can be checked by a very simple program called a proof checker, which has only 200 lines of code. And by doing that, we bring more trustworthy formal verification to K, and we reduce trust base from the previous 120K lines of code to this 200-line proof checker. And we tested our methods on various programming language paradigms, including imperative, functional, and assembly languages. And the conclusion is that we can give efficient proof checking for formal verification. Now, in the rest of my talk, I'll spend more time in describing the background, the context of work, and then I'll show you some technical details. So the first thing I want to say is about K. So formal verification is done in a language-agnostic way in K, just like everything else. So as you can see on the right, so this is the K framework. It's a collection of these language tools. We have interpreter, compiler, modal checker, symbol executor, and of course, a program verifier. Now, what's interesting is that these tools are all parametric in a formal definition of a language. So you can define your programming languages as a formal semantics, and you can pass them as input to the framework. And the framework instantiates these tools based on the language you give it to them. So this is why we have, so this is what we call the K framework. It's a language framework. You can define the semantics of language in it. You can generate tools from it. And here's an example K semantics of a very simple imperative language called imp. So this is like the hello world example in PL. And it has two modules. It has a syntax module, a semantic module. In the syntax module, we define the concrete syntax of this language using BNF grammar. So for example, here's the BNF grammar for expressions and for statements. So you can see that we have, for example, assignments, if and else, while loops, and so on. In the semantic module, we define configurations. So this is like the state of the program run in this language. And for imp, the configuration is very simple. It's just a pair of the program, the code to be executed, and a map from program IDs to their values. And then we have all these rules. They're called semantic rules. And they define the operational semantics of a language. For example, the first rule says it's a lookup rule, right? So it says if I see a program ID X in some evaluation context, and the program state is map M, then I will rewrite X into M of X. I'll look up its value in the map. So this tells how to look up a program variable in the program map. And we have all these rules. They are written in this like a small step semantic style. So it's very clear to see how we can use these semantics to execute programs. Now you may ask, okay, this looks great. This semantics is executable. How does it relate to formal verification? Well, it turns out that you can use exactly the same operational semantics to do formal verification. So actually, K's formal verification algorithm is entirely based on such operational semantics. So somehow there is this myth in formal methods that operational semantics are only good for execution. If you want to do formal verification, you need another semantics, like denotational semantics or whole logic or axiomatic semantics. Well, that's not true, right? So operational semantics is all you need to do sound and complete formal verification. And let me show you how we can do that. So suppose we have this simple program. It's a sum program. It has a while loop. All it does is to calculate the total from 1 to n, where n is this symbolic input. And we can write the spec of this program as what we call a reachability claim. So let's say that for any value n, if I start with a sum program and empty map, then eventually I will reach this final configuration where I have no computation left. So .k means nothing, right? So there is all the computation, all the code has been executed, and the map looks something like this, where S maps to the total sum from 1 to n. Now, in order to prove this spec, of course, I need to write down the invariant for the while loop, and this looks like something like this for any S and n. If I have the loop and I have any map, then eventually I will consume all the code, and maps is updated like this. Now let me show you how I can prove this invariant using nothing but just the operational semantics of a language. Okay? Of course, the first thing is I have a loop. So I have two branches, whether I get into the loop or not. So let's say we get into the loop. And that's here. So we have a side condition, n is greater than 0, and then we have the body of the loop itself, and the same thing. Okay? And now we can use symbol execution to consume these assignments. And we see the loop again, but the values of S and N are updated. Now here's the interesting thing. So let's compare this with our invariant. Well, you will see that, okay, the invariant tells me that this holds for any S and N. And what happens here, I have a different value of S and N, so I can instantiate the invariant to prove the subgoal. And this step is called co-induction. So because you're using the invariant to prove one of its sub-goal. And this is sound because we are making some step, right? So we're making a progress, so that's guaranteed soundness. And by doing that, we have something like this. This is the right-hand side of the invariant instantiated, and this is the original right-hand side. And we see that, okay, everything else is the same, so I just need to prove this equality about integers. I can do that using SMT solvers or some domain reasoning tools. So what I'm showing here is that I can use operational semantics with symbolic execution, with co-induction. So this is the step where I prove a sub-goal using the claim I'm proving. And this gives us full formal verification for all programming languages because it's based on the formal semantics of a language. Now, you may say, well, this looks great. You have a program verifier for all languages. And because it's based on semantics, so it is sort of like correct by construction. So what else? Well, the issue is that K has a very large code base, right? It's over 550K lines of code. And at least 120K lines of them are directly related to symbol execution and formal verification. Of course, there are more things about non-symbol execution and front-end and others. So the motivation here is, can we at least do something to this large trust base, right? It's just too big to be in our trusted code base. Can we do something there? Our solution is to reduce K to something simple, a logic. And in particular, we use matching logic. So matching logic is this variant of first logic extended with fixed point and second order variables. It's very, very expressive. So you can express all these existing logics, calculate type systems, including K. All of them are definable as theories in matching logic. And what matters to this work is that matching logic has a very simple proof system. So here's the matching logic proof system. If you are not familiar with logic, don't worry, we'll not get into it. So what you see here are what we call the proof rules. And matching logic has only 15 this kind of proof rules. And what they do is they define this provability relation between axioms and the claim. So think of these axioms to be the programming language semantics you have. And the claim would be this, the spec of a program or this invariant property you want to prove. And this proof system is what we call a Hilbert-style proof system. And that means the proof has a very simple linear structure. It's just a list of formulas, one by one. And every formula is either an axiom, or it is the result of applying some of the rules to the previous things. So the conclusion of that is it is extremely easy and simple to check the correctness of such a proof. And the program that checks the proof is called a proof checker. And we implement the proof checker for matching logic in only 200 lines of code using this language called MetaMath. So the conclusion is matching logic is a very small, simple logic. It has a very simple proof system. So it has a very small trust base when it comes to proof checking. Okay? Now, how does it relate to K? Well, we can really think of K's deductive verifier as a matching logic proof searcher. So imagine this is a set of all matching logic formulas. Some formulas are programming language semantics, so they are axioms, they are assumed. And the claim I want to prove about my program is out there. So the question is there a proof using the proof system? So I'm trying to find such a proof. If I find it, this red line is going to be this proof certificate, and I can pass it to the checker. The checker will check the correctness of it. And how do I get to this red line? Well, I have the verifier. And the program verifier is kind of taking the bigger steps. Why? Because the verifier operates at a more higher level, more abstract level. So it takes these execution steps, but it can be regarded as a hint, a guidance. It is a proof searcher. It's the best effort heuristics to find such a proof. So I can really reproduce from the blue trace the red trace. And this part is called proof generation. We generate proof certificates to kind of fill in the gap between the execution steps of a verifier and the actual mathematical, logical proofs. So our main contribution is a set of proof generation procedures. So the first one is about symbol execution, and actually it all boils down to proving the correctness of one-step execution. So basically, if I have a semantic rule, left-hand side versus right-hand side, from that, I can prove this claim where I instantiate it with some substitution theta. And besides, I also need to prove transitivity, branching, case analysis, all these useful lemmas. The second one is what we call the pattern subsumption. So it's essentially implication between two formulas. So we've seen this example before. I end up with something like this after co-induction, and this is my original goal. So I need to do some sort of like pattern matching, and to realize that, oh, I just need to prove that these two expressions are the same. And finally, we need to do co-induction. So this is sort of the essence of formification. And for that, please read our paper for more details. Okay. All right, so let me show you the workflow. Okay, so the workflow is we start from the definition of a language, say imp, and we start from the invariant or the spec of a program we want to prove, and we run these proof generation procedures on top of it. Right? And the output is going to be this matching logic proof certificate, which includes all the detailed mathematical proof steps. And then we can pass it to the 200-line proof checker. And if a checker says yes, then we know that the claim is actually correct. And notice what's happening after we do this. So firstly, we remove the K verifier from the trust base. You no longer need to trust K anymore. And secondly, you don't need to trust these proof generation, you don't need to trust the proof generation procedures either. Why? Because all of them are just part of the proof search process, right? They're heuristics to find such a proof. What's important is I somehow get the proof certificate of my claim, and this certificate is correct. It's automatically checked by the checker. So that's all I need. My trust base is the checker. K and proof generation, they're just part of the heuristics. Okay, so I'd like to wrap up with some evaluation. So we did we had implementation, and we did some preliminary experiments on it. So the main takeaways are, one, our methods is language agnostic. So we tested on imperative functional assembly programming languages. So this is why, for each program, there are kind of like 3 versions of the same program there. And we achieve efficient proof checking for formification. So if you look at the last column, so this is the time in seconds that we need to check the proof certificate for formification. You can see that's mostly done in a few seconds. And what's interesting is that if we compare the time with the time that K uses to verify the program, you can see that sometimes it's actually faster. So it's actually more motivated to generate the proof certificate and to check it using the checker rather than run the verification algorithm again. Because one, it's faster. Two, it's actually, it has a smaller trust base. And 3, it's easier to do so because you don't need to set up the entire K pipeline to do that. You just need to set up this 200-line checker. Okay, so to conclude, our work brings more trustworthy formification in K. So in this sort of like a translation validation style. And what's interesting is that our work is language agnostic. So we are not specific to a particular programming language, but instead we are based on and opera semantics of the language, so it works for all programming languages. And by doing that, we reduce the trust base of formification in K from 120K lines to this 200-line checker. And by doing that, we also found bugs in the K framework, like missing axiom, etc. So overall, we make K more trustworthy. So that'll be the end of my talk, and I'm happy to take any questions from you. Thank you. Yes.
Hello, thanks for your very nice talk. Your slide, you do not show the size of the code because I see the specification. So I see the size of the proof.
Yes. So
but the code that you check. So where is the size of, for example, in number of lines? To have an idea.
You mean the size of the program?
Yeah, the size.
Oh, it's mostly here. So they're very, very simple programs, right? So for now
okay, because this is written spec, so it was not clear for me what
the
means
spec. Yeah, so the spec includes the program and also the property, right? So the program plus the property you are proving.
And are you not worried of the difference between the size of the initial program and the size of the proof?
The size
because these are megabytes, or?
Do you mean there are 2 numbers here?
So what are the size of the proof here?
Oh, it is the size of the output, the proof certificate that we are generated. So the first one is the one before proof compression, and the second one is after proof compression. I didn't talk about proof compression, But because proofs are encoded in this text-based format, so if you run just some compression algorithm on it, you can get very, very good improvement on that. But essentially, you can think of the size as this is the size of a proof, the mathematical proof. Right.
Okay.
So yeah. So if you write down mathematical proof one by one, so it's.
So these are in megabytes.
Yes.
Yeah.
Yes. So and this is encoded in this language called MetaMath. So it's a formal language that allows you to write abstract mathematics and proofs.
Okay. Yeah. And so what do you think of the size of the proof with respect to the size of the input program?
Yeah, the proof is huge, and the reason for that is the logic, right? The proof system is at a very low level. So we really reduce the execution of programs down to the basic level of logics, right? Okay. So somehow there is a balance between how if you have a very advanced proof system with many fancy features, of course you can have shorter proofs, but the proof checker will be more complicated. So what we want is, can we make the checker to be as small as possible? Right, and for that, the cost of that is the proofs are going to be slightly bigger.
Thanks.
Yeah, thank you for the question.
Let's maybe you can take your computer and we get the next speaker up, and then we can answer the next question. You want to ask the next question while we're setting up?
Thank you. You were speaking about the co-inductive step. Is that part of the case system, or that you need a co-inductive step, or is it in particular for this approach where you have got the proof certificates and you check the certificates?
So we need co-induction to do formal verification in general. What's interesting in our case is we have only one rule for co-induction. So it's a co-induction for all programming languages. So if you see classic approaches like for logic, if you have a while loop or if you have like a recursive function calls, the corresponding for proof rule is actually doing co-induction, but for that particular language construct. So what we have here is a very general rule called co-induction that can give you, complete formal verification for all languages. Yeah. But it's part of our framework, right? So the framework has this co-induction ability. All right. Thank you.
All right. Thank you. All right, our next talk will be complete first-order reasoning for properties of functional programs. It's by Aditi Murali, Lucas Pena, Ranjit Jala, and Moda Sudan.
Okay, hi everyone. I'm Aditya, and today I'll be talking to you about our work on complete first-order reasoning for properties of functional programs. This is joint work with Lucas Pena, Ranjit Jala at UCSD, and my advisor, Madhu Parthasarathy in Wirral at Illinois. Now, this work goes from practice to theory. In verification of functional programs, there's a popular heuristic employed by many tools like Liquid Haskell, Leon, or Stainless for Scala programs, Daphne, etc. We undertake a foundational study of this heuristic and develop a theoretical framework to understand its effectiveness. The heuristic that I'm talking about is essentially unfolding definitions followed by SMT solving. Let's call that USMT. For those of you who know, this refers to unfolding recursive definitions, treating them like uninterpreted functions, and calling an SMT solver. We'll see an example of this later in the talk. This heuristic is very effective in practice, and like I said, many tools use it. But weirdly enough, it also fails very easily, and in fact, on simple examples. For users, this can be a frustrating experience because they know that the theorem is true and they can prove it on paper, but the tool cannot. You can't generate counterexamples because there are no counterexamples. The theorem is actually valid. And if you try to look at the internal state of a prover, it's meaningless. In this work, we ask when the heuristic works, when it fails, and more importantly, what we can do to overcome the failures. And the answer, surprisingly, turns out to lie in the completeness of a certain first-order logic over ADTs and recursive definitions. Let's just look at an example. Here we have the algebraic data types of lists over integers. We also have programs, which we write as recursively defined functions. We have two functions. Insert front simply inserts the given key at the head of the list, so that's just a cons. Find is a recursively defined function that goes through the list and checks whether the given key is equal to any of the elements in the list. Now, we want to show that if you try to find a key after just inserting it, then the find function will return true. How do we prove this? Well, first we unfold the definitions on the given terms. So insert front of x comma k is equal to cons k comma x. Let's call that equation 1. And then we unfold the definition of find on cons kx. Let's call that equation 2. We now ask an SMT solver whether 1 and 2 conjunction imply the property phi. Note that this is a quantifier-free formula. And of course, in this case, this formula is actually true. The relevant bit is the disjunct marked in pink. This is an example where the USMT heuristic succeeds, and many proofs are of this kind in practice. But like I said, USMT also fails on very simple examples. Let's look at such an example. We still have the same problem as before, except now we want to insert at the back of the list instead of the front. So now we have a recursively defined function called insert back, and we want to prove as before that finding after insertion returns true. Now unfolding does not work here, no matter how many times you unfold. And to see why, think about unfolding the definition, let's say 3 times. You will only be able to know from the unfolding that the list obtained after insertion is equal to the original list in the first 3 elements. So for the 5-element list shown on the slide here, you can't actually conclude from just 3 unfoldings that the property that find will return true. This is the fundamental tension that we want to study. And so I'll give you an overview of our result. So verification conditions, or VCs, for functional programs are written in a first-order logic over algebraic data types. The model where you want to check the validity of the VCs is the standard model. So that's Zeus over there. This is the standard model. So the ADT sort here is realized by an initial algebra. The integer sort is the true integers, etc. And this logic is actually incomplete, which means no procedure can prove all valid theorems. In contrast, we can also consider the class of models obtained by axiomatizing each sort. So we have other people made in the image of Zeus. We can even give a complete axiomatization for each individual sort, like ADTs, sets, or integers, and consider the models of that combined axiomatization. The standard model is one such model, but there can be many other models that respect the axiomatization. And so in the context of lists, you can think of these other models as infinite lists for today. We'll see an example of this later. In the context of this picture, the key insight is that unfolding definitions and SMT solving are both sound for the axiomatized class of models, which means that any theorem that can be proven using the USMT heuristic is actually a theorem in this weaker class of models. More importantly, we show in this work that USMT is actually complete for the theory of axiomatized models. And this helps explain why the heuristic is so effective in practice, right? Because we have very good axiomatization for the individual theories, and most theorems that people want to prove actually do follow from these axioms. But our result also helps explain why, despite this effectiveness, USMT can also fail very easily. When a theorem has to be valid in the theory of the axiomatized models, it has to hold in every axiomatized model. But this need not be true. There can be a model whose individual sorts satisfy their respective axiomatizations, but in combination, the model falsifies the theorem. We call these rogue non-standard models. So that little devil fellow over there is preventing your theorem from being provable by this heuristic. Non-standard models are actually well known in logic literature, but these are usually models that are indistinguishable from the standard model using a formula. Individual sorts have such non-standard models, and they have complete axiomatization, so this is not a problem. But their combination allows for these rogue non-standard models to exist, which can in fact falsify a theorem that's actually true on the standard model. Furthermore, our result also helps explain the role of user help when USMT fails. The user provides help in the form of inductive lemmas to bridge the gap between axiomatized models and the standard model. And a useful lemma eliminates the rogue non-standard models, thereby helping prove the theorem. With this understanding, let's look at that failure example again. We know that no matter how many times you unfold, you can always find a bigger list on which USMT cannot show the property. We can in fact generalize this intuition into a rogue non-standard model containing an infinite list. So let's just look at this infinite list 1, 2, 3, and so on. And infinite lists are actually a legitimate model of the ADTs. Do check out the paper for the detailed explanation of why that's the case. But let's just take that for a fact. And in this model, insert back can actually be interpreted in a way such that it just loses the key. It keeps recursing down the list, and then in the end, it just returns the original list. So it basically behaves like identity. And then find only returns a key if it was already there in the original list. In this model, think about inserting the key 0 into the infinite list shown here. Insert back will just lose the 0, and find will just return false. So this property does not hold. And this kind of model is why your USMT heuristic cannot prove this property. The way to overcome this failure is to actually prove the property by induction. So you assume it for tail of x, and then you show it for x. And more generally, you assume a helper lemma, you show that lemma by induction, and then use that lemma to prove the theorem. And such lemmas rule out these non-standard models. This is the formal statement of our completeness theorem. I've shown the pseudocode of the USMT algorithm on the right, where the indefinite unfolding of definitions is the 2 lines in pink. We denote the theory of the axiomatized models by T-comb for combined theories. We write the defined functions as defs, the quantifier free property we want to prove as phi, and then the VC can be seen as checking the validity of the formula defs implies phi. We show that if this USMT algorithm returns valid, then defs implies phi is actually a theorem in the combined theories. And this is the insight that we saw earlier, that it's sound only for this weaker class of models. More importantly, if defs implies phi is indeed a valid theorem in the combined theories, then USMT will eventually prove the theorem valid. And this shows that USMT can prove precisely all the theorems in T-comb. Our theorem requires that the definitions be provably acyclic. This is actually a generalization of termination, and it essentially says that you have to prove the recursive definitions terminating using ranking functions. Every tool we know of proves programs terminating in this case, in this way, so this requirement is actually satisfied in practice. And in fact, if you look at proofs of termination in very many tools using ranking functions, you will notice that they are first-order proofs, because you can't express well-foundedness in first-order logic. That is only in the mind of the user, and you know that the standard model is well-founded. So acyclicity actually captures precisely how tools know that a certain definition is well-formed. And so a really primordial notion of well-definedness emerges from our result. Identifying this precise fragment is actually one of the main contributions of our paper, because finding such something that helps explain practice and also covers all the examples in practice took us over a year. I'll give you a glimpse of the proof. It's essentially a model construction argument. So what happens is that when unfolding fails, you have instantiated recursive definitions on a downward closed region. So in the case of our list example, this would be x, tail of x, tail of x, etc. And when unfolding fails, we have to construct a rogue non-standard model where the definitions are satisfied everywhere, right? So you've instantiated such that the definitions are satisfied on this downward closed part, which we call a computational closure. And then you want to make sure that definitions are satisfied everywhere so you can produce a real non-standard model. The key insight is that definitions can be extended beyond computational closures for these kind of well-formed computationally closed sets. And this model construction is actually fairly complex. I encourage you to check out the paper. But the basic intuition, you can think of this as this iceberg picture over here. And so that's it. We have finished our quest for a foundation for the USMT heuristic using our completeness theorem. USMT works precisely when the given theorem is valid under the combined theories and fails otherwise. And this means every failure is exactly because of a rogue non-standard model. This is actually an incredibly hard problem, right? It's incomplete, and so people, when they design heuristics, they know they can't prove everything. They're not thinking about completeness, but we find, surprisingly, that this heuristic is in fact complete, not for the real logic, but for a reasonable abstraction of it. And of course, the way to fix failures is to do inductive lemmas, which eliminate the rogue non-standard models. Now, I've been telling you this whole time that USMT is used by many tools for verifying functional programs. So let's actually look at some of these tools with the lens of our new understanding. First, we look at Liquid Haskell. Liquid Haskell has a strategy called proof by logical evaluation, or PLE. It's essentially unfolding, but it just unfolds the definition once. It's in fact a little weaker than that. This is already very effective for the class of examples that Liquid Haskell covers. And so, using our theory, we know that the gap can either come from insufficient unfoldings or from the gap between the axiomatized class of models and the standard model. We actually investigate the benchmarks in Liquid Haskell. Ranjit, who's a collaborator on this project, helped us look at these benchmarks, and we actually find that most examples, the PLE heuristic fails, not because of insufficient unfoldings, but in fact because of the gap. And we in fact visualize some of these non-standard models, the rogue non-standard models in the paper. And of course, users use inductive lemmas to overcome failures. We also look at Leon or Stainless, which does Scala programs. There, this tool unfolds definitions indefinitely, and in fact, it asserts the contract on all recursive calls. This is in fact not the heuristic that I showed you, because you can also claim that the property is true for all smaller lists and then try to prove the property rather than just using the definition. This is a slightly more powerful heuristic, but we show in our paper that it can in fact be modeled using USMT. We show an encoding that basically reduces this to the USMT algorithm that we saw in the earlier slides. And therefore, our completeness theorem applies to tools like Leon or Stainless as well. And again, users provide inductive lemmas or induction principles to overcome failures. Now, the impact of our theory for tools like this is twofold. One, tool designers can now know that the instantiation strategy that they are using is actually complete in its horizon, which means you don't need to worry about instantiating other terms, and users can in fact be made aware of this fact. And you can design tools using complete instantiation techniques that are also thrifty in this way. Secondly, we can also give user feedback using these rogue non-standard models, helping the user understand why their heuristic has failed and helping them identify the kind of lemma that would be needed to overcome these problems. We have many more details in the paper. We actually provide a walkthrough of the full verification experience in Liquid Haskell and Leon. We visualize these cursed rogue non-standard models, and we show some impossibility theorems that tell you why it's going to be hard to generalize our result. So, in summary, I have told you about a heuristic called USMT for verifying functional programs over the domain of algebraic data types and other background theories. This USMT is FO complete with respect to the axiomatizations of these sorts. The gap, therefore, in this heuristic is in precisely the gap between the standard model versus the axiomatized models. And lemmas then serve to eliminate these rogue non-standard models. This is, in fact, one of two results that we now know of this form. Earlier work by members of our team have actually shown this for the imperative program world, where the objects are in fact dynamic heaps rather than algebraic data types. And there, the appropriate form of USMT is FO complete. And the gap there is actually the gap between first-order logic with least fixed point, the recursion, and first-order logic. And there too, lemmas eliminate such rogue non-standard models. That's it. I'm actually on the job market, and my work identifies these creativity gaps in reasoning using logic learning. These are, in fact, creativity gaps because the tools are fundamentally limited in this way, and you do need human ingenuity to come up with these lemmas. Well, you need human ingenuity so far. Last year at UPSLA, we have some work on the imperative program side where we synthesize lemmas using some of these rogue non-standard models, and we would like to carry this on for the functional world as well in future work. Thank you.
Great, thank you. We have time for a couple of questions. So I have a question while other people are thinking of theirs. Why is an infinite list a valid model, even though it's a rogue one?
Oh, great. So let's take your favorite axiomatization of algebraic data types. So this is a first order theory, right? So what you need is that if you destruct cons, then you get unique things. If you construct using unique things, you get a unique element. And you also want some kind of acyclicity, right? Which is that if you destruct finitely many times, for arbitrarily finitely many times, you can't get back the original element. All of this is true for infinite lists. If you take an infinite list and tack on another number, you do get a unique infinite list. If you destruct an infinite list finitely many times, you don't get back the same list. You get a kind of finite index from it. And you also, when you destruct a list, you get two unique sublists, a number and a sublist. So all your favorite axioms are actually true for infinite lists as well. And that's why it's a valid model of the ADTs.
I see. It's because there's no axiom that prevents it from being infinite, basically.
Yeah, exactly.
Okay.
No junk is actually expressed by saying that you have some axioms and it's the least model satisfying these axioms. But a first order theory can't do this.
Got it. Thanks. Do you have a question?
Talk. Thanks. So you motivated your talk by saying you were going from practice to theory. Let me try to push you back to practice, right? And yeah, you mentioned that towards the end of your talk too. How would you present these So first, can you, how did you present these rogue non-standard models to users? And you were alluding to using those to actually find out what inductive lemmas need to be proved. But I would assume that undecidability would still play some role in the discovery of lemmas. So
you mean incompleteness?
Yes.
Right. Okay.
So, what's the boundary?
Okay. Yeah. So I'm going to explain. I'm going to answer your questions in order, right? So firstly, you asked how are you going to show these non-standard models to the user? Well, the cleanest answer is future work. But a better answer is that there is actually some work on visualizing a certain class of rogue non-standard models that you can, in fact, visualize in a cyclic way, right? So in this infinite list, 1, 2, 3, so on, I actually didn't need to give you a list of the natural numbers. I could have just given 1, 2, 3, 1, 2, 3, 1, 2, 3. And this is now a finitary object. And you can depict cycles, and you have to, of course, make sure that it respects the axioms of the ADT and so on. But there is some work, I think, maybe in the separation logic world or something like that, in kind of finding these kinds of models. And they use finite model finders to find such models. Now, whether these models are going to be intuitive for the users is another question, right? And so that's something that we have to work on in terms of actually surfacing these models. Now, in terms of lemma synthesis, because it's incomplete, any algorithm is going to fail eventually. And so lemma synthesis cannot also cover everything. In the work in which we did in the imperative world, we have a particular form of induction templates. And we do grammar-based synthesis. But even if you didn't do this, we have a particular template of induction using which we say, this is the kind of lemma we want. And there aren't finitely many induction templates for first-order logic with recursive definitions. Proofs, you can prove something in any crazy way you want. And so, yeah, the way in which we automate lemma synthesis is by looking at certain kinds of proofs. And that's one way in which incompleteness can manifest. Yeah.
All right, thank you very much. All right, so the next talk is by Ortamir, and it's on counterexample-driven quantifier instantiations with applications to distributed protocols.
Oh, glad you said that. That was long. Okay, so it's a joint work by my colleagues, Marcelo Taub, Ken McMillan, Sharon Shoam, Guy Guetta, John Owell, and Molly Sagiv. Okay, so let's start. So why did we choose distributed protocols? Basically because they're everywhere, and we like things that are everywhere. And because the academia can't really find a good way to verify it by papers. So some quick examples, code, if you're familiar. And then we found it's not really correct. Ziziva, best paper, something that should be correct. And not really. So it's a real problem, okay? These are smart people. They're not like PhD candidates, okay? They're really smart, and they got it wrong. So we need something better. And currently, our tools we're talking about Isabel or Cork or Iron Fleet, they really it takes a really long time to prove something, okay? So, and I'm not talking even about the butterfly effects that you have here in Daphne. Okay, so what do we want? What is our goal? Okay, so we want this validation system. We get a system S, a property phi, and we either get a counterexample or we get a proof. Okay, but the problem is that Rice did his thing, and we sometimes don't know. And that's a problem. So what we do before that, we use inductive invariance. This is a standard notion of inductive invariance. I'm not going really to go into that. Just saying that the inductive invariant covers all the reachable states, and it's closed under transition. And it can't reach a bad state, which is what we want, that everything is safe and good. Okay, so we're getting there. We have in the middle these three formulas that you can see. All these three formulas just satisfying the requirements that I showed earlier. Okay? But, and here's a confession here, because I know it's unpopular to say, but I really like decidable logic. Okay? So I know there are other opinions here, but here's what I say. And hopefully you'll be in this opinion once I'll finish the talk. So the problem here with undecidable fragments is that you get this quantifier alternation, okay? This nasty for all exist, okay? They're everywhere. They come from functions. They come because you're building your logic. And the problem is that once a circle comes out, the solver can make an infinite number of instantiations, and it diverges at some points. Okay. So this is our elephant in the room, okay? This quantifier alternations. So what did we do in this decidable logic before? We said, well, maybe we're not smart enough. Maybe we can write our model in a way that this circle doesn't exist. And sometimes you can, okay? And we also tried modularity. We broke the system to several pieces. And then, hopefully, every piece is in a decidable fragment, and then you're good, okay? But sometimes it's not enough. And what we're showing in this work that we're adding relational abstraction, and in the case that it doesn't help, we need some manual instantiations. Okay, so I'll walk through at least 2 examples so you can see what I'm talking about. So say we have this n participants, and we want to decide a value, okay? And we're sending values from one to another. And we can send the value that we got. We can send our initial value. And if there is a quorum of voted value, then we are saying that this value is decided. Okay? A really simple consensus algorithm, but not that simple, apparently. Okay. We would like to, of course, prove that only one value is decided. Okay, so even in this simple protocol, we have this notion of quorums. And quorums, by themselves, you need cardinality. You need stuff that takes you away from your decidable fragment. Okay? So what do? We axiomatize things in first-order logic. Okay? So instead of saying that we need a quorum to be more than half, we're saying that every 2 quorums intersect. Okay? And that's enough, apparently. So this is how you write it in Ivy, but what you need to know is this, that we have this property that at the end ensures us that every 2 quorums intersect. Okay. And we're keeping away all this arithmetic and cardinality away. Okay, so here's our initial state. No one is voted to anything, and no one decided anything. And we have this property, and a node can cast a vote, okay? Very trivial so far. And a vote is decided if there is a supporting quorum, okay? And this is our safety property. Okay, so here I'm going to supply the inductive invariant, which is fairly simple. We have the safety property, of course. We have that we can't decide the non-value, this one. And we have that every decided value is supported by a quorum of nodes. Okay. So we're starting the verification process, and what we see is that we're getting an edge because there is a vote function for the node, from the node type to the value type. Then we're getting another green edge from the value type to the set type because of this for all exist here. And lastly, we're getting another edge here from this for all exist. And that's a problem because we are no longer in a decidable fragment. Okay. So what do? Abstracting. Okay. We're taking a function. For instance, this for all exists, the property that I just showed you. Okay. And we are making it a relation. Okay. R intersection. Okay. And I'll show you how it's done. And this function comes out of columnization. And we're doing the abstraction to a relation. Here you see it's no longer a function. And now in the decide function, when the decide action, when we're trying to verify it, we see that things broke. And the problem is that we forgot that this function is total. Okay, so now we get something that is really bizarre. We get an empty quorum, a quorum that has no nodes in it. And apparently, this quorum can support any decision, because every node in it voted to any value that we want, because no node is in this quorum. Okay. So this is why we need instantiations. Okay, so what we need is a specific node, okay, in our proof to show that the previous example cannot happen. It's not real. So this is how we do it, okay, at least on the slides. We're starting with a violated safety, assuming that we have two values that were decided are not the same. And then we're working with the proof of the solver. And we see that the solvers commonize this function, okay? The property that we have a supporting quorum for every decided value, okay? Then we would like to say, all right, intersect these two quorums, okay? Because we know that every two quorums intersect. The solver doesn't know, but we do, okay? So we then instantiate our total axiom here on these two quorums. And we're getting another node, N0, that belongs to these two quorums. And by that, we're getting our contradiction because this node voted to two different values. Okay? Okay, so here lots of data, but what I want to focus on is these two columns. We tried our technique on many protocols. Some of them, the PBFT variants, went extracted into C++ code. And what I wanted to show that we don't really need lots of instantiations. Okay? Most of our inductive checks run without anything. They're just passing through, and the solver is doing all the proof work for us. So that's good news, at least we think that. And I would like to conclude. So our approach is predictable. We don't have any butterfly effects. Okay? And once you proved something, it stays proved. And it's sound, which is important. And another surprise is that actually first-order logic complete. So anything that you can prove in first-order logic, we can prove by adding more and more instantiations if needed. And the last, which I don't think it's a word yet, but it should be, progressibility. This means that the user can always take a step forward to complete the proof. Previous techniques didn't know why. If you can't break the module to your model to separate modules, then what should you do? Try harder? Maybe. If you can't rewrite, what you're left with, I don't know. Maybe you're not smart enough, but you have no solution. Here you can always take a step forward to complete the proof. And you guarantee that if you can prove it in first-order logic, you'll be able to do it here too. All right. So on this graph of automation versus expressiveness, we are somewhere here. We are less expressive than proof assistance, but we are far more automated. And we need less proof lines to the same extracted code. Okay, so this is what I have for you for today.
Excellent, thank you. Are there any questions? We have time for a couple, I think.
Hi. Very interesting that you're kind of reducing the burden of kind of infinite quantified instantiation by guiding it using counterexamples. I was very interested in the completeness. How does it manifest in the presence of theories?
So we didn't prove that it's complete with theories, but I can tell you that we did interact with theories in our proof because you need it. You need it. Sometimes you need array theory. Sometimes you need other stuff. But if your theory is encoded in first-order logic, you still get your completeness.
But then your instantiation might blow up, right? Even the counterexample guided one, because see, if I just needed 14,000 something, right? Instantiation may not find it, but
yeah, so
maybe just solving it or using some decision procedure. So is that something that is possible? Completeness in the presence of interfacing with the SMT or something?
So I can tell you, for instance, we did an example with when you take an array and you shift it, okay? And and it's not bounded by how many, and we did manage to prove it with instantiation. You did need more invariants, okay? And that's true. It's not. It wasn't easy work, but it was done.
I see. Okay.
Yeah, I can show you that offline.
Cool. Thank you.
Okay, maybe let's change over. I have one more question, maybe what you can answer as we switch over.
Yeah.
So I was thinking a little bit about like the user perspective on this methodology, right?
Yeah.
As a user, are there guidelines that can help you tell, which instantiation you need to do next, or if you're maybe bumping up a more fundamental issue like your formulation is incomplete, or you're going past FOL?
Yeah, so what you can do usually, and I did not talk about it, but we're using finite model checker to check your FOL formulation is correct, your inductive invariant is correct. So if you're in this point that you know that your invariant is indeed inductive, or if you suspect it's inductive, okay, then your counterexamples are always because you forgot about some totality axiom, okay? So at least that.
Okay.
Okay. So it's something that you get a feeling when you're seeing lots of counterexamples, and usually you just see it and you know what's missing. You're like, this bogus element is missing.
Right.
Yeah.
All right. Thank you. Let's thank the speaker again. All right, the next talk will be a conceptual framework for safe object initialization by Clément Blaudot and Fenyang Liu. Clément?
All right, thank you. Thank you all for being here. So my name is Clément Blaudot. I'm a third-year PhD student at INRIA, and I'm going to present a work we did with Feng Nguyen while we were at EPFL. So the goal of this work is to provide you with a conceptual framework. So I'm going to detail a bit what this means for safe object initializations. So what's the deal with object initialization? Let's look at a couple of examples. Let's say you're tempted to write this kind of code where you have several fields, and the examples will be given in Scala throughout the presentation. And here you try to access a field before it's initialized. So you get an initialization error. You have a field access that's too early, basically. Another variant of that error is to try to call a method on the object, on the this object, before the object is initialized. And again, you reach the field before it's initialized through a method called. And so you have a method code that's too early. And another way of having the same kind of issues is that if you build your object and inside the constructor of your object, you pass the this pointer to another object. And so the B class here expects an A object, so it tries to access a field of A, and there is an initialization error. And the third one is more worrying because it means that the error can appear anywhere in the program. Actually, the core problem of initialization is that objects under initialization that do not fulfill their class specification yet. And so this is a big deal because it means that when you have objects that are not fully initialized, they break the core assumption of object-oriented programming that objects that do fulfill a class specification. It's not the case. Okay, so you may be tempted to say, okay, let's forbid all of this crazy code inside the constructor. But the thing is, there are examples where you actually want complex initializations, where you're happy to be able to have escaping of the this pointer before the end of the initialization, so you can have cyclic structures. And here you can verify that there is no early access in this code. Another example is maybe if the initialization process is very long, you have like some server and the initialization process takes a long time, and you want to emit some effects before the end of initialization. And maybe that's safe to do so if you can start broadcasting even if the rest of the server is not ready or something. Okay, so here we have kind of the examples of things can go wrong and things can go right, and how can we find a sweet spot in between. So we have a design space. Okay, we want to prevent all initialization errors. Okay, so we want a sound system in which it's impossible to access a field before it's initialized. But this is kind of a large design space. It goes from very strict initialization, where you're not allowed to use the this pointer before the end of the constructor, like you have in the OCaml objects, for example, all the way to like full separation logic proof of program, where you're allowed to do anything. Inside this design space, we're interested in having an expressive system in which you're allowed to do some form of controlled escaping to build up those cyclic structures. But at the same time, we want a system that's modular, which means that we want a class-by-class analysis, and if possible, we want a limited footprint, which means that if the code does not do crazy initialization stuff, the initialization checks should not invade like all of the rest of the code. It should be of limited footprint. And so the last thing we want in the design space, design requirements for a system, is for it to be usable, which means that it should be understandable by the user and, if possible, inferred in most common use cases. So that's where we believe that Celsius stands, some sweet spot inside this design space. And that's what I'm going to present now. So in this presentation, I'm going to give you an overview of the Celsius model, so how we represent object under initialization. And then I'm going to present the core principles, the main idea behind the design choices of Celsius. And those core principles are like high-level design ideas that you can apply to your language in very different ways. And I'm going to illustrate one way of applying it to a minimal calculus that we give in the paper to show that actually it works to have those principles. And if you follow the principles, you'll be rewarded by the local reasoning, which is kind of the core idea of the core property of a system for safe initialization that I'm going to give you an overview of. In the paper, you'll find the actual calculus that illustrates those properties, the typing system with temperature annotations that you have for your that we have for the minimal calculus, and then a soundness proof that is very modular because it only relies on the principles in a way. And also everything is implemented in Scala, so Scala is way bigger than the minimal calculus, but the ideas are kind of the same, and everything is proven in Coq. Okay, so let's jump in the Celsius model. So how do we model object under initialization? So the idea is that when you start at the beginning of the constructor, the object has no initialized fields. Okay, so we consider it cold. A cold object, you cannot access any of the field of a cold object because they might not be initialized. And then throughout the constructor, some field will get initialized and the object will get cool. Once you've reached the end of the constructor, hopefully you've initialized all the fields and you get a warm object. And the thing is, a warm object is not ready yet. It does not fulfill its class specification yet because it might still have inside one of its fields a cold object. So using a warm object might still be unsafe because you might still transitively access an uninitialized field. So initialization is really finished when you have hot object and you can only reach transitively objects that are freely initialized. Okay, so that's it for the Celsius model. Now let's talk a bit about the core principles that support the Celsius model. And again, those are design principles, and you can apply them in many ways to your language. The first principle is monotonicity. We believe that that's a good idea when you have evolving states that they evolve in a monotonic way. So the initialization states should also be like the arrow of time, in a way. You can enforce several granularity of monotonicity. One is partial monotonicity, when you disallow the uninitialization of fields. But for soundness, we need a stronger notion which is called perfect monotonicity. Because if you disallow the uninitialization, it will prevent warm object from getting cooler, but you can still have an hot object that gets warm because you put a cold object inside one of its fields without deinitializing it. And in the calculus, we implemented monotonicity with language design. We don't have a way of deinitializing a field, so we don't have like null values, those kind of things. And we also have a typing restriction that you can only update fields with hot values. But again, you can enforce the principles in many ways. The second principle, which is very linked to the notion of monotonicity, is called authority. If you have two aliases of the same object and you do an update on one of the alias, you can maybe consider it to be hot at some point. But the local visions you have of the initialization state might differ between the different aliases. So you might do something on one of the alias that is locally monotonic, but actually globally is not. So if you do some update on the second object, and that downgrades the first. So in the presence of aliasing, to ensure monotonicity, you need this notion of authority, which means that state updates are only authorized on a distinguished alias. And a natural candidate for this distinguished alias is the this pointer, which is like a natural candidate for between all of the aliases of the object. In practice, in the minimal calculus, we only authorize the typed updates, so the object getting hotter inside the constructor. And we distinguish between first assignment, so when a field changes from uninitialized to initialized, and updates of a field. Okay, so now we know, thanks to the first two principles, that objects get hotter over time. But how do we know that they reach warm at some point, that we finish the initialization of the fields? The principle of stackability, and it states that all fields must be initialized at the end of the constructor. The intuition behind the word stackability is that the constructors, they form a cold stack. There are different ways, again, of enforcing this principle. In minimal calculus and in Scala, we have mandatory field initializers, and we do not have control effects in the constructor, so there's no way of like throwing an exception and not finishing the code of the constructor, which could like break the stackability principle. Okay, if we combine the first three principles, let's look at, so the question is, how do we get from warm to hot object? And if we combine the first three principles, let's say we have some hot object and we create a new one that starts cold, and the creation of that object might trigger the creation of other objects, and so we have the object going from cold to cool, and you may have cycles, and at some point the initialization of C3 finishes, so you get a warm object. And the initialization of C2 finishes also, so you get, again, a warm object. And then you know that you only have warm object in your heap, so you know that you can only transitively reach things that are fully initialized, so you can upgrade all of the objects from warm to hot. But what happens if inside the heap, there are also other objects that are unreachable and that are cold? Like what happens if you have parallel initialization or if you have nested initialization processes? In those cases, you will not be able to upgrade a set of objects from warm to hot if you don't know that they are actually in a restricted part of the heap. So the principle of stackability states that basically you should control the accessible part of the heap to show that in this accessible part of the heap, there are only warm objects. So the principle of scopability, access to object under initialization must go through controlled channels. In the calculus, we remove global variables because if you have like cold objects that are globally available, you never know that the object you're building will ever reach the hot status. But this was covered by my co-author in the paper published at Uppsala this year and presented this morning. And also we have like in our setting we over-approximate the set of the heap that's accessible basically. Okay, so that's all the 4 principles, and if you manage to have all of those principles in your language, then you will get the local reasoning property, which is like kind of the core property behind our approach. And the idea is that if you execute an expression or a program inside a hot environment, so it only accesses a hot object, you will, the result you will get will also be a hot object. Why is it the case? I'll show like an overview of the proof because it shows how the principles appear. The idea is that after the execution, you have a resulting heap, and you have the object that was produced. And if you try to access an object from the object that was produced, it's either a new object. So if it's a new object, it means that we run its constructor, and the constructor finished, so it's a warm object. And if it's a old object, it was already accessible in the heap from the execution environment before. And before the execution, it was hot, because the execution environment was hot. And thanks to, let's advance a bit. So the old object was already accessible by the scopability principle. And as it was hot before the execution, it remained hot thanks to monotonicity and authority. So in both cases, you can only access warm or hot objects, so it means that actually you can only access things that are fully initialized. So the object you get is fully initialized. And this gives rise to a typing system where you have hot bypasses, meaning that when you know the piece of code you're considering is not doing crazy initialization stuff because it's only in a fully initialized context, you can ignore these initialization checks when you handle like hot objects. So let's quickly take a look at how it applies in a like modified Scala with temperature annotations, which is the minimal calculus, basically. So I revisit the example before, and I add annotations to all the types in the fields of the objects. And you can check that basically you have like the obligations, and you never access an object that if you don't have the corresponding temperature. And the thing is that if you have another part of the program that does not do crazy initialization where you need to finally check that all the fields are well defined, like for example in the main class, you know that the initialization starts in a hot environment, an empty environment, so it's hot. And you know that at the end you get a hot object. So in the rest of the program here, you can completely ignore initialization checks. So that's really the beauty of the local reasoning principle. So it does not like pollute the whole of the program. When you handle hot objects, you can just ignore the initializations. Okay, so what's the takeaway? So I gave you kind of a conceptual framework for self-initialization, meaning that it's a simple interface to a solve problem. You can think of the initialization problem in terms of the 4 principles, and that gives you a good overview of what's going on. You have the Celsius model for initialization of objects. You have the 4 language agnostic principles that you can, again, enforce in many ways, and the core idea of local reasoning. And I invite you to see the paper for the precise definitions, the typing system, the soundness proof, which again is modular in the sense of the principles. It's quite interesting. And some hints on the Scala implementation. Thank you very much for your attention.
All right, great. Do we have some questions? I'll start with one while people are coming up. Is this shipping with a Scala compiler? Is there conversations about like putting it into practice?
That's a very good question. It's actually right now in the Scala free compiler. You have a compiler option to activate the initialization check. Same as for the work on global objects. You have an initialization check. And the implementation like kind of follows the principle, but the language is way more complex. So there are a lot of other things in the actual implementation. But yeah, it's currently in Scala.
Yeah, excellent.
I'm not quite sure if I got completely the way it's working. What's about the constructors? So as long as the constructor is not completed, you may still have critical initialization steps going on. In the examples you showed the direct initializations of variables, so I'm not quite sure how the effect of constructors is modeled in there.
So let's go back to this example in the Celsius syntax. So the way we model this problem, and it's the same in Scala, we have mandatory field initializer. So the constructor, you should think of it as like the list of those expressions on the right that are the basic initialization for those fields. But you can also have like a normal constructor, which is a function, and it can do anything. And then we said that you should prove in some way to have the stackability principle that at the end of the constructor or at the end of the initialization process, you have initialized all the fields. Does that answer your question?
Yeah, okay, then I think I get it. Yeah.
Sorry, so the design aspect here is that we have a basic initialization value for all the fields. So we know at least that there is something inside all the fields at the end of the initialization.
And then maybe a comment more. These terms, hot, cold, cool, confuse me a bit because hot is dangerous, soft, whereas cool is, let's say, stable, safe. Yeah? So it's counterintuitive in that context for me. Did you pick them from somewhere else? Did they exist already, or was it your?
It's more of a cooking idea. So you cook the object, and at some points it's fully cooked and it's ready to heat. But actually, we discovered like yesterday that it's also a terminology that is used in some distributed systems, like when you have like a VM that starts and it's not ready yet, it's cold, and it like ramp up to being hot and usable. So it is accidentally a terminology that is used elsewhere, but yeah, the intuition more comes from like a cooking.
Thanks.
Thank you.
All right, one more question. Yes.
I have one question. So, am I correct that, like, if you don't consider the mutually recursive initialization, then you can just topologically sort and then initialize from the left, and the problem becomes easy. But in the actual Discord, there is a mutually recursive initialization going on, and the type system you have devised is basically ruling out like the cycles, like the meaningful cycles that actually access the field of the object. But the type system you devised ensures that such a cycle doesn't happen. Is my understanding correct?
So you can have cycles, like you can realias the object that the this pointer, for example.
Okay.
But there are some patterns that you cannot do with this system, definitely. But like basic cycles where you do an alias of yourself or those kind of the patterns are allowed. But you cannot access a field of yourself while you're initializing.
Yeah, thank you.
Thank you.
Thank you. So you told us about this problem of initialization in the context of Scala and objects. Are there other languages or language features where a similar problem would show up?
So that's a very good question, and actually it's kind of ongoing research, just started. But yeah, the module system of OCaml has recursive modules, and they have an initialization phase that is not well documented and also kind of broken. There are like dynamic checks and everything, and we would like to apply this approach to this system. So definitely, I think there are more languages that could benefit from this approach. Thank you.
All right, thank you so much.
Thank you.
Okay, welcome everybody. We are going to have the second session on distribution and networking. And we are going to start with the talk by Lorenzo Guerri, and collaboration with Nobuko Yoshida, I guess, on hybrid multi-party session types. Floor is yours.
Hi, thank you for having me. So I present today my work on hybrid multi-party session types, co-authored with Nobuko, and I'm Lorenzo, yes. So multi-party session types were introduced in 2008, and among the many features and nice things in the paper gives us global types. Global types allow for the formal specification of safe communication protocols. Disclaimer now, safe is my way, I use safe loosely, and it's my way to say, in short, something that carries good semantic properties. So with global types, I can specify communication protocols that are safe and with multiple participants that communicate with each other distributedly. In this work, what our contribution is achieving distributed protocol specification. Namely, we add modularity to the formal design phase in multi-party session types. Now, multi-party session types, a brief introduction. Let's say we have this system with 3 participants, P, Q, and R. And the intended behavior is that P sends a message M1 to Q, Q sends a message M2 to R, and R sends a message M3 to P. Now, on the right-hand side, you see written in the syntax of local types, you see the implementation for each participant, which is distributed. So this implementation, for example, for P, P receives, question mark is received, exclamation mark is sent. So if, for example, for P here, the implementation would be that first P receives a message M3 from R, and then it sends to Q a message M1. Analogous for the other, as you probably have spotted, this system is deadlocked. So if the distributed implementation is like this, every participant has a receive action as the first one, they all wait to receive something, no one sends, and the execution is stuck. Then, of course, here we can do just checking the things. We can just swap the constructs in the first implementation so that P first sends to Q and then receives from R. And the execution goes well. Everything is fine. Formally, the top-down approach of multi-party session types gives a way to specify a way to have this safe code by having a designer who specify a global type for the whole system. And as you can see at the bottom of the slide, there's this object called G, which is a global type that gives the full discipline of the system. So first there's a message from P to Q, M1, and then a message from Q to R, and then a message from R to P. It's like a scheduling. Now, so there is one designer specifying this protocol. The protocol is projected into the local types that you see that for each participant. Here I show in the slides, you can see the full syntax of global and local types. So in the previous slide, I presented the global message, so the arrow construct from P to Q, and the send, exclamation mark, and receive question mark for local types instead. Both syntaxes have the expressiveness of recursion and branching. With the syntaxes, again, here you have at a glance the top-down approach. With the syntaxes, a designer specifies the global type that is then projected onto local types, and processes can be type-checked against the local types. That on the right-hand side of the slide, I have an example on how good semantics properties are proven in literature. For example, now we pick label transition semantics, and the traces are equal for global and local types if the collection of local types is obtained by projection from G. So projection preserves semantics. In the rest of this talk, the main concept is global types. So what is specified with a protocol is safe. And I will indicate this safety with boxes as in the drawing there. Now, what's the good of multi-participation type? This safe design, so a formal design that guarantees safety. What is the bad? That the design is centralized. We are dealing with distributed systems, but if we admit, of course, distributed implementation, but not distributed design. And this work overcomes this limitation. The motivation is quite simple. When we deal with larger scale systems, there are many participants involved, and they exchange many messages among each other, and ideally they are specified in terms of components. So there will be more than one designer. Core idea behind this work is to have hybrid syntax, that's why hybrid types, that puts together the global and the local constructs. The global messages, this is important because I know it generates confusion, but the global messages are for internal communication, for intra-component communication. The intuition behind this might be that, for me, is that the designer has full control on the message, namely both participants are in each component. While if the designer needs to send or receive some message from a different component, then well, it will use a local construct, namely a send or a receive. So I'll start describing an example of a company. A company with 3 departments, each department has a designer, and the designer specifies the communication of its component, of its department, with a hybrid type. In this case, we have the strategy department of a company, where D, the participant director, sends a product internally to ad, which is the participant responsible for advertisement. Now, the director decides on the product, so not only it sends it internally to ad, but to other components of the company, or more precisely, to other participants in other components of the company. In particular, D sends the product to S in the sales department and to F1 in the finance department. The price, so the advertisement, responsible for advertisement ads, needs to publish the ad and needs to know the price. The price will be decided, however, in the finance department and sent to ad by F2. This is instead the point of view of the sales department, where we have the participant S that sent the product. After receiving the product from D, it sends the products to W, which is the responsible for the website where the product is actually sold. Again, W needs to receive also the price from the finance department F2. And now the final specification of the component of the finance department. So first, as you can see also in the type on the right, F1 receives the product from D externally, sends an internal message from F1 to F2, so the product is communicated from F1 to F2. F2 will decide on the price and communicate it externally with a send to ad and then to W. So this is how the system looks like at a glance. And I said before that safety is guaranteed by boxes in this talk. So we have 3 boxes that are not sufficient for the whole system, but they somehow certify the internal messages. So the intra-component messages, the internal messages of each component. Now, what about the inter-component messages? They are not boxed. So we take a different point of view. We forgot about what we have already verified. We forgot about the components, and we box them. So we give a specification for safety only on for the inter-component messages. And this we give as a hybrid type or as a global type, so hybrid type with only global constructs, for compatibility. So we have one specification, separate specification for each component, and then we need an additional one, so n+1, for compatibility. Now, we have boxed the internal messages. We have boxed the inter-component messages. Our result is that this works. This can be composed, this specification, this modular specification can be composed in a global type for the whole system. So the whole system, the communication for the whole system is safe. This is our development at a glance. In particular, there is one novel notion that we had to introduce, which is compatibility. And the compatibility, once specified every component and the compatibility type, we check compatibility of each component against the compatibility type. So this is based on projection, and actually we had to extend projection so that we can project the compatibility type onto a set of participants, not only onto a single participant. This must be equal to the localizer of the component. What does it mean? That the localizer is the dual of projection. It's not true, but the intuition can be that. So the localizer preserves only the external construct of the type of such component. With this, as said, we prove compositionality, so we can compose and obtain a global type for the whole system, and we are safe now. Now, for applicability, there's one more thing we want, and we prove this too, that projection is preserved. So we don't have to build the global type G, because we are guaranteed that this G exists by the theory, but then we can obtain the local type locally in each component by projecting the component, of course, only in its internal participant. So we achieve some separation of concerns. I'm already at the conclusion. This is what we offer. We offer a theory for distributed protocol specification. We have introduced new concepts, and we have proven that our theory is sound, is correct. Now, the reason why I was so loose on the semantics is that this development is purely on syntax. So that system of global and local type is pretty standard, and it has, over the years, since 2008, it has been given many different kind of semantics, synchronous and asynchronous, for example. And no matter what semantics you give, as long as you rely on a global type, a well-formatted global type for safety, you can apply these compositional techniques. Therefore, there is compatibility with the existing multi-party session type system. Not only that, these techniques are pretty general in the sense that the concepts behind them, okay, this development is ready for implementation, and we have sketched in the paper, we have sketched how to. But not only that, we have an example in the paper that these techniques can be extended to more sophisticated systems. So if the global types are richer, they, for example, have constructs for delegation or explicit connections, we can just redo the theory in a way, but reapply the same techniques. And as long as the theory is based on a global type projecting onto local types, these techniques are applicable. At the end, I will list the future work. As said, top-down implementation is on the way. It's pretty straightforward from this. And there you see what, in particular, we have in mind to apply these techniques to Scribble or Scribble-like design languages. There, and better in the paper, you can see the roadmap. Of course, this technique is ready for theoretical extension, as I said, but I'm confident that it can be brought further, so it can be ported to different formalisms for choreographies, so not only multi-party session types, but for example, choreography automata or choreographic programming. And then the last 2 points are interesting. The first one is very dear to me. I haven't done anything in this sense yet, but I want to mechanize this work in Proof Assistance, and I witness this love for Proof Assistant with the talk I gave a few days ago, ST30, the workshop for the 30 years of session types. Also, we want to change the perspective and apply these modular techniques, compositional techniques, to a bottom-up approach. So we start from the local types, maybe inferred from your programs, and then verify them. A first work on this was what my co-author presented at PPDP, again, some days ago in the context of SPLASH. Thank you very much. If any question, I'll be happy to take them.
So if there are questions, you can approach the mic.
Can you hear me?
Yeah.
Okay. I'm very happy with this work because I think that finally, after 16 or 17 years of multi-party session types, we're making some progress. And this is just a teasing, yeah? One thing that I'd like to understand is that, So you see, in traditional multi-party session types, you have the global type, and then you project into each one of the participants. So what I would like to see is this projection piecewise, so that you don't have to project in one go into all the participants. And I think this is what you're doing here. Can you go back a few slides, please, until where we have these diagrams?
This one?
So, yeah, so the traditional part is on the right-hand side, right? So on the left-hand side, you have 2 levels. Can you make it 3, 4, 5, 10 levels, or you have to?
I mean, you're not the first person asking this, so reviewers did that. Yes, you can. This work was very much driven by the motivation of what I presented, achieving this distributed specification. So I didn't think in terms of a hierarchy of levels connected via projection, but I thought in terms of having a global type, actually at the beginning, very naively, having multiple global types and putting them together. Then I had to open them with local constructs with hybrid type. But yeah, in principle, the theory is there. You had to add some parameters. I started sketching it, but you can definitely go more level up.
So you could decompose in 2, and then each of these in another 2,
yes.
And like this.
And you will have, of course, you will stop, if you start from above, you will stop at the level of local types. Okay. But if you're, for example, if your compatibility type, here is a global type, but if it's a hybrid type, so it's open, you could in principle first prove that there is a hybrid type for multiple components and then compose with something else with another compatibility type and other components. So yes, you can do this hierarchy of things.
All right, thank you.
Hey, thanks. That's very interesting. I wondered, like, have you considered, sorry, let me take one step back. If you consider the one component with the hybrid types, do I understand it correctly that, like, if you have an open communication to another component, you need to know which participant in that other component you are referring to?
Yes, we work under this assumption, yes.
Yeah. Have you considered to, like, lift this to a more also abstract this in the sense of your motivation of distributing actually the design, because then you still need to know internals of the actual component that you might not know, right?
Yes, sorry, I'll take this question and then it's yours. So, yes, the fact is that in this case, I consider this a feature and not a bug. I'm not joking. I mean, previous work, they could compose only 2 components, and they use forwarders. So that's also in my PPDP paper with my co-authors. They are the previous work. They are the authors also of previous work. So they use forwarders. So if you want to, if you want a system or a composition where each component is allowed to send only to some particular participant, that's you can always do. You pick one in the component in this case. But this was an addition actually, with respect to what was in the literature.
Okay, thanks.
Yeah.
Okay, let's thank Lorenzo again. And we stay with session types, this time with mechanizing session types using a structural view. That's work by Shuta Sano, Ryan Kavanagh, and Brigitte Pinker. And Shuta is going to explain us.
Okay, I think it's working. Cool. All right, hello. So I'm going to talk about mechanizing session types. These are actually binary session types, as they're called. So in contrast to the global types that were presented previously, it's more going to take a local view. So first, I think mechanization is quite popular in PL, and it's gaining increased popularity, which I think is a really good thing. Now, maybe what's preventing us from mechanizing everything is that it's time-consuming, it's difficult, it's tedious, so on. And so I would say that mechanization is currently an art. There are lots of components that we have to mechanize, and each component has their own design challenges, various strategies that people have developed to try to tackle these individual aspects. And in particular, I want to highlight the first point, which is on modeling bindings and context. Most languages have a notion of variable binding. And I would say for the functional setting, the trade-offs for all these techniques is fairly well understood. Maybe not perfectly, but there have been a lot of nice comparisons and a lot of just general, I guess, sheer quantity of mechanizations that one can look at to sort of compare. But on the other hand, for session type systems, which is message passing concurrency, there are a couple challenges. One is that there are lots of different systems and formulations, so it's very hard to compare different mechanizations, and that bindings are quite complex compared to the functional setting. So this, in turn, does not make, say, techniques in the functional world easily or trivially applicable to the session type setting. And furthermore, we have to deal with a linear type system, which is hard. So bindings are difficult. Higher order abstract syntax is a popular technique to mechanize, attack the challenge of bindings. And it's been employed in the functional setting, so does it work for session types? Well, we'd encode channel bindings because variables are channels in session types. And you would encode them as functions in your proof assistant, like coq, agda, whatever. And the benefit is that you get the binding infrastructure of the host language for free. You get alpha renaming for free, you get substitution properties for free, and so on. And for some specialized languages, you can even let the host language manage the context, so you don't even have to deal with the context at all. Well, first we still have a linear type system. Most proof assistants don't natively support linear implications, so you can't just simply use higher order abstract syntax to model bindings. And the solution, I will let you know in the next 12 minutes. But before that, I think it's also good to talk about what we mechanize. So we mechanize Phil Wadler's classical processes. It's a system based on the Curry-Howard isomorphism with linear logic. And it's quite simple, modular, and I think most of all, it's well-studied, and there are lots of extensions. So it's sort of easier to see how our technique scales to, I guess, more modern research. OK, and to set our expectations, I'm going to be talking about development of a new calculus called structural classical processes. The main summary is that we're going to outright remove the requirement of linear context in CP. We're also going to be mechanizing that in the proof assistant Beluga, which, and mostly I'll be talking about the first point, which is the encoding of the syntax in the logical framework LF. So some background, we can take a classical linear logic sequent. You can label the assumptions and assign a proof term. That gives you a type judgment for a process. You can read it like this. Process P communicates across the binary channels x1 to xn, and they follow the protocols A1 to AN respectively. OK, there are type constructors associated with these session types. I'll give just two. There's A plus B, which is a form of internal choice. The process should send an in-left or in-right signal and proceed as type A or B. And then there's also the unit, type 1, which corresponds to termination. So here's some scary type judgments. But it's important to focus on the context part, because I'm arguing that the context management by linearity is quite difficult. So we say that a process can close if it only has an assumption x of type 1. So that requires some sort of context operation to ensure the size of the context or ensure that it doesn't have other things. Here's one of the typing rules for plus. The process will send an in-left signal across the channel x, continuous p, and now the type of x changes to A, so to speak. This is a concept known as continuation channels. And so in the context of context management, how do we sort of handle these mutations of types? It's a bit weird, right? And we have the parallel composition rule, which again, I want to focus on the context. It really is about context splitting or context merging if you view it top down. So how do we sort of deal with this context split in the context of mechanization? So introducing structural classical processes, where we just outright remove the linearity in the context, but instead we'll be using additional local predicates to ensure linearity that way. So I'll be relying on the predicate lin_xp, which you can informally read as channel x and its continuations are used linearly in the process P. And so going back to the first problem, I'll slightly address this, and then we'll go back and fully address this. How do we ensure that the context only contains one assumption? Well, the idea is going to be that every time we bind a channel, we're going to check this linearity predicate. It's hard to show right now. It will be more clear later. But for now, you can see the type judgment. in SCP, which corresponds to this close, which allows an arbitrary gamma, which seems a bit scary because what if we're dropping live channels? Well, the linearity predicate is designed to prevent that. So we'll see how it all connects in the future. OK? And just to give a little heads up of what the linearity predicates look like, here's a very simple one. X is being used linearly in the process close X. Fairly simple definition. OK, here's problem 2, continuation channels. The channel type changes. Well, let's keep the old channel. We'll keep X of type A plus B and bind a fresh W of type A. So we're explicitly binding these continuation channels. And the linearity predicate for this construct is a bit more sophisticated than the closed one. So if you want to show that X is being used linearly in this process, you have to continue checking that W is being used linearly in P, the continuation process, and also that X doesn't appear again. Because if X appears multiple times, that's duplication. That's a violation of linearity. And finally, the context splitting problem. How do we do that? It's best to look at the linearity predicate first. So we'll look at it from the perspective of one particular assumption, Z. Well, the idea is that if you have this composition of P and Q, Z will appear in P but not in Q, or the other way around. So we'll have another rule that says it's linear with respect to Q but does not appear in P. OK, so that's the technique we're sort of going by. And circling back to the initial point about the close, well, we said that how do we ensure that all these bounded assumptions have satisfy the linearity predicate? And here we look at type rules that bind new assumptions. So that's the cut rule. This is CP. In SCP, it looks like this. There are 2 differences to note. One is that we're not splitting the context. We just keep the same gamma. And the other is that we have these additional linearity predicates over P and Q with the new binding X. So that really ensures that every bound channel is going to satisfy the linearity predicate. OK, and to make this all formal, we have this adequacy theorem, which essentially states that our linearity predicate is really capturing linearity. So graphically, we have CP, SCP. SCP is bigger because it has contraction and weakening, so it types more things. You can go back and forth between a subset of SCP and CP. The epsilon is just the encoding, because the process syntax is slightly different. But the key point is that we can actually characterize this subset with this condition that everything in the context satisfies the linearity predicate. So that really confirms to us that the linearity predicate is really capturing linearity. And to briefly talk about the mechanization aspect, there are essentially 3 components of the mechanization. First is that we encode the syntax in logical framework LF. We mechanize the type preservation proof in Beluga. And we also, on paper, prove the adequacy of our encoding in the sense of LF. I mostly want to just highlight the higher order encoding part. So I'm going to be depending on some types name, proc, and TP. Name stands for channel names, proc for processes, and TP for session types. I will spare you all the details of how you encode the session types, because they're fairly standard. But here you'll see higher order abstract syntax at play. Well, not here, but the next one. So we'll start with something simple. How do we encode the SCP process close X? Well, it's just a constructor that takes in a name. Very simple. OK, now you have this in-left process. OK, so the constructor takes a name. Good, that's the X. And then the second argument is a function, name arrow proc. So that's what's really encoding this binding of w.p. We're encoding it as a literal intuitionistic function in LF. OK? And in parallel composition, you can play the same game. P and Q really are being bound to these fresh channels X. So both P and Q we encode as name arrow proc, just functions that take a name and output a process. OK, and this is, I think, maybe the most sophisticated part of this encoding, is how we encode the linearity predicates. So on paper, we write linearity predicates in a sort of hand-wavy manner, lin xp, right? So in our encoding, we're going to be encoding this predicate as a predicate over functions. They're functions that take a channel name and then outputs a process that treats that input linearly. Okay, so any function that satisfies this predicate will take a name and use it linearly. That's the idea. Okay, so here's a simple rule with the close. So the function that takes in an x and then outputs the process close x uses x linearly. That's the idea. Okay, so the more interesting rule in left. Okay, so first of all, if we look at the on-paper formulation, we have two premises. Let's tackle the first premise, lin WP. That's covered by the premise in the encoding linear p. And the w sort of disappears because we encode these w.p's continuations as a function. So we don't really need to explicitly specify a w. And then the question is, where did the other premise go? The premise that x does not appear in p. That's actually wonderfully covered by higher order unification. So the idea is that the meta variable capital P on the encoding is bounded outside this lambda x. So there's no way that capital P can depend on x. So that's how we recover these free name conditions for free, so to speak. And I was kind of gonna talk about the parallel composition, but it's really the same idea as in left. We get the free name condition for free. We have to do some manipulating because we have to deal with multiple bindings. But really, the idea is the same as in left. Okay, so we have two things. We have the meta theory of this new calculus SCP, and we have the mechanization of it in Beluga. So to talk about it separately, SCP we developed as maybe a promising foundation for a session type system that's more about mechanizing. And the key motivation or step is that we try to separate the idea of linearity from being a property of context that you have to encode to this explicit localized predicate. And I also want to argue that this idea, although synergizes really well with HOAS, higher order abstract syntax, isn't just for this technique. Any sort of way you deal with bindings, you'd have to deal with some linear context. And I'm proposing that if we use SCP, we don't have to deal with a linear context. We can use a structural context, which there are many more libraries available for. You have to deal with fewer operations, and it's better understood, I think. And our mechanization in particular, as I mentioned, uses HOAS to encode these channel bindings. And I think the biggest strength we were able to showcase with this style of encoding is that we get these free name conditions for free. And the type preservation proof actually required 9 additional lemmas, which is, I think, remarkably small compared to how it's usually done. In fact, a colleague of mine mechanized CP by explicitly managing contexts. And the last time I heard from him, he had 90 lemmas to deal with just the linear context. So linear contexts are, quite difficult to work with. And I think there are two interesting avenues for future work. One is to mechanize SCP in non-HOAS settings and other proof assistants. I'd very like to see sort of the trade-offs between this additional linearity predicate and the act of not having to deal with linear contexts. And also, as I mentioned, there are lots of baseline process calculus session type systems that people develop off of. It's not just CP. There are things like GV or SIL. It would be nice to see how this linearity predicate idea works to these other systems as well. Thank you very much.
Thank you. This is very nice. So you gave some motivation for how this makes things easier, but were there any particular pain points that you ran into? Because it looks quite a lot more complicated in some ways.
So the pain point was figuring out the right encoding. So there are many ways to sort of encode this linearity predicate. There are many ways to encode this process. We didn't necessarily have to use HOAS. We didn't necessarily have to use continuation channels. And getting it wrong really makes the type preservation proof really tedious. So it took 3 retries to get that really solid baseline encoding. And once that happened, all the proofs were remarkably simple.
So you think you've hit some sort of sweet spot? I guess, yeah, you really need to try it out in other contexts to see if it does actually adapt.
Yeah, although I think it's worth mentioning that we sort of summarized our, I guess, our trial and error into this theory of SCP. We didn't come up with SCP first. We sort of did the mechanization, sort of backtracked, and got SCP.
Yeah. Please.
So I agree with you, linear contexts are really difficult, but other people suffered before, and I was wondering whether you considered implementing directly into a logical framework that had linear context or on top of an implementation of linear logic.
Yeah, so there are some frameworks that really do provide linear context management, as you said, like Self, like concurrent LF, and so on. The drawbacks to those are that they don't have any solid implementation. So although there's a theory behind it, we couldn't really sort of write actual code and compile it, so to speak. And as for dealing with the context explicitly, I think that's the standard approach that's taken for mechanizations. And I think there are lots of lemmas that you do have to prove to say context splitting is safe. You can sort of either mutate or delete and add channels in a safe manner and so on. So I do think that it is like a very promising approach to not deal with these linear contexts as long as we don't have a solid proof assistant with native support for linear functions.
Okay, last question, very fast.
Okay, just this idea of types for objects that evolve in time or in your derivations is very unique to session types. But you got away with that by rebinding the channel, right? This W that you use. So I assume your operational semantics will take care of that, whenever you have rebinding. So this reminds me that, so if you go into the functional languages with session types, this is exactly what is happening there. Okay, that you rebind, so that you don't have one variable that will have two different types along a derivation. So because so this is probably my intuition is that you will have all the machinery that needed if you want to look into session types for functional languages, because you already have this rebinding thing. Yeah, just a comment.
Thank you. Yeah, I agree. I think there's no obvious challenges, I guess, to apply this technique to say, functional languages with session types.
Okay, let's thank again the speaker. Okay, and the next presenter is Federico Mora, which is going to talk to us about message change for distributed system verification. Please.
Awesome. Can you hear me? Yeah. Okay, cool. Okay, so thank you everyone for coming. So I'm just going to get right into it. It turns out that it's not very hard to find examples of bugs in important distributed systems. So here's one that I found in a blog post that I particularly enjoyed. This is a senior principal engineer at Amazon Web Services just describing how a bug in an implementation brought down all of Amazon.com. It's a fun read. I definitely recommend it. The point that it gets across, especially for this presentation, is that distributed systems have bugs. These bugs exist in real systems. They're common and severe. Okay, so luckily we have some tools at our disposal to try and help with this. So the kind of tools that I'm particularly interested in are formal verification systems. So on the screen you see kind of like a sketch of what the usual input-output behavior of these tools is. So on the left you have like a system description S, some properties usually in the form of invariance I. Then these are given to a tool which is in the middle that checks or tries to prove that S satisfies I. Ideally, you get a check mark and you're happy you're done. Most likely what you get is kind of like a timeout or an unknown or a counterexample to induction, and you have to like fix your system S or update your invariance or something like that. And one kind of rule of thumb that's important for this presentation in the space is that usually like the more detailed your system S gets, the harder it is to get your invariance I right to get that proof to pass. And so this is an issue for us because the goal for our work for this presentation is to try and verify asynchronous distributed systems kind of like as close to the implementation level as possible. So specifically, we want to basically verify systems that look like what a developer would write in a language like Erlang or P, or using a library like Akka. And so these languages are explicitly talking about message passing using this concept of like an event handler, which I've pasted 3 examples on the screen. These are like blocks of code that describe how a process reacts to an incoming message. This will become relevant later, but this is kind of like what we're trying to target with this verification. Okay, so overall, the contributions that we're going to make in this paper is we're going to define message chains, a notion that we're then going to use to verify asynchronous message passing systems while avoiding reasoning about individual messages or individual buffers, and without having to like manually abstract your system too much, and without having to like manually relate these abstractions back down to your implementation level. We're going to do this all in a prototype tool called the up verifier that targets like a P-like language. That's where the P from up verifier comes from. Okay, so to make it a bit more concrete, we're going to look at an example. This is from a publication from 1979 that I'll just call the Chang and Roberts algorithm. It's a really nice paper. They have, I'm going to pull out basically 2 paragraphs that summarize the algorithm really well, so we can kind of get rid of a little bit of noise here. Essentially, what you have is a circular arrangement of nodes. They can communicate clockwise, and what they're trying to do is collectively like collaborate to figure out which one of these nodes has the largest ID. They also have unique IDs, by the way. Okay, so the code, or like description for the algorithm is, again, really simple. We're going to skip through this quickly. Essentially, each node will start by sending their ID clockwise, and then the nodes will be receiving these messages. If the message they receive is larger than their ID, then they're going to forward that. If the message they receive is less than their ID, then they're going to kind of ignore that. And if they receive an ID that's equal to their own, then they're going to realize that they're the leader, that they should go do the thing that they want. So here's a really extremely rational instance of the Chang and Roberts algorithm that you can use for your next OOPSLA submission. So if you have to maybe draft a rebuttal or something like that, you need to pick one of your co-authors to open that document, start drafting the rebuttal. You can use the Chang and Roberts algorithm. Basically, you would have your ORC IDs as the unique IDs. You would have the author list give you that circular arrangement, and you can use email for message passing. This is kind of a joke, but I'm going to use it as an analogy for message chains later on. Okay. Oh, and by the way, the goal would be the specifications that you would care about here is like you don't want 2 authors to think that they're the leader and start kind of like drafting a rebuttal. That would be bad. Okay, so let's try to model this system, and let's try to verify it later. Since this system has been around since more than 40 years, basically everyone has verified it. And so here is an example in TLA+. It's a little bit hard to read, so you might have to just take my word for it. But essentially what they're doing is they're defining this messages variable, which is like a global shared variable, and they're modeling message passing using that variable kind of in like first order logic. This is really common, so this is a more recent tool called MyPyVi. This, I should mention, is zoomed into the code that's actually like receiving a message and deciding what to do in that protocol. And so the proof in MyViPy is essentially the same as the TLA+ one. Instead of a messages variable, we have a variable called pending. And they're doing kind of interesting things, like, for example, when a node actually receives a message, it doesn't necessarily kind of like mark it as received. It could just like continuously receive the same message over again. And that's fine. It works for the proof. It's an abstraction. They're manually modeling message passing. Okay, and of course, there are many more choices. There's stuff like Ivy in the domain-specific tools space. There's also proof assistants. There's software verification engines. In general, what you see when you go out and look at proofs for this protocol and protocols in general, it's that, people are manually modeling message passing, and then they're writing proofs about these kind of like shared memory variables, these abstractions. Okay, so what we want to do and what the up verifier does is it actually takes P-like code, and so it takes message passing kind of like event handlers like this, and we want to verify at this level. So this leads to kind of like shorter code for the engineer or formal verification user. But it's also can be a little bit dangerous because it's more detailed in the semantics of message passing. Like we don't have those abstractions to play with. We're actually at the message passing level. And so as we know from our rule of thumb, the more kind of detailed your system gets, the more work you have to do at the invariant level. Okay. And so that's where our main contribution is. This is where we're going to go on a little bit of a tangent to define what message chains are, and then we're going to return to that system and verify it using message chains and see why that's really cool. Okay, so message chains, first of all, they're just like a data type, and it looks almost like a list data type in a functional programming language. So message chains are either empty or they're kind of like this send object, where a send has a source, a target, a payload, and then this kind of like this history, which itself is a message chain. And then the semantics of the message chains, how we like create these, is basically like our verification engine will automatically instrument the P code following two rules. So first, if you have a send statement that's like inside of an event handler, then what we do is we like extend the message chain that we received. So we'd be receiving a message chain, and then whenever we have a send, it's like that message chain that we received is like the history of the new one. And then the second case is even simpler. If we're sending a message outside of the event handler, then the history is just empty. So if you remember our rebuttal election example, case 2, where we're kind of like sending from scratch, is on the far left. It's just that first email in an email chain. And then there's the email chain on the far right is like successive applications of case 1. Like we're extending these message chains. Okay, and then finally, when I talk about message chain invariance, essentially I just mean like a predicate P that holds for all message chains that appear in the system. And so everything is fixed, and P is just the predicate that kind of talks about the message chains. So again, in the rebuttal election example, a couple message chain invariants that are sort of interesting is that if you look at any of these emails, the most recent email always holds that largest ORC ID. That's like a useful property, interesting property. Another one is that we never skip an author, like we're always going in that circular arrangement. All right, cool. So now we actually have everything we need to do a full verification of the Chang and Roberts algorithm. And so here it is. This is kind of heavily commented, but with invariance directly from the proof. So the properties that we care about are at the top. They're basically just saying that we want at most one leader to be elected, and we want that leader to be the one with the largest ID. So these are safety properties. And if we were to give this to our tool, we would essentially get a counterexample to induction. Like alone, they're not enough to prove. Alone, they're not inductive. So what we can do is we can add 2 message chain invariants, which are exactly what we already saw. So we want to say that the largest ID at the front of every message chain is, or the ID at the front of every message chain is the largest ID in that message chain. And 2, that we never skip anyone. We never skip an author in that order. And so that one's a little bit harder to write, but it's described there as well. And so this is really cool, actually, because that proof, first of all, it guarantees that this system works no matter how many nodes are in the system. So it's kind of like parametric in that sense, which is cool, but other people are already doing that. What's even kind of like extra cool is that the proof never once talked about like individual messages. It never talked about like individual message buffers. It didn't require any kind of like abstractions, manual abstractions. And the automated abstraction that we put in, this message chain one, was kind of like automatically related to the implementation level detail. And also I would argue that the invariants were relatively intuitive. So that's yeah, we're really excited about this. What's kind of maybe even more exciting, especially moving into the future, is that we can learn a lot of these message chain invariants automatically. And so just we're using techniques called specification mining. Quick definition here is that specification mining is a machine learning approach to discovering formal specifications that code likely obeys. So it's kind of like you're giving observations as input, and the tool is giving you back like a predicate that should hold for those observations. in our setting, we're interested in learning message chain invariance. And so kind of more concretely, like we can take a tool like Trio, which I've cited on the bottom here, which is a program synthesis tool for recursive functions. We can give it example message chains that occur in the system, just we can generate those by fuzzing the system. We can give it some hints of message chains that don't occur in the system, shouldn't occur in the system, and it will automatically synthesize a recursive function, like lightning quick. It's a really impressive tool that is equivalent to the first auxiliary invariant that you used. And this is just from examples. Another way to think about it is like we're kind of giving this tool like a bunch of emails from our rebuttal election, and it is returning like, hey, the most recent email holds that largest ORC ID, which is a property that we used for our proof. Okay, so sorry, that was a bit of a whirlwind. And so let's kind of step back a little bit and try to talk about an evaluation. So in the paper, we go over 5 research questions, and I encourage you to go check them out. For the presentation, I'm only going to talk about RQ2 and RQ5. We mentioned a little bit of RQ3, so in the paper, we basically look at more case studies, kind of like the Chang and Roberts verification, and we show what the proofs would look like using message chains. We also do the same thing for specification mining. Yeah, and so definitely check that out in the paper. The RQ2 is, RQ2 tries to answer like it's a performance comparison. So essentially, we have our compiler that is automatically instrumenting all these message chains. It's adding new variables. It's doing some work. And so one thing that you might be worried is that we're getting a really big performance degradation. And so what we did to evaluate that is we essentially took a bunch of benchmarks from a PLDI-20 paper from MyPyVi. We translated them to the up verifier kind of like as faithfully as we could. And then we timed the verification. And we found that there doesn't seem to be that big of a performance degradation, if at all, when using all our kind of like compiling infrastructure and verification. So that's exciting. We then also took 2 systems that were kind of relevant to one of our co-authors, Ankush, who works at Amazon Web Services. And so Amazon Web Services had a couple systems that they were interested in verifying. We talk a little bit about this in the paper. The first one, Global Clock, is kind of a smaller system. It takes about 1.5 seconds to verify. The second one, I think, is a little bit more interesting, so I want to take a second to talk about that. It's a 2-phase commit, multi-version concurrency control protocol. And one kind of exciting thing here is that in 2-phase commit, you have this kind of like this situation where you're sending out, you're broadcasting a lot of messages, and then you're kind of like waiting for responses. You're sort of like flooding. And so message chains are a very linear thing, so it's kind of surprising that even though we have this non-linear kind of artifact, that they're still useful. And so I'm out of time, but thank you everyone for listening, and I'm happy to take any questions that you might have.
Okay, we have a couple of minutes for questions while Leven sets up.
So on your slide 31, you have this property. No worries. Okay. That, you guarantee that at most one drafts the response. What about at least one drafts the response? So you have safety, but what about liveness?
Yeah, that's a good question. We don't do any liveness. We're in a purely asynchronous setting, so liveness kind of goes out the window. We're kind of thinking about starting to support like partial synchrony and situations where we can start getting some liveness back. But our system model doesn't, like we have no kind of guarantees that a message will even eventually get delivered. So no liveness for now.
So actually, what is the system model? Because you are doing an abstraction over a message that is sent over a channel. So what are you assuming from the channels?
Very little. So Yeah, we're like purely asynchronous message passing system. We're assuming that there's no kind of like scrambling, like on purpose, whatever. But since we're doing like our proofs by induction, kind of like the solver is free to explore kind of like crazy states before, like pre-states before our inductive step. Yeah, we're able to kind of like put something into the network, and we're able to grab from the network.
Eventually arrives no disorder.
Oh no, there's no order.
Okay.
It's asynchronous. Yeah.
Okay, thank you. Okay, and we move now to randomized testing of Besant and fault-tolerant algorithms. Levin will be presenting this work, which, as you can see on the slide, is one of the distinguished papers.
Yeah, thank you for the introduction. My name is Levin Winter, and I'm going to present our research paper on randomized testing of Byzantine fault-tolerant consensus algorithms. This is joint work with Florena, Dan, Klaus, and Bochu. As you probably know, in recent years, blockchains have increasingly increased in popularity. These systems often run on a set of distributed validators, which all keep a local history of the transaction and the blockchain. When a new transaction is submitted to the network, these validators need to agree on the order of these transactions. For this, they typically use Byzantine fault-tolerant, or BFT, consensus algorithms. In our work, we focus on consortium-based BFT algorithms, which are much like the seminal PBFT and its variants. Unlike crash fault-tolerant consensus algorithms, so for example, Paxos or Raft, Byzantine fault-tolerant consensus algorithms are resilient to malicious, or also called Byzantine nodes. To better understand what that means, let's have a look at an example. Below, you can see the execution of Ripple's XRP Ledger consensus protocol, and I show you the messages that the 7 validators that we have in the system exchange throughout time, where time flows from left to right. In general, these consensus protocols are structured into rounds, and as you can see here, we have 5 distinct rounds. 1 transaction round, and then 2 proposal and validation rounds, which alternate. During the transaction round, P3 disseminates a transaction that it received from a client to all of its other peers, and we denote this with the blue arrows. This is followed by a proposal round where all of the validators share their intent to include this blue transaction into the next ledger I. Once the validator sees sufficient agreement with all of its peers, it moves on to the validation round. Here, it casts its final vote on wanting to include the blue transaction into ledger I, and once it reaches a quorum with all of the other validators, it will commit this blue transaction to the log. Since no new transaction has been submitted to the network, in the following proposal and validation round, they agreed to not include any transaction into ledger I+1. So far, so good. But as you know, not everything always goes according to plan. So let's imagine that P1 crashes during the 3rd round. It's not able to send any validation or proposal message afterwards anymore. As you can see in the chart, the rest of the cluster is able to continue normally because the protocol is resilient to crash faults. Since this is a Byzantine fault-tolerant consensus algorithm, it is also resilient to Byzantine faults. So let's imagine that P6 turns evil and sends a malicious validation. Then you can see again that the rest of the cluster, all of the honest nodes, continue to correctly operate, and the protocol makes progress. I think you can all imagine that in order to deliver these guarantees, it is essential that the protocol is implemented correctly. Unfortunately, this can be quite difficult in practice, as these systems often become very complex. And even BFT algorithms whose models have been formally verified can have buggy implementations. What I just described is not just a theoretical concern, but an actual issue in practice. Over the years, many adversarial scenarios have been detected in several BFT systems and their preliminary versions. We therefore identified a strong need for testing tools for BFT algorithms. Unfortunately, in general, the existing testing methods do not sufficiently address this Byzantine behavior. Byzantine behavior is defined to be arbitrary and unbounded in nature. This means that basically anything is possible except a few limiting constraints, like Byzantine validators cannot break cryptography. I think that makes sense. Unfortunately, the existing tools do not sufficiently address and explore these Byzantine behaviors. We therefore set out the goal of designing a testing algorithm for distributed systems that can detect these BFT bugs while remaining practical and applicable to large-scale blockchains. Our response to this goal is BizFuzz, a randomized testing method for BFT algorithms. It relies on 4 key insights. The first is that we bound the number of faults that we inject into the system in order to ensure that it continues to make progress. Secondly, we simulate network partitions, as these have been shown in the past to expose some of the bugs. Third, we use structure-aware mutations. This is inspired by the input generation from traditional fuzzing, and it means that we preserve the general structure of the message in order to make it remain correct. Lastly, we propose the new concept of small-scope mutations. These small-scope mutations apply a small change to a value. We hypothesize that this is sufficient to expose most of the bugs in a distributed system. A small change can either be small in absolute value, meaning that you, for example, increment or decrement an integer, or it can be small in temporal difference, meaning that you replace a hash with, for example, a hash that has been previously in the network. We hypothesize this because we think that these small changes expose most of the bugs. We used BizFuzz to discover previously unknown bugs in several blockchains. To better understand how we did this, let's have a look at an overview of BizFuzz. The developer supplies as input a list of processes procs and 4 integer parameters. BizFuzz then continues to randomly select F processes to be faulty. It selects D rounds during which a network partition will be applied and C rounds during which we apply our structure-aware and small-scope mutations to the messages that are in flight. These faults are distributed among R rounds of the consensus algorithm. Once this is done, BizFuzz can start the execution of the protocol. We mutate or drop the messages that are sent between the different processes according to the previously generated fault configuration. For this, we use a given set of message mutations that has been supplied. After the execution completes, we check for the 4 consensus properties of agreement, integrity, validity, and bounded termination. OK, I think to better understand this, let's have a look at a concrete example. Here you can see how BizFuzz, or well, now you can't see it, but I will show you how BizFuzz injects 1 process fault into the execution of Ripple's XRP ledger consensus protocol. We again have the 7 validators, and BizFuzz randomly selects that P3 is going to be the Byzantine validator. We instruct BizFuzz to distribute the process fault among one of the 5 rounds that we've already seen. BizFuzz then randomly determines that during the 3rd round, so the first validation round, the validation messages sent from P3 to P1, 2, and 4 will be mutated. We're now ready to start the execution of the protocol. We again have the transaction round where the transaction gets disseminated, and the proposal round where all of the validators agree to or propose to include the blue transaction into ledger I. We've already seen this. Now comes the interesting part. OK, the slides are back. Cool. I guess the slides got too excited. I don't know. OK, now comes the interesting part. All of the correct validators propose to validate ledger. This really caught me off guard. OK, all of the correct validators send a validation message for ledger I, whereas BizFuzz. OK, let me try this again. All of the correct validators send a validation for ledger I. You can see that at the top. BizFuzz now mutates. I don't know. I keep seeing the slides over there, so yeah, I don't know what that is. But BizFuzz mutates the validation that is being sent from P3 to P1, 2, and 4 to be a validation for ledger I+1. This happens in flight, and this mutation is a structure-preserving and small-scope mutation because it slightly changes one of the messages fields. The execution of the protocol continues, and so far everything seems to happen normally. All of the validators propose to not include the transaction. But during the validation round, you can see that the consequences of the mutated validation message manifest. All of the validators that previously received this mutated validation are not able to themselves send validations anymore. This is because their internal state got corrupted, and yeah, they cannot send validations anymore. Because there are not sufficiently many validations in the network, they cannot reach a quorum and therefore cannot make progress. This violates the consensus property of termination. We have just found a buggy execution. This is actually a bug that BizFuzz detected in the production implementation of the XRP ledger that was previously unknown. I would like to highlight that this bug only exposes using our small scope mutations because the ledger sequence numbers are checked to be in a specific interval. In our endeavor to thoroughly test BizFuzz, we applied it to 3 blockchains. For an implementation of PBFT, we detected a known liveness violation and 3 implementation bugs. For the production implementation of Tendermint, we discovered 1 potential liveness vulnerability. However, our most exciting results were, as you can probably already think, with the XRP ledger. Here, we discovered 2 known protocol vulnerabilities and 1 new variant of these, as well as, most noteworthy, this new implementation bug that was previously unknown in the reference implementation of the XRP ledger. Let's have a closer look at these results just to get some more insights. On the left, you can see the configuration of BizFuzz. So C is the number of process faults that we inject, and D the number of network faults. In the subsequent columns, you can see how many out of the 300 configurations, out of the 300 executions that we ran per configuration, violated one of the 4 consensus properties of termination, validity, integrity, and agreement. In addition, for every configuration that had at least 1 process fault, we ran 1 set of experiments using our small scope mutation and 1 set of experiments using the any scope mutations. Any scope mutations don't make a slight change to the value, but replace it with an arbitrary one, so a randomly generated one. Furthermore, we implemented a baseline fuzzer that randomly flips bits and randomly drops messages. As you can see, this baseline detected significantly fewer buggy executions and only managed to expose 1 of the several bugs that BizFuzz found. I would also again like to draw your attention to the second last column, where you can see that some of the bugs only expose using our small scope mutations and not using any scope mutations. Much like the bug that we've already seen, there were also other bugs that also only exposed using our small scope mutations. But this bug that I just showed to you in the previous example existed because the developers ignored the fact that there are malicious nodes, or there could be malicious nodes in the network when implementing a particular part of the system. They assumed that incoming validation messages are correct, coherent, and as we know, this doesn't always have to be the case. We have reported this bug to Ripple, and together with them, I developed a fix which since has been merged into the production branch. And I would like to highlight that our bug was deemed eligible for reward under Ripple's bug bounty program. To conclude, I've shown you BizFuzz, which, to the best of our knowledge, is the first randomized testing tool for Byzantine fault-tolerant algorithms that found actual BFT bugs in production blockchain systems. It relies on the 4 key insights of bounding the number of faults in order to ensure progress, of simulating network partitions because they can often expose buggy scenarios, and it uses the structure-aware and small-scope mutations where, yeah, I place an additional emphasis on the small scope mutations. We use BizFuzz to detect previously unknown bugs in several production blockchain systems. And if you have any questions, I encourage you to have a look at the paper, ask now, or talk to me after the conference. Thank you very much.
Good timing. Please.
Thanks for the nice talk. I have a question about, like in your test, how many participants do you use? Like in your example, you mentioned it's 7 participants, but in your experiment, maybe you use more than that, or you think just using 4 participants, or just not 7 participants are just enough?
So in the experiments for the XRP ledger, we indeed used the 7 participants. I'm not entirely sure about the PBFT experiment and Tendermint, but yeah, we always kept that constant and just simulated a smaller network. Yeah.
Okay, so like is it like guaranteed that like if there's no problem with the 7 participants, then there's no problem with more participants?
No, I mean, that is not guaranteed, but so this is a randomized testing method, so I mean, there are really no guarantees to this method, but yeah, we decided on this configuration because, yeah, it was quite approachable, it made sense for us, but yeah, you could, of course, you could apply this method to a larger cluster if you wanted to, so you could sample more faulty processes, increase the general number of validators, so these are definitely things you could look into if you wanted to.
Yeah, thank you for...
Yeah, thanks.
Hi, thank you. It was a great talk. I was wondering how easy or how difficult it is to apply this technique, the system, to other blockchains. I mean, there are different consensus protocols, there's different implementations, and like, you know, do you have like maybe like plans to do it, or maybe instructions on how other, you know, blockchains could take advantage of that?
Yeah, so I think I can really answer that question because, for example, for the XRP ledger, there we implemented this system from scratch. So what you basically need is a message interception layer. We basically implemented a giant proxy through which all of the messages are routed. And if you have such a message interception layer, you just need to implement the BizFuzz algorithm, which really is very simple, so that shouldn't be much of an effort. But yeah, you need to have control over the network and be able to mutate the messages. But if you have that, yeah, you're set and you can use BizFuzz.
Thank you so much. Thank you.
Yeah, thanks.
So I have also a question. The mutation seems very specific to the use case. Are you exploring to see if you could use it for other kinds of distributed system algorithms?
So you mean this increment of that sequence number? It's now very specific?
It is, yeah.
Yeah, so I mean, this is something where the developer would come in and not guess, but use their judgment to make up these mutations. But of course, this is also something that you could try to automate. So in our future work, we want to look at more intelligent ways to devise these mutations to better ingest these faults. So this is something, we plan on doing.
Okay, thank you, Levin.
Yeah, thanks.
So we are going to close the session with a talk on validating IoT devices with rate-based session types. Okay, that's quite a title. So thank you, Grant, and please, floor is yours.
Hello, I'm Grant, and yes, I get to close out OOPSLA 2023 by talking to you about some work I've done with myself, my PhD lab mate Cheng-En, our advisor Luke, and our collaborator at Queen Mary, Ray, on how we can apply rates to session types. So if you take a look around the room, maybe down at your own wrist, you might spot a smartwatch floating around. And a very common feature of these devices is a heart rate sensor, one right here on my wrist. And we will look into the structure of how the signal processing necessary for this works. We see this, a pipeline of concurrently running tasks connected by message passing channels, implemented in a variety of ways. But one thing we've noticed about a lot of these embedded devices, especially IoT type things doing sensing, is that they use message passing internally. Now, why am I focusing on this one? Well, because that's what we used in our artifact. We actually pulled an open source smartwatch implementation. That's where this pipeline structure comes from, and built it up during our framework. And if you thought the Rust talks were next door, guess what? This is yet another Rust talk. We'll get there at the end. But as a type systems person, I look at this and I see there's kind of something more going on than just normal protocol stuff here. There are some rates associated with these channels. It's important that the data moving from the sensor to the signal processing block to the next happens at a fixed known cadence. This ends up being an assumption often baked into the math of these blocks. So again, being a PL person, a natural thought is, how can we use types to capture some of this behavior? And if I want to capture behavior over channels, a natural place to look would be session types. So the goal of this paper was to use session types to capture some of these correctness properties in systems with rates. Now, the problem we run into is session types are great at ensuring agreement on protocols, and they've even been extended to deal with some temporal aspects, but none of them really captured the correctness properties our systems expect from rates. Now, I should be clear here, what do I mean by session types, because there are many varieties. We based our system on traditional binary session types. We're going to use types to capture the protocol of our view of a channel. Those types look something like this. We can send a value with a fixed data type v, and then continue with a session continuation described by the type t. Now, wherever there's a receive, there needs to be a corresponding send, and vice versa. So we have a receive primitive, which lets us accept that value v. Now, our pipeline doesn't need it, but we do support select and offer, which allow you to talk about branching constructs in your protocol where one side offers some options and another selects how the protocol should continue. A key part of what we end up doing, though, is capturing repetition. The traditional way to do this is via a fixed point combinator, often abbreviated mu, which talks about a session t that repeats. Now, if you want to terminate, we have a construct for that as well, end. But there's something interesting about these constructs I'd like to point out, which is that they've got a correspondence going on. And this has a name in the binary session types literature, where it is called duality, and is a relationship we need to check between channel types when we do type checking. Specifically, we're going to look structurally at these and walk along the types, making sure every send is paired with a receive, any select is paired with an offer. Whatever I do, my communication partner really needs to be ready for. So how might we apply this to our systems? Well, our paper has developed all of its theory in terms of process calculus. I find that a little hard to read on a slide. So I'm going to be talking in terms of some more abstract pseudocode. That's what I've got up here. So I've defined a periodic task. This is something that is going to execute its code with a fixed cadence. Here, 1 second. This particular task is that first block in that pipeline. It's going to do some external I/O to read from its heart rate sensor, and it's going to pass the raw sensor reading down a channel for the rest of the pipeline to operate on it. And then it's going to repeat. This is a session that continues over and over again. Now, again, this is pseudocode. If we were to do something a little more implementation-like, we'd end up with something that looks a bit like this. Same structure, more or less. Its big difference would be our periodicity has been boiled down to an actual real-time OS primitive, wait for period, more or less delay with some extra bookkeeping. But really what this is capturing is a more general paradigm of a producer. That is the core communication that's happening here. Now, in systems, producers come up a lot, usually paired with a consumer. So here we've got almost the same process, but we're doing the receive. So we've got a send, and we've got a receive. Now, how would we apply types to this system? Well, we are sending in a loop, so our type needs to look something like that. So we end up with this. We have a recursion where we are recursing to create an infinite session in which we simply send an int. Now, analogously, our consumer is going to have a type where it receives that int. And this is good, because we have that duality property I was talking about a moment ago. So we can, in fact, type check this. If I walk along these types syntactically, I can see that everything lines up. But what happens if I change that consumer process just a little bit? And by just a little bit, I mean 1 character. I flip that period of 1 to be a period of 2. Now, the code hasn't changed. Nothing our types know about has changed. So the types are going to remain the same. The problem, though, is rates are a temporal property, and we've changed timing properties. So it's not quite clear that this remains valid the way the previous code was. In fact, it doesn't. To see why, consider drawing this out over time. So here I've kind of interpreted that recursive type in an equirecursive manner as just an infinite string of sends. Correspondingly, on the bottom, we've got an infinite string of receives. And again, in a traditional equirecursive fixed point interpretation, this is fine. It's not for us, because this horizontal axis represents time. So as we execute this session, there is a divergence between the receiving end, which is running slower, and the sending end, which is running faster. This grows unbounded in time. The longer we execute, the further apart we get. Depending on how you actually realize this system, you may stutter because you're waiting on someone else. You may overflow any finite-sized queue, this grows without bound, or you may choose to just drop messages, in which case your signal processing is going to be very, very wrong. So we need to move some of this information into the type. And we do this by replacing that fixed point construct with something very similar syntactically that can capture the period information from that construct we had before. So instead of mu, we're writing omega, and that n is the key part there that tells us how often does the session in T get repeated. Fundamentally, this is a binding construct, details in the paper. So now if we look back at that consumer process and think about how we could use this type, we end up with something that looks like this. And now these look a little different syntactically, and this is good. When I want to check an updated form of duality, I'm going to look at these annotations, and I'm going to see they're different. And from that, I can conclude these do in fact represent incompatible behaviors. This is not a program I should allow. I should statically reject this. Now, what happens if I look at yet another consumer? Well, let's say after I've changed the period, I now change the number of communications. So now, left side unchanged, I'm going to continue sending 1 every 1 millisecond, but for my consumer, I'm going to be receiving 2 every 2 milliseconds. Well, type on the left, unchanged code, unchanged type. The type on the right, that session in the body now has 2 receives in it, and that's going to get reflected directly in the type. Again, I can check syntactically for duality and conclude these are not dual, type checking fails. Now, it turns out it's not quite this simple, because it's actually not clear that this is broken in the same way our earlier example was. Consider what happens if we look at the behavior of this over time. So here I've written the execution of the producer on the top, the consumer on the bottom, and connected them with arrows indicating when the communications happen. And we get this block that repeats over and over, but we see now those arrows are actually lined up in time. So we've got different periods, but that communication cadence is consistent. The rate in both ends of the session is the same. Another important thing to note is this whole block has its own cadence. It's got its own period where the whole thing repeats. Here, 2 milliseconds. This is not a new observation. In the real-time systems literature, it's referred to as a super period and captures something about the periodicity of the system overall. So going back to our producer-consumer, I have this type on the left. But it would be more helpful to reason about that interval I just showed you on the before. So I really want a type that talks about it over 2 milliseconds, something like this. If I wait twice as long, it runs twice, performs 2 communications. Somehow there's a relationship between these two. And that would be nice, because if I could solidify that, it looks very much like that type I had on the other side. Those are dual. So the question now becomes, how can we get between these two types? one of which reflects the code we have in front of us, the other reflects the behavior we want to validate against. We formalize this relationship via a relation we refer to as expansion. So given this process we had here and its type, we can talk about a related process that has analogous behavior, but over a longer time interval. This process would have this type that we were looking for. And again, they represent analogous behavior. They do the same protocol at the same rate, just with a different length body. So again, there's a relation here. I've chosen a suggestive symbol. It is in fact a partial order over types, pedantically not subtyping for reasons we get into in the paper, but we can use it in much the same way. And that means we can define a compatibility relation. So this is what we actually end up using during type checking. In our compatibility relation, instead of subtyping using expansion, we can say two types are compatible if for both of them we can find some T3 that is an expansion of T1 and where T3's dual is an expansion of T2. That T3 represents some common interval over which we reason about these types. Some common interval. What common interval? Well, the good news is it's actually not that hard to find. There's only one reasonable choice for T3. It came from this diagram earlier. T3, that common interval, is that superperiod. It is the interval over which the system has that well-defined periodic behavior overall. Here again, 2 milliseconds. Expansion to a given length is unique, meaning we can directly go to what is the superperiod, known to be the least common multiple of the periods, and find that type we actually need to check to be T3. This is exactly what we end up doing in our implementation via some nice encodings into Rust's trait system. And yeah, the Rust part. So this is actually a snippet from our artifact representing that section of the pipeline there. A little dense, so I'm going to focus your attention on 3 pieces here. One of which is how we encode processes. The processes representing the tasks become Rust functions. Now that periodic construct necessarily has some timing information, which we encapture via that annotation on the process there. The channels have session types, and those session types directly become Rust types, with a Rust syntax that directly mirrors the syntax we use in the paper. Finally, communications are now effectively methods on those channel objects, and to get the linear behavior we need, we return a continuation. And there's some fun stuff we do in the implementation to make sure that this continuation gives us full linearity built on top of the substructural type system of Rust. And again, I mean, that's the implementation. We go through a bunch of examples in the paper, the implementation, and then we prove some very nice properties about that implementation. I will call out, we have a formal definition of error and lack thereof. And then what we end up with is the debugging board you see on the left there. That's the debug version that we built our implementation on. And then I managed to port that to the release version, which is currently running on my wrist. And we have an artifact for that. Rust is fashionable. Types is fashionable. If you want to be fashionable, put some types on your wrist.
Thanks for the enthusiastic presentation. Some questions for
Is it decidable, your compatibility relation? Namely,
Yes.
if you nest, no problems on nesting
No problems on nesting because we don't allow it. So critically, that no nesting captures the requirement that those periods are statically known. If you could nest, you could switch periods via mutual recursion, and that doesn't really mirror what we wanted to capture.
I think you may have just answered it, but just to clarify, does this mean that you don't support, say, instead of expanding one task with periodicity 1 into, kind of 2 calls with periodicity 2, does it mean you don't support then having, say, 2 separate tasks, each with periodicity 2, say they kind of alternate sending to one receiver with that periodicity 2?
Yeah, so you can't get that directly, partially because our channels are binary. There have to be exactly 2 tasks talking on a channel. In many cases, you can get similar behavior using those branching constructs I mentioned earlier. They don't show up in this simple example, but we do have some examples that use that. That gives you kind of some runtime decision about how the protocol is going to progress.
Okay, thanks.
Very cool work. I have a small question about all the other things that you are doing in your Rust code. Do you have something in the paper that also describes the timing of the normal code that you're executing, and whether it's in sync with timings that your types are representing?
So one of the key modeling decisions is we effectively assume the computation takes a negligible amount of time. And in a lot of these systems, that more or less ends up being true. You'd like to be asleep, not doing computation. So the one thing we effectively rely on is a runtime primitive for wake me up every, say, 1 second. And that's the thing, that was the wait for next period thing. That is how we incorporate timing at runtime. In the Rust, it gets pulled directly off that annotation and handed over to the threading at runtime.
Okay, let's thank Grant again. And thank you everybody for being here. I hope you enjoy Uppsala. See you in the next edition.